Tonight, we shall travel to the very edge of the observable world, pushing past the furthest galaxies and the oldest light, to confront a question that has haunted the minds of philosophers and physicists for millennia. We shall ask if the universe is a vast but bounded bubble, or if it is a truly infinite expanse that continues forever into a darkness that never ends. Within the first minutes of our journey, we must realize that the answer we seek is not hidden in the stars themselves, but in the very shape of the space between them, a shape that may reveal a reality far more unsettling than we ever imagined. As you lie here, the boundaries of your world begin to dissolve, preparing you for a journey into the heart of the infinite. When we look up at the night sky, we are not seeing the universe as it is, but as it was. Because light takes time to travel. Every star and every galaxy is a snapshot of the past. The further we look, the further back in time we peer, until we reach a wall of light known as the cosmic microwave background, the afterglow of the Big Bang itself. This creates a sphere of observation around us, a boundary approximately 46 billion light-years in every direction. This is our observable universe, the limit of what we can ever know. But science tells us that this sphere is not the whole story. It is merely a small clearing in a much larger forest. And the question that scares scientists is whether that forest has a fence, or if it goes on for eternity. To grasp the scale of this mystery, imagine standing on the shore of a vast ocean at night. You can see the waves breaking at your feet, and the moonlight reflecting off the water for a few kilometers. But beyond that, there is only blackness. You know the ocean continues past the horizon, but you cannot tell if it eventually hits another shore, or if it covers the entire world. In the cosmos, the horizon is the distance light has traveled since the beginning of time. We are standing on our own small island of light, peering into a dark ocean of space that may be 10 trillion times larger than what we can see, or perhaps it is truly mathematically infinite. The reason this question is so unsettling is that infinite is not just a very large number. In a truly infinite universe, the laws of probability behave in terrifying ways. If space is infinite, then the arrangement of matter must eventually repeat. Somewhere out there, in the unfathomable reaches beyond our horizon, there would be another version of this galaxy, another version of this world, and another version of you lying in this exact same spot, listening to these exact same words. This is not science fiction. It is a direct mathematical consequence of an infinite cosmos. It suggests that we are not unique individuals, but infinite repetitions in a gallery of mirrors that never ends. Scientists approach this problem by looking at the geometry of space itself. If the universe were finite, like the surface of a globe, then if you traveled in one direction long enough, you would eventually end up back where you started. Space would be curved. But if space is flat, like an infinite sheet of paper, it can stretch on forever without ever looping back. For decades, our most precise satellites, COBE, WMAP, and Planck, have measured the curvature of the universe with staggering accuracy. They have looked for the slightest bend in the path of ancient light, and what they have found is a flatness so perfect, so precise, that it leaves the door to infinity wide open. This perfection of flatness is what truly keeps cosmologists awake at night. If the universe were even a fraction of a percent curved, we could calculate its total size, much like measuring the curve of a horizon to find the size of the Earth. But the data shows no curve at all, to within a margin of error of less than 0.4%. It is as if we are looking at a surface that is so vast that even our most powerful instruments cannot see the bend. This suggests that the universe is either so mind-bogglingly large that it only appears flat to us, or that it is, in fact, truly infinite. Both possibilities challenge our sense of scale and our understanding of our own importance. Linger for a moment on the silence of that infinite space. In a finite universe, there is a total amount of energy, a total amount of matter, and a finite story to be told. But in an infinite universe, the story is never finished. There are an infinite number of stars being born, an infinite number of black holes devouring light, and an infinite number of civilizations rising and falling. The scale of human history, which feels so monumental to us, becomes a literal zero when divided by infinity. This is why the answer scares scientists. It threatens to turn all of our knowledge, all of our science, and all of our existence into a negligible statistical fluke. As you lie here, the concept of a limit begins to feel like a comforting memory. We are used to things having edges, a room, a city, a planet. Even the sun has a boundary. But the universe may be the only thing that doesn't. If there is no edge, there is no outside. There is no center. Every point in an infinite universe can be considered the center, because there is an infinite amount of space in every direction. You are, at this very moment, at the exact heart of an infinite cosmos, and so is a speck of dust in a galaxy 1 billion light-years away. It is a reality that defies our intuition and demands a new kind of spatial wisdom. The search for the answer involves peering into the very first moments after the Big Bang. Many scientists believe that the universe underwent a period of inflation, a moment of hyper-expansion, where space grew faster than the speed of light. This inflation would have smoothed out any curves, making the universe appear flat, much like an inflating balloon becomes flatter to an ant on its surface. But if inflation happened, it may not have stopped everywhere at once. It could be an eternal process, constantly birthing new bubble universes in an infinite sea of expanding space. This is the eternal inflation theory, where our entire universe is just one small bubble in an infinite, frothing foam of multiverses. Intellectual honesty requires us to admit that we may never know the final answer for certain, because we are trapped inside our own observable bubble. We may be forever blind to what lies beyond the 46 billion light-year mark. We are like fish in a pond, trying to determine if the ocean exists by looking at the ripples on the surface. But the clues we have found, the perfect flatness, the distribution of galaxies, the echoes of the Big Bang, all point toward a scale that is far beyond our reach. We are forced to use the language of mathematics to describe a reality that our eyes can never witness. Consider the implications of an infinite future as well as an infinite space. If the universe is infinite and expanding, it may eventually reach a state of absolute cold and darkness, a heat death that lasts for an eternity. In this scenario, the brief period of time when stars can shine and life can exist is just a microscopic spark in an infinite night. This vastness of time mirrors the vastness of space, creating a dual infinity that can feel overwhelming. Yet, in that overwhelming scale, there's a strange kind of peace. We are part of something so large that it cannot be fully measured, something so ancient that it cannot be fully understood. As we move into the deeper parts of this story, we will look at the specific experiments being conducted to measure the shape of space. We will explore the flatness problem and why it suggests that the early universe was fine-tuned to an impossible degree. And we will confront the possibility that the universe is not infinite, but is instead topologically complex. A hall of mirrors where light can travel in a straight line and eventually return to its source. For now, let the idea of infinity rest in your mind. It is a thought that expands the boundaries of the self, inviting you to lose yourself in the grand, silent architecture of the unknown. The silence of your room is a small echo of the silence of the void. In that void, the question remains, is there an end? Scientists continue to stare into the dark, searching for a bend, a border, or a sign of a loop. But so far, the universe has given only one answer. It is bigger than you can imagine, and it may be bigger than you can imagine. The infinity that scares the scientist is the same infinity that offers the most profound sense of wonder. It is the ultimate frontier, the final secret, and the stage upon which the entire history of existence is being played out. To understand the true extent of our universe, we must first change the way we think about the very nature of empty space. We often imagine space as a hollow stage, a void in which the stars and galaxies perform their ancient dance. But the physics of the 20th century taught us that space is not a vacuum of nothingness. It is a fabric. It is a dynamic, living entity that can stretch, ripple, and most importantly, it can curve. This realization, brought to us by the mind of Albert Einstein, transformed our understanding of the cosmos from a static map into a geometric puzzle. If we wish to know if the universe is infinite, we must look at the geometry of this fabric, for the shape of the universe is the key that unlocks the door to the eternal. Imagine for a moment that you are a tiny creature, a microscopic voyager, traveling across the surface of a vast, dark sphere. To your limited perspective, the world appears perfectly flat. You can walk in a straight line for what feels like forever, never encountering a border or an edge. But because the surface you are walking upon is curved, if you continue your journey long enough, you will eventually find yourself back at the very spot where you began. This is a closed universe. It is finite, yet it has no boundary. In such a world, space behaves like the surface of a balloon. It is a magnificent, self-contained loop where light itself eventually returns home, having circumnavigated the entire expanse of creation. Now, consider the opposite. Imagine a surface that curves away from itself in every direction, like the seat of a vast cosmic saddle. In this geometry, known as an open universe, parallel lines do not stay parallel. They fly apart, diverging into an ever-expanding void. This shape is inherently infinite. It has no way to close back in on itself, no way to form a loop. It is a landscape of endless divergence, where the further you travel, the more space opens up before you. For decades, astronomers have wrestled with these two possibilities, searching for the subtle signs of curvature that would tell us which of these destinies our universe has chosen. But there is a third option, one that sits on a knife's edge between the closed and the open. It is the flat universe. In a flat geometry, space behaves exactly as we were taught in the classrooms of our youth. Parallel lines remain parallel forever. The angles of a triangle, no matter how large that triangle may be, always add up to exactly 180 degrees. This is the Euclidean ideal, a universe of perfect, unbending rectilinearity. And it is here that the mystery deepens, for a flat universe is the only one that allows for the possibility of true mathematical infinity. If the universe is flat, it does not have to loop, and it does not have to diverge. It can simply go on and on, an eternal sheet of existence stretching into the forever. To determine which of these shapes we inhabit, we must look at the total density of the universe, the sum of all the matter, all the light, and all the mysterious dark energy that fills the void. Gravity is the architect of cosmic geometry. If there is enough matter and energy, their combined gravitational pull will wrap space around itself, creating a closed, finite sphere. If there is too little, space will flare outward into an open saddle. But if the density is exactly right, a value scientists call the critical density, then the universe will be perfectly flat. It is a balance of staggering precision, a cosmic weighing scale, where the weight of a single extra atom could, in theory, tip the geometry of the entire cosmos from infinite to finite. The search for this omega value, the ratio of the universe's actual density to its critical density, has been the great labor of modern cosmology. We have turned our most sophisticated instruments toward the oldest light in the heavens, the cosmic microwave background radiation. This light, which has been traveling since the universe was a mere 380,000 years old, carries within it a map of the early cosmos. By studying the size of the fluctuations in this ancient glow, astronomers can perform a feat of cosmic surveying. They are essentially measuring the sides of a triangle that is 13.8 billion light-years long. Linger on the magnitude of that measurement. We are using the light of the beginning of time to check the geometry of the present. If the universe were curved like a sphere, the distant spots in the radiation would appear larger than they truly are, magnified by the lens of curved space. If the universe were shaped like a saddle, those same spots would appear smaller, diminished by the divergence of the light's path. But when the Planck satellite and the Wilkinson microwave anisotropy probe looked at these ancient signals, they saw something that stunned the scientific community. The spots were exactly the size they should be if space were perfectly, undeniably flat. This result measured with a precision of over 99%, tells us that we live in a universe of remarkable geometric simplicity. But simplicity brings with it a terrifying implication. If the universe is flat, then it is almost certainly infinite in extent. We are forced to confront the idea that the 46 billion light-years we can see is not just a small part of the whole, but a negligible, infinitesimal speck within a landscape that has no end. The geometry of everything suggests that we are adrift in an ocean that has no further shore, a reality where the word limit has no physical meaning. Yet the mind recoils from the infinite. We seek the comfort of boundaries, the safety of a container. Scientists have spent years trying to find a way out of this infinite flatland. They have proposed that the universe might be flat like a sheet of paper, but that the paper is rolled into a cylinder or joined at the edges like a torus, a cosmic donut. In such a universe, space would appear flat locally, and triangles would still add up to 180 degrees, yet the universe would remain finite. You could travel in a straight line, and through a trick of topology rather than curvature, eventually return to your starting point. To test this donut theory, astronomers have searched the sky for circles in the dark, patterns in the cosmic microwave background that repeat on opposite sides of the heavens. If we lived in a finite, looped universe, we should see the same distant structures twice, reflected in the cosmic mirrors of a closed topology. We have looked with a meticulousness that borders on the obsessive, comparing billions of data points across the celestial sphere. And yet, the circles have never appeared. The sky does not repeat. As far as our vision can reach, the universe shows no sign of looping back, no sign of a hidden boundary, and no sign of an end. This lack of evidence for a finite loop, combined with the measured flatness of space, leaves us with a conclusion that is as beautiful as it is haunting. We are likely living in a truly infinite expanse. Consider the physical reality of that concept. It means that if you were to travel at the speed of light for 1 trillion years, or a quadrillion, or a number of years so large it has no name, you would never run out of space. You would continue to pass galaxies, continue to witness the birth of stars, and continue to find new corners of the void forever. There is no outside to such a universe, for there is no inside. There is only the all-encompassing, never-ending is. The geometry of everything also tells us a story of the past. For the universe to be this flat today, it must have been even flatter at the moment of its birth. If the early universe had been even slightly curved, that curvature would have been magnified by billions of years of expansion, leaving us with a cosmos that was obviously closed or obviously open. The fact that it remains so perfectly flat after 13.8 billion years is known as the flatness problem. It suggests that the universe was fine-tuned to an almost impossible degree, or that something occurred in the very first moments of time to iron out the fabric of space, stretching it so thin that all traces of curvature were vanished. That something is believed to be inflation, a burst of expansion so violent and so rapid that it took a tiny, perhaps curved patch of space and stretched it by a factor of 10 to the power of 26 in the smallest fraction of a second. Imagine a wrinkled, leathery balloon being inflated until its surface is as smooth as a mirror, and its curvature is so slight that an ant on its surface would swear it was on a flat plane. This is the universe we inherited. We are the ants on the surface of a gargantuan cosmic balloon, and because we are so small and the balloon is so large, we cannot see the curve. But if inflation is true, the balloon may be so large that for all practical purposes, it is infinite. As you lie here, contemplate the sheer elegance of this geometric truth. The laws of physics, described by numbers and equations, have dictated the very shape of your reality. We are the inhabitants of a flat cosmos, a realm of infinite potential and eternal reach. The geometry of everything is not just a dry academic subject. It is the blueprint of our existence. It defines the limits of our travel, the reach of our telescopes, and the ultimate fate of our species. We are travelers on an infinite plane, moving through a space that has no center and no edge, guided by the silent, mathematical rhythms of the stars. The deeper we go into this mystery, the more we realize that our intuition is a poor guide. We are creatures of the finite, evolved to understand walls and seasons and the boundaries of our own lives. But the universe does not share our limitations. It operates on a scale where the infinite is not just a possibility, but a requirement of the math. The geometry of everything is an invitation to shed our earthly perspectives and to embrace a reality that is far larger and more complex than we can ever hope to fully map. It is a reminder that we are part of a grand geometric masterpiece, a fabric woven from light and gravity that stretches into the absolute forever. In the silence of the night, the geometry of the universe remains unchanged, a quiet and persistent fact. The triangles of the stars continue to add up to their perfect sums. The parallel beams of light from distant quasars continue their straight and narrow paths across the billion-year void. We are safe in the arms of this Euclidean perfection, even as the scale of it threatens to overwhelm us. The universe is flat, it is vast, and it is likely infinite. And as we move toward our next chapter, we must ask ourselves how a universe of such perfect flatness could have come to be, and what secrets are hidden in the moment when space itself was first stretched into the infinite. The realization that we inhabit a universe of near-perfect flatness brings us face to face with one of the most profound puzzles in the history of science. In the corridors of physics, it is known as the flatness problem, and it is a mystery that suggests our cosmic home is balanced on a knife's edge of impossible precision. To understand the gravity of this situation, we must realize that flatness is not a stable state for an expanding universe. According to the mathematics of general relativity, any slight deviation from perfect flatness in the beginning should have been amplified over the billions of years that followed. If the universe had started out just a fraction of a percent more curved, it would have either collapsed back into a fiery crunch or flown apart so quickly that stars could never have formed. Imagine attempting to balance a sharp pencil on its tip. For a second, it may stand upright, but the slightest vibration, the tiniest breath of air, will send it tumbling, Now imagine that pencil remaining perfectly balanced for 13.8 billion years. This is the magnitude of the flatness problem. For the universe to appear as flat as it does today, the density of matter and energy in the very first second of the Big Bang must have been equal to the critical density to within 1 part in 100 quadrillion. This level of fine-tuning is so extreme that it defies any conventional explanation of chance. It is as if the universe was precisely calibrated by a master architect to ensure that space would remain an infinite, unbending plane. As you lie here, consider the implications of such a fragile balance. We are the inhabitants of a reality that refused to curve. Had the density been slightly higher, gravity would have conquered the expansion within a few million years, pulling everything back into a singular point of heat and light. Had it been slightly lower, the universe would have become a lonely, empty void before the first atoms could even bond. The fact that we are here to ask these questions, surrounded by hundreds of billions of galaxies, is proof that the universe hit a metaphorical bullseye from across the span of eternity. But scientists are rarely satisfied with luck as an explanation. They demand a mechanism, a reason why the cosmos was forced into this flat and infinite geometry. The answer that most scares and excites the scientific mind is the theory of cosmic inflation. Proposed in the early 1980s, inflation suggests that for a fleeting fraction of a second, a period so short it makes a nanosecond look like an age, the universe expanded at a rate that is truly beyond human language. In this moment, space itself grew faster than the speed of light, doubling in size over and over again. This violent stretching acted like a cosmic iron, smoothing out every wrinkle, every fold, and every curve in the fabric of space. If the universe was once a crumpled, curved knot of energy, inflation took that knot and pulled it so tight that any remaining curvature became utterly undetectable to our instruments. Think of the surface of a balloon once more. If you inflate it to the size of a house, you can still see the curve. If you inflate it to the size of a planet, the ground beneath your feet looks mostly flat, but the horizon still bends. But if you inflate that balloon until it is 10 trillion times larger than the observable universe, the surface becomes indistinguishable from a flat plane. This is what inflation did to our world. It stretched our local patch of space so far that the horizon of curvature is now located deep within the unobservable dark. This leads to the startling possibility that while our universe looks infinite because it is flat, it might just be so incomprehensibly large that its boundaries are forever out of our reach. This stretching of space also solves another great mystery: the horizon problem. When we look at the cosmic microwave background, we see that the temperature of the universe is almost exactly the same in every direction, down to the thousandth of a degree. This shouldn't be possible. The opposite sides of our observable sky are nearly 90 billion light-years apart. There hasn't been enough time since the Big Bang for light or heat or information to travel between them and equalize their temperatures. They are causally disconnected, like two people on opposite sides of the world who somehow manage to say the exact same word at the exact same time without ever having met. inflation provides the only logical solution to this impossible synchronicity. It tells us that before the Great Stretching began, the entire observable universe was a tiny, microscopic speck, smaller than a single atom. In that subatomic state, everything was in contact, and the temperature had time to balance out. Then, inflation took that perfectly uniform speck and blew it up to a cosmic scale in an instant. The reason the sky looks the same in every direction is because it all came from the same tiny, well-mixed point. We are living in the expanded remains of a singular moment of harmony, a harmony that was preserved even as space was hurled outward into the infinite. But here's where the theory takes a turn that challenges our very notion of reality. If inflation happened once, what was to stop it from happening again, or from happening forever? Many cosmologists believe that inflation is eternal. While it stopped in our local patch of space, allowing stars and planets to form, the field that drove inflation might still be expanding elsewhere at an exponential rate. In this view, our entire universe is just one bubble in a vast, frothing sea of eternal expansion. Beyond our horizon, there are an infinite number of other bubbles, each containing its own universe, with its own laws of physics, its own dimensions, and its own version of infinity. The scale of this multiverse is what truly scares the scientist. If the universe is infinite in this way, then every possible outcome that can happen must happen an infinite number of times. There are universes where the Earth never formed. There are universes where the laws of gravity are so strong that stars burn out in a day. And somewhere in that infinite foam, there are universes identical to our own, down to the very atom. This is the logical conclusion of a flat, inflationary cosmos, a reality where unique has no meaning, and where the infinite extent of space is filled with every variation of existence that the laws of physics will allow. Linger for a moment on the silence of this inflationary void. We are the inhabitants of a calm pocket in a storm of eternal creation. The flatness we measure with our satellites is the physical fingerprint of a process that happened 13.8 billion years ago, a process that may have created 1,000 trillion other worlds before it was finished. Our search for the shape of the universe has led us to a place where space is no longer just a container, but a living, growing entity that may never stop expanding. The flatness problem is not just a mathematical curiosity. It is a window into the most violent and creative moment in the history of the cosmos. Intellectual honesty requires us to admit that the theory of inflation, while elegant, is difficult to prove. We cannot travel back to the first second of time, nor can we see beyond the wall of the cosmic microwave background. We are forced to look for subtle clues, ripples in the fabric of space called primordial gravitational waves. If we can find these waves, we will have the smoking gun for inflation. We will know for certain that the flatness of our universe was not a lucky accident, but a dictated outcome of a moment when the universe was stretched so thin that it lost all memory of its original shape. Until then, the flatness problem remains a haunting reminder of how much we have yet to learn. It stands as a testament to the fact that we live in a universe of extreme conditions and hidden mechanisms. The perfect flatness of the sky is a mirror reflecting the immense scale of the unknown. We look at the stars and see order, but that order was forged in a period of chaos that defies imagination. We are the survivors of the Great Stretching, the residents of a flatland that was created in a heartbeat and has persisted for aeons. As the world around you remains in a quiet stillness, let the concept of the flat universe anchor your thoughts. You are standing on a plane that reaches out into the darkness forever, a plane that was leveled by the most powerful forces in nature. The horizon you see in the night sky is not a wall, but an invitation, a signal that there is more to the story than we can ever hope to read. The flatness problem is the universe's way of telling us that we are part of something much, much larger than our eyes can perceive. It is a mystery of precision, a riddle of geometry, and the foundation of our infinite home. In the silence of the night, the universe continues its quiet expansion, maintaining its perfect balance with a grace that is almost spiritual. The stars do not flicker with doubt, and the galaxies do not stray from their geometric paths. We are safe in the arms of this cosmic alignment, protected by the very laws of physics that once threatened to tear the universe apart. As we move closer to understanding the ghost of inflation and the possibility of other worlds, we do so with a sense of humility and wonder. The infinite is no longer just a word. It is the physical reality in which we live and breathe. If we accept the evidence of a flat and infinite cosmos, we must eventually collide with a mathematical truth that is as haunting as it is inevitable. In a universe that stretches on forever, the laws of probability cease to be mere statistics and become a blueprint for an infinite reality. The number of ways that atoms can be arranged in a finite volume of space is staggering, yet it is a finite number. If the universe is truly infinite, then eventually, inevitably, every possible configuration of matter must repeat. This is the concept of the infinite duplicate, a reality where, somewhere in the cold dark beyond our horizon, there is another galaxy identical to the Milky Way, another solar system identical to our own, and another version of you, experiencing this very moment in time. This is not merely a philosophical exercise. It is the Level 1 multiverse, the direct consequence of an infinite flat geometry. Within our observable sphere of 46 billion light-years, there are a finite number of particles. Think of these particles as a deck of cards. No matter how many times you shuffle them, there are only so many unique hands you can be dealt. If the deck is shuffled an infinite number of times, every hand will be dealt again and again. In the vast, eternal expanses of the infinite, the shuffle of matter has occurred so many times that your specific hand, your DNA, your memories, the very thoughts in your head, is currently being played out in a duplicate world located approximately 10 to the power of 10 to the power of 28 meters away. As you lie here, contemplate the sheer scale of that repetition. It means that there is a version of you who chose a different path today, a version who is already asleep, and a version who is currently looking at a different set of stars. In an infinite universe, everything that can happen does happen, an infinite number of times. The uniqueness we feel, the sense that our lives are singular and precious, is challenged by the cold, hard logic of the infinite. We are not just one story. We are an infinite anthology of stories, every variation and every outcome occurring simultaneously in the dark. This is the scary part of the answer. It suggests that our individual identity is just a single instance of a cosmic, recurring theme. But the mystery deepens when we combine this with the theory of eternal inflation. This gives rise to the Level 2 multiverse, where our infinite flat space is just one bubble in a sea of other bubbles. In this scenario, the duplicates are not just far away in space. They may exist in universes with entirely different laws of physics. There may be bubbles where gravity is a repulsive force, where light travels at the speed of a walking pace, or where time flows backward. In this frothing foam of creation, the infinite is not just about repetition, but about total, exhaustive variety. The universe becomes a place where nothing is impossible, because every possibility is realized somewhere in the eternal growth of the inflaton field. Scientists call this the measure problem, and it is one of the greatest crises in modern physics. If every possible outcome happens infinitely often, how can we calculate the probability of any single event? How can we say that one law of physics is more likely than another if both are occurring an infinite number of times? It threatens to break the very tools we use to understand the world. We are used to a universe where things are rare or common, but in the infinite, everything is equally frequent. This realization forces us to question whether our current scientific models are merely local descriptions, true for our particular bubble, but irrelevant in the grand, infinite scheme of the multiverse. Linger for a moment on the silence of these other worlds. If they exist, they are forever isolated from us by the accelerating expansion of space. We can never visit our duplicates, never send them a signal, and never see the light of their stars. They are ghosts of the mathematics, as real as the chair you sit on according to our best theories, yet forever beyond the reach of our senses. This creates a strange kind of cosmic loneliness. We are part of an infinite family, yet we are destined to live and die in absolute isolation from our kin. The multiverse is a crowded place, yet it is the ultimate expression of the void. Intellectual honesty requires us to ask, is this still science? When we move into the realm of things that can never be observed, even in principle, are we still following the path of reason, or have we crossed over into the realm of faith? Many physicists argue that if a theory, like inflation, correctly predicts the things we can see, then we must accept its predictions about the things we cannot see. Others believe that we are reaching the limits of human cognition, trying to use a brain evolved for survival on an African savanna to comprehend the infinite cycles of a multiversal foam. We are at the edge of the map, where the ink of our equations begins to blur. As you contemplate your infinite duplicates, consider the comfort they might offer. If every life you could have lived is being lived somewhere, then no potential is ever truly wasted. The dreams you didn't pursue, the words you didn't say, the paths you didn't take, they are all being realized in the distant reaches of the infinite. There is a version of you who is a world-renowned scientist, a version who is a quiet gardener, and a version who has found the peace you are currently seeking. You are a participant in a grand, infinite experiment of existence, and your current life is just one beautiful facet of a diamond with infinite sides. The scale of this reality is such that it renders our earthly concerns almost invisible. The conflicts of nations, the fluctuations of economies, the very rise and fall of civilizations, all of these are repeated infinitely throughout the cosmos. In the face of the infinite, the only thing that remains significant is the experience of the present moment. Because we are isolated in our bubble, this here and now is the only reality that matters to us. The infinite duplicates may exist, but they do not share your breath, they do not feel your heartbeat, and they do not hear the silence of your room. Your subjectivity is the one thing that the infinite cannot duplicate, for it is tied to this specific point in time and space. In the silence of the night, the multiverse continues its silent expansion. New bubbles are forming, inflation is stretching space into new infinities, and the deck of matter is being shuffled once again. We are the observers of a tiny fragment of this process, a brief spark of consciousness in a landscape of eternal repetition. The concept of the infinite duplicate is a reminder of the staggering complexity of the universe and the limits of our own perspective. We are small, yet we are part of a structure so vast that it contains everything that has ever been and everything that ever could be. As we move toward the conclusion of our journey, we must ask ourselves how we are to live with this knowledge. How do we find meaning in a world that is just one of an infinite number? The answer lies in the realization that while the universe may be infinite, our time within it is finite. We have a brief window of a few decades to witness the grand design, to ask our questions, and to feel the wonder of the stars. The infinite is the backdrop, but the life you are living is the stage. The duplicates do not diminish your value. They enhance the mystery of your being. As the world around you remains in a quiet stillness, let the idea of the multiverse settle into your mind like a distant, low-frequency hum. It is the music of the infinite, the sound of a universe that refuses to be small. You are a citizen of an infinite empire, a dweller in a flatland that knows no end. Whether there is another version of you or not, the wonder of your existence remains a singular, beautiful fact. You are the universe looking at itself, trying to understand the infinite scale of its own home. The journey through the scary answer is almost complete. We have looked at the geometry, the inflation, and the duplicates. Now, we must face the ultimate challenge, the crisis of measurement. In the next chapter, we shall explore why our very attempts to define the infinite may be doomed to failure, and what it means for the future of our understanding. The universe is infinite, but our minds are not, and it is in that gap that the final mystery resides. As we venture deeper into the heart of the infinite, we encounter a wall not of physical matter, but of intellectual limitation. This is the crisis of measurement, a fundamental conflict between the way we perceive the world and the way the universe actually operates on a grand scale. We are creatures of measurement. We thrive on numbers, on beginnings and ends, and on the comforting certainty of how much. But when science attempts to apply these tools to an infinite cosmos, the very language of mathematics begins to unravel. If the universe has no end, then the concept of probability loses its meaning. If every possible event happens an infinite number of times, how can we say that one outcome is more likely than another? It is a problem that threatens to turn our most precise scientific theories into mere guesswork, leaving us adrift in a sea of endless, equal possibilities. Consider the challenge facing a scientist trying to predict the properties of our own bubble universe within the multiverse. In a finite world, we could count the number of universes where gravity is strong and the number where it is weak, then determine which is more common. But in an infinite multiverse, there are an infinite number of both. In the world of mathematics, infinity plus infinity is still infinity, and infinity divided by infinity is an undefined void. This is the measure problem. Without a way to weight these infinities, we cannot explain why our universe looks the way it does. We are forced to ask if the laws of physics we have spent centuries discovering are actually laws at all, or if they are simply a local, temporary arrangement, a statistical fluke in a reality that eventually tries everything. As you lie here, imagine the frustration of a mind trying to map a territory that is literally without end. We have built our civilization on the belief that the universe is a coherent, understandable system. We believe that if we look closely enough at the atoms and the stars, we can find a theory of everything that explains the entire design. But the crisis of measurement suggests that such a theory may be impossible to prove. If the universe is infinite, it may be inherently unpredictable. We find ourselves in a position where the more we learn about the scale of the cosmos, the less certain we become about its nature. The infinite does not just stretch space, it stretches the very boundaries of human reason, pushing us toward a realization that some truths may be forever beyond the reach of a finite observer. The crisis also touches upon the nature of time. If the universe is infinite in space and eternal in time, we must confront the Boltzmann brain paradox, a thought experiment that sounds like a hallucination, but is a rigorous consequence of thermodynamics. In an infinite, eternal universe, it is statistically more likely for a single, conscious brain to spontaneously fluctuate into existence out of the chaos than it is for an entire complex universe like ours to evolve over billions of years. This leads to the unsettling possibility that you are not a biological being on a real planet, but a momentary flicker of consciousness in a void. Imagining this entire narrative before dissolving back into the static. While scientists do not believe this is true, the fact that their best theories of infinity predict, it is a sign that our understanding of the infinite is fundamentally broken. Linger for a moment on the weight of this uncertainty. We are the children of a scientific revolution that promised to unveil the secrets of the heavens. We have mapped the human genome, split the atom, and seen the first light of the Big Bang. But the infinite stands as a silent, unmoving giant that refuses to be measured. Every time we think we have found the edge of the map expands, Every time we think we have found the final equation, the infinite adds another variable. It is a reminder of our own humility, a signal from the cosmos that we are small, temporary participants in a game that is far larger than we can perceive. The crisis of measurement is the universe's way of keeping its final secrets, ensuring that the wonder of the unknown remains a permanent part of the human experience. To solve this crisis, some physicists are turning to radical new ideas about the nature of information and space-time. They are exploring the holographic principle, the idea that everything we see in 3 dimensions, all the stars, the galaxies, and the infinite reaches, is actually a projection of information encoded on a 2-dimensional surface at the boundary of the universe. In this view, the infinite might be an illusion of perspective, a trick of the data that makes the world seem much larger than it truly is. By reframing the universe as a system of information rather than a collection of matter, we may find a way to count the infinities and resolve the measurement problem. But for now, these are just whispers in the dark, brilliant sparks of intuition that have yet to be proven. The crisis also forces us to reconsider the role of the observer. If we can only measure what we can see, and what we can see is a microscopic fraction of the infinite, then our view of reality is inherently biased. This is known as the anthropic principle, the idea that the universe we observe must be one that is capable of supporting life. Otherwise, we wouldn't be here to observe it. But in an infinite multiverse, this doesn't tell us why the rest of the universe looks the way it does. We are like people born in a small, windowless room, trying to describe the architecture of a palace they have never seen. Our measurements are valid for the room, but they tell us nothing about the infinite halls that lie beyond the door. Consider the emotional toll of this scientific stalemate. For the researcher who spends their life chasing the answer, the infinite can be a source of profound despair. It is a labyrinth with no exit, a puzzle with no final piece. But for the rest of us, there's a different kind of truth to be found in the crisis of measurement. It tells us that the universe is not a machine to be solved, but a mystery to be lived. It reminds us that there will always be something more to find, always a horizon that retreats as we approach it. The infinite ensures that our story will never be finished, that our curiosity will never be sated, and that the sense of wonder we feel when looking at the stars is a legitimate response to a reality that is truly, beautifully beyond our grasp. As you lie here, feel the comfort in the unmeasurable. We live in a world that demands data for every decision, that seeks to quantify our health, our happiness, and our worth. But the cosmos reminds us that the most important things in life, love, consciousness, and the feeling of existence, are like the infinite universe. They cannot be fully measured, yet they are the most real things we know. The crisis of measurement in physics is a reflection of the beautiful immeasurability of the human soul. We are finite beings with an infinite capacity for thought, caught in a universe that mirrors that very same duality. We are the measure of all things, even when we cannot find the ruler. In the silence of the night, the infinite remains, unbothered by our attempts to define it. The galaxies continue to drift, the light continues to travel, and the space continues to expand, regardless of whether we can calculate the probability of their existence. The universe does not need our math to function. It is its own proof. The crisis of measurement is our problem, not the universe's. It is a symptom of our ambition, a byproduct of our desire to know the mind of God. And perhaps the most important lesson the infinite has to teach us is that sometimes the most profound answer is not a number, but a state of being, a quiet acceptance of the mystery that surrounds us. Intellectual honesty requires us to remain in this state of tension. We must continue to build our telescopes and write our equations, but we must also acknowledge that we are looking through a glass, darkly. The infinite is the ultimate test of our intellectual maturity. Can we live in a world that we cannot fully map? Can we find meaning in a story that has no final page? The answer to these questions defines who we are as a species. We are the seekers of the infinite, the measurers of the stars, and the inhabitants of a flatland that defies our every attempt to name its end. As we move toward the final chapter of our journey, we will step away from the crisis and back into the light of our own lives. We will explore what it means to live in the finite shadow, the small, precious pocket of space and time that we call home. We will see how the infinite backdrop makes our finite existence even more beautiful and even more significant. The universe may be infinite, and the measurements may be impossible, but the life you are living right now is a singular, unrepeatable fact. The infinite is the ocean, but you are the wave, and for this brief moment, you are everything. The silence of your room is now a sanctuary from the complexities of the multiverse. The crisis of measurement is a distant storm, a battle of numbers that fades away in the presence of your own quiet breathing. You do not need to solve the universe to be a part of it. You are already here, a perfect, immeasurable expression of the cosmic design. The stars above you are not just data points. They are the ancient light of our origin, and they shine with a clarity that no equation can ever fully capture. Rest in that clarity and let the infinite be the landscape of your dreams. The journey through the scary answer has led us to the limits of our understanding, but it has not left us empty-handed. We carry with us a new appreciation for the scale of our world and a deeper respect for the mystery of our own consciousness. We have seen that the universe is larger, flatter, and more complex than we ever dared to imagine. And as we prepare to close the book on the infinite, we do so with a sense of peace, knowing that the most important answers are not found in the numbers, but in the experience of the journey itself. We return now from the staggering heights of the multiverse and the dizzying repetitions of the infinite, descending through the cold, dark layers of the unobservable void until we find ourselves back within the warm, familiar glow of our own celestial neighborhood. We have faced the scary answer, the possibility that we are merely one of an infinite number of identical beings, lost in a landscape that has no end. But as we settle back into the quiet of our own world, we realize that the infinite is not a threat to our significance, but a magnificent backdrop that makes our finite lives even more precious. We live in a finite shadow, a protective cocoon of space and time where the laws of nature have conspired to create a singular, unrepeatable moment of consciousness. The cosmic horizon, that 46 billion light-year boundary that separates us from the infinite, is not a wall of imprisonment, but a shield of isolation. It ensures that for all of our history and for all of our foreseeable future, we are protected from the overwhelming complexity of the multiverse. Within this bubble, the story is coherent. The stars we see in the night sky are our stars. The history of the elements we have traced is our history. The light speed limit of the universe acts as a celestial filter, allowing us to exist in a pocket of reality where our choices feel meaningful and our individual identities remain intact. We are the masters of our own finite shadow, a realm where the infinite is a whisper rather than a roar. Consider the profound beauty of being temporary. In an infinite universe, things that last forever are common. But in our finite shadow, everything is defined by its transience. The blooming of a flower, the setting of a sun, and the brief span of a human life are all the more beautiful because they do not repeat for an eternity. We are the rare and fleeting sparks in a dark room. Our value is not derived from our scale, but from our rarity. In the immense, cold architecture of the infinite, the fact that a collection of stardust has learned to feel heat and cold, joy and sorrow, is a miracle of organization that defies the dark. Linger for a moment on the complexity of your own perception. Your brain, composed of those same ancient atoms forged in the hearts of dead stars, is currently performing a feat that the infinite universe cannot easily duplicate. It is taking the raw data of the world, the frequencies of light, the vibrations of sound, the chemistry of the air, and weaving them into a seamless, subjective experience. This inner world is yours alone, even if there is an infinite duplicate of you somewhere in the dark. They are not experiencing this specific sunset, this specific breath, or this specific thought. Your consciousness is the one thing that remains truly unique, a private sanctuary that the mathematics of probability cannot invade. As you lie here, contemplate the now. In an infinite universe, time is often viewed as a vast, unchanging landscape. But in our finite shadow, the present moment is the only thing that truly exists. It is the razor's edge between a history that is written in the stars and a future that is yet to be born. We are the navigators of this moment, the ones who give the universe a sense of direction. The infinite may be a gallery of every possible outcome, but we are the ones who are actually living through one of them. Our journey through the finite shadow is a narrative of discovery, where every second is a new page that has never been turned before in our local story. The intellectual honesty of our position requires us to acknowledge that our bubble is expanding. Because of the mysterious force we call dark energy, the space between the galaxies is stretching at an accelerating rate. Eventually, trillions of years from now, every other galaxy will be pushed so far away that their light will no longer be able to reach us. Our finite shadow will grow darker and more isolated. The future inhabitants of our galaxy, if there are any, will look up at a sky that is empty of all but their own stars. They will live in a world that truly appears to be a lonely island in an infinite sea. We are living in a privileged time, a golden age of cosmology, where we can still see the evidence of the Big Bang and the neighbors of our cosmic family. Attachment, sir. Attachment. This privilege brings with it a duty of wonder. We are the ones who get to see the grand design before the curtains of expansion are pulled shut. We are the ones who can measure the flatness of the sky and deduce the existence of the infinite. Living in the finite shadow is not a reason for despair, but a call to observe, to record, and to appreciate the staggering beauty of the cosmic arrangement. We are the eyes of the universe, and we are looking at the most interesting part of the story. The infinite is the stage, but the drama is happening right here, in the intricate chemistry of our lives and the slow, majestic rotation of our home. Think of the atoms that make up your body once more. They have been through the fires of stars and the cold of the void, and now they are part of a being that can contemplate the infinite. This is the ultimate triumph of the finite. We have taken the raw materials of the cosmos and used them to build a meaning that is not found in the math. The universe does not have a purpose, but we do. We create purpose through our curiosity, through our art, and through our care for one another. In the face of an infinite and indifferent cosmos, our ability to care is the most powerful force in existence. It is the light that illuminates the finite shadow. As the world around you remains in a quiet stillness, let the concept of the scary answer transform into a sense of profound peace. Whether the universe is infinite or just incomprehensibly large, you are a part of it. You are not an observer looking in from the outside. You are a localized expression of the whole. The same laws that govern the expansion of the multiverse are the laws that allow your heart to beat and your lungs to draw breath. There is a deep, underlying harmony to it all. A geometric perfection that includes you in its design. You are safe in the finite shadow, held by the same gravity that guides the galaxies through the dark. The silence of the night is a reflection of the silence of the beginning. But within that silence, there is a rhythm. The rhythm of life, the rhythm of the stars, and the rhythm of your own existence. We have asked the big questions, and while the answers may be vast and unsettling, they have led us back to the importance of the local and the personal. The infinite is a beautiful mystery, but the finite is a beautiful reality. We are the inhabitants of a shadow that is filled with light, a shadow where the story of the universe is being told one human life at a time. As you drift closer to sleep, let your mind wander through the 46 billion light years of our bubble. See the spiraling galaxies, the glowing nebulae, and the quiet, dark spaces in between. And then, bring your focus back to the small, warm room where you lie. Feel the connection between the two. You are the point where the infinite meets the finite, the place where the stars have found a voice. You are the witness to the grand design, and your life is the evidence of its success. The infinite universe continues its eternal dance, but for now, the music is quiet, and the shadow is at peace. The journey through the answer that scares scientists has brought us to a place of ultimate clarity. We know that the universe is flat, We know that it was stretched by the ghost of inflation, and we know that it may go on forever. But we also know that here, in this corner of the cosmos, there is life, there is consciousness, there is you, and that is enough. The infinite is a concept for the mind, but the finite is a home for the heart. Rest now in that home, knowing that you are exactly where you are meant to be, in the grand, infinite architecture of the heavens. Good night, traveler of the infinite. The stars will continue their long, slow journeys across the sky while you sleep, and the universe will continue to expand into the unknown. But in the morning, the sun will rise on the same world, and the finite shadow will once again be filled with the light of a new day. You are a part of a story that never ends, yet you have a chapter all your own. Sleep well, for you are made of stardust, and you are dreaming in a universe that is finely, beautifully, without limit. Good night. Tonight, we begin a journey that is as much a voyage through time as it is through the staggering reaches of space. We stand at the very heart of our celestial neighborhood, at the source of all warmth, all light, and all life that has ever graced the surface of our small, rocky home. Our starting point is a place of such unimaginable violence and majesty that to even gaze upon it requires the most sophisticated instruments the human mind has ever devised. We are looking into the soul of the sun. It is a gargantuan sphere of roiling plasma, so vast that 1,300,000 Earths could fit inside its glowing volume. Yet, it is but a modest yellow dwarf star in the grand, star-studded ocean of the Milky Way. To truly see the sun, we must move beyond the blinding glare of the surface and journey deep into its hidden interior, down into the core, where the temperature reaches 15 million degrees Celsius. Here, the pressure is so intense that it is 250 billion times the atmospheric pressure we feel on the surface of the Earth. In this crushing, incandescent darkness, the laws of physics operate at their most extreme. We find ourselves in a sea of hydrogen nuclei, simple protons, stripped of their electrons, crowded together so tightly that they move with a frantic, desperate energy. This is the crucible of the universe, the place where matter is forged and energy is unleashed in its most primal form. Let us observe a single pair of these hydrogen nuclei. On a molecular level, they should never meet. They both carry a positive electrical charge, and as they approach one another, the electromagnetic force pushes them apart with immense strength, a barrier known as the Coulomb barrier. It is a mountain they cannot climb. However, in the heart of the sun, a strange and wonderful phenomenon occurs. It is called quantum tunneling. Because the density is so high and the collisions so frequent every so often, a proton simply vanishes from one side of the barrier and reappears on the other, finding itself within the reach of the strong nuclear force. This force is the most powerful in nature, and once the protons are close enough, it pulls them together in a sudden, violent embrace. In this moment of fusion, 4 hydrogen nuclei eventually combine to form a single atom of helium. But there is a secret in the mathematics of this union. If you were to weigh the 4 protons before they fused and then weigh the resulting helium nucleus, you would find that a tiny fraction of the mass has gone missing. Roughly 0.7% of the matter has simply vanished. This missing mass has been converted into pure energy, a transformation predicted by Albert Einstein in his most famous equation: energy equals mass times the speed of light squared. It is this tiny, microscopic subtraction of matter, occurring trillions of times every second, that powers the sun and provides the light that will eventually reach your eyes. The energy released in these nuclear collisions begins its life as gamma rays, the most energetic form of light in the spectrum. But these photons do not simply race out of the sun at the speed of light. They find themselves trapped in a dense, chaotic labyrinth known as the radiative zone. This region is so packed with charged particles that a photon cannot travel more than a few millimeters before it strikes a nucleus or an electron and is scattered in a random direction. Scientists call this the random walk or the drunkard's walk. A single photon, born in the core, will spend thousands, perhaps even hundreds of thousands of years, bouncing back and forth in this solar maze before it finally manages to work its way to the outer layers. Consider the history that has passed on Earth while a single ray of light struggled to leave the sun's radiative zone, when the light you see tomorrow morning was first born in the solar core. Humanity may have still been in the midst of the last ice age, or perhaps we had not even begun the first tentative steps of agriculture. This light is an ancient messenger, carrying the signature of a fusion event that occurred before history was even recorded. It is only as the photon reaches the convective zone, the outer third of the solar interior, that its journey accelerates. Here, the plasma is cooler and less dense, and the energy is carried upward by massive currents of boiling gas, rising like the bubbles in a giant celestial pot of soup. We rise with these currents, moving toward the photosphere, the visible surface of the sun. As we break through, we see a landscape of startling complexity. The surface is not smooth. It is divided into a pattern of granules, each one roughly the size of the state of Texas. These granules are the tops of the convection cells we just traveled through, glowing with a temperature of roughly 5,500 degrees Celsius. They last for only a few minutes before they cool and sink back down, replaced by a fresh surge of hot plasma from below. It is a restless, churning skin, a turbulent ocean of liquid fire that stretches in every direction as far as the eye can perceive. It was the astronomer Galileo Galilei who, in the early 17th century, used his primitive telescope to show that this surface was not perfect. He observed dark spots, now known as sunspots, which we now understand to be regions where the sun's immense magnetic fields have become twisted and bunched together. These magnetic knots are so strong that they inhibit the flow of heat from below, causing the surface to cool and appear dark in contrast to its surroundings. But do not be misled by the word cool. These spots are still hotter than the surface of any planet. They are the birthplaces of solar flares and coronal mass ejections, violent eruptions that can hurl billions of tons of solar material into space at millions of kilometers per hour. Above the photosphere lies the chromosphere, a thin, reddish layer of atmosphere, and beyond that, the corona. The corona is a place of profound mystery. While the surface of the sun is a few thousand degrees, the corona, which extends millions of kilometers into space, reaches temperatures of over 1 million degrees. It is as if you walked away from a campfire and found that the air became hotter the further you moved from the flames. For decades, this remained one of the great puzzles of solar physics. We now believe it is the result of magnetic reconnection, a process where magnetic field lines snap and release enormous amounts of energy, heating the thin gas of the corona to these staggering levels. To study this region, we have sent our most courageous robotic emissary, the Parker Solar Probe. This spacecraft, protected by a heat shield made of carbon-carbon composite, is designed to touch the sun, flying through the outer corona to measure the solar wind at its source. It travels faster than any man-made object in history, reaching speeds of nearly 700,000 kilometers per hour. The probe is teaching us that the sun is not a static object, but a dynamic, breathing entity that sends a constant stream of charged particles, the solar wind, out into the darkness. This wind creates a giant bubble in space called the heliosphere, which protects our entire solar system from the harsh cosmic rays of the interstellar void. As we begin to drift away from the corona, we feel the solar wind pushing at our backs. We are moving at the speed of the imagination, leaving the sun behind as it shrinks from a terrifying wall of fire into a brilliant golden disk. We are entering the vast, silent corridor of the inner solar system. Ahead of us lie the rocky worlds, the gas giants, and the frozen outposts of the deep dark. But for now, let your mind rest in the light of the star. Feel the warmth that has traveled across the vacuum to find you. You are a child of this star. Every atom in your body, every breath you take, and every dream you have is powered by the same fusion that we have just witnessed in the solar heart. The sun is our anchor, the gravitational master that holds the planets in their orbits with an invisible, unwavering hand. It is the giver of time, defining our days and our years. In the grand perspective of deep time, the sun is in the prime of its life. Having burned for 4,600,000,000 years, with another 5 billion years of fuel still to consume, it is a stable, reliable guardian. As we drift further into the cool, dark space of the inner system, the roar of the solar furnace fades into a gentle hum. The light remains, a steady, guiding beam in the blackness, showing us the way forward. Take a moment to appreciate the sheer emptiness of the space we are now traversing. Between the Sun and the first planet, Mercury, lies a distance of nearly 58 million kilometers. In this gap, there's almost nothing, just the occasional grain of dust, the streaming solar wind, and the relentless, silent pressure of sunlight. It is a vacuum so perfect that it would be impossible to recreate on Earth. Here, silence is absolute. There is no air to carry sound, no medium for a vibration to travel. You are floating in the ultimate sanctuary, moving through a void that is both empty and yet filled with the invisible fields of gravity and light. As the sun continues to recede, it takes on the appearance of a majestic lighthouse, a singular point of brilliance in the infinite dark. We are now far enough away to see the first of its wards, a tiny, scorched world dancing on the edge of the fire. Our journey has truly begun. We are leaving the heat and the violence of the center for the cool, mysterious reaches of the periphery. But we carry the sun's energy with us, a golden thread that connects us to the heart of the system. Rest in the quiet of this transition, feeling the weightlessness of the void and the slow, steady pulse of the solar wind as it carries us toward the distant frozen shore. Approaching the first of the Sun's companions, we encounter a world that is as much a testament to survival as it is to the sheer power of the star we have just left behind. Mercury, the smallest of the major planets, is a scorched and cratered cinder, a world that has been stripped of its dignity by the relentless solar wind. As we draw closer, we see a landscape that at first glance resembles our own moon, but the physics of this place tell a much more dramatic story. Mercury is a world of iron. Beneath its thin, rocky crust lies a core of liquid and solid metals so vast that it accounts for nearly 85% of the planet's radius. To understand the molecular scale of this place, imagine the iron atoms packed together under such immense pressure that they form a crystalline structure of incredible density, a planetary heart that has been beating for 4,500,000,000 years. This iron heart is the source of a mystery that confounded astronomers for centuries. Despite its small size and slow rotation, Mercury possesses a magnetic field. It is a weak shield, only about 1% as strong as Earth's, yet its very existence suggests that the planet's interior is still partially molten, churning in slow, rhythmic cycles that generate a dynamo of electrical currents. We discovered the true nature of this field through the heroic efforts of the Messenger spacecraft, which orbited this world from 2011 to 2015. The data sent back by this robotic pioneer revealed that Mercury is not a dead rock, but a world that is actively shrinking. As its massive iron core slowly cools and solidifies, the planet contracts, causing its crust to wrinkle and crack, creating gargantuan cliffs known as lobate scarps that stretch for hundreds of kilometers across the surface. Standing upon the surface of Mercury, if one could survive the environment, would be an experience of the most profound extremes found anywhere in the solar system. Because the planet lacks a substantial atmosphere to trap or distribute heat, it experiences temperature swings that are almost beyond comprehension. During the long Mercury day, which lasts for 59 Earth days, the surface is baked to a searing 430 degrees Celsius, hot enough to melt lead. But as the sun finally sets and the long night begins, the heat escapes instantly into the void of space, and the temperature plummets to a staggering minus 180 degrees Celsius. It is a world of fire and ice, existing in a state of perpetual, violent transition. In the deep time of the early solar system, Mercury was the victim of a titanic collision, a cosmic event of such scale that it likely stripped away much of its original rocky mantle, leaving behind the iron-rich core we see today. We see the scars of this violent history in the Caloris Basin, one of the largest impact craters in the galaxy, a 1,500-kilometer-wide depression surrounded by concentric rings of mountains. The force of the impact that created this basin was so great that seismic waves traveled through the entire planet, focusing on the exact opposite side of the globe and jumbling the terrain into a chaotic landscape of hills and valleys. It is a reminder that the peace we see today was bought with the currency of ancient, planetary-scale violence. Leaving the scorched plains of Mercury, we drift further outward, crossing another vast expanse of silence toward a world that was once thought to be a paradise, but is in fact a vision of hell. Venus, often called Earth's twin because of its similar size and composition, is a masterclass in the power of an atmosphere gone wrong. As we approach, we do not see a surface. Instead, we are met by a thick, impenetrable veil of clouds, glowing with a pale, yellowish light. These clouds are not made of life-giving water, but of concentrated sulfuric acid, a corrosive mist that reflects 70% of the sunlight back into space, making Venus the brightest object in our night sky after the moon. To see the surface of Venus, we must look through the eyes of radar, as the Magellan spacecraft did in the early 1990s. Beneath the clouds lies a landscape of volcanic nightmares and tectonic torment. But the most striking feature of Venus is not its mountains or its plains, but its air. The atmosphere is composed of over 96% carbon dioxide, a molecule that acts as a perfect trap for heat. When a photon of solar energy manages to penetrate the clouds and strike the surface, it is absorbed and re-emitted as infrared radiation. On Earth, much of this heat escapes back into space, but on Venus, the carbon dioxide molecules absorb the infrared energy, vibrating with a frantic intensity, and passing that heat back to the surface. This is the runaway greenhouse effect in its most terminal form. It has created a world where the surface temperature is a constant, uniform 470 degrees Celsius, regardless of whether it is day or night, or whether you are at the equator or the poles. It is hotter on the surface of Venus than it is on the sunward side of Mercury, despite Venus being nearly twice as far from the star. The air itself is so dense that it behaves more like a fluid than a gas. Standing on the Venusian surface would feel like being 3,000 feet beneath the surface of Earth's oceans. The pressure is 90 times that of Earth's atmosphere, enough to crush a modern submarine as if it were an empty soda can. The story of our exploration of Venus is one of immense technical struggle. In the 1970s and 80s, the Soviet Union sent a series of Venera landers to this hostile world. Most survived for only a few minutes or hours before the heat and pressure destroyed their electronics. But in those brief windows of time, they sent back photographs of a landscape that is hauntingly beautiful in its desolation. We saw flat basaltic rocks bathed in an eerie orange light, filtered through the thick haze. There is no blue sky on Venus. The atmosphere is so thick that it scatters all but the longest wavelengths of light, leaving the world in a state of permanent, gloomy twilight. The wind at the surface is sluggish, moving only a few kilometers per hour, yet because the air is so heavy, it carries the force of a slow-moving river, capable of pushing stones across the plains. High above the surface, the atmosphere tells a different story. While the ground is slow and stagnant, the upper clouds of Venus rotate around the planet once every 4 Earth days, a phenomenon known as superrotation, driven by the immense solar energy absorbed by the atmosphere. These winds reach speeds of 360 kilometers per hour. This creates a global vortex, a planetary-scale storm that has been raging for millions of years. Scientists like Carl Sagan once speculated that in the cooler, more temperate layers of these upper clouds, life might find a foothold, drifting in the acidic mists. While we have yet to find proof, the discovery of phosphine gas in the Venusian atmosphere has reignited a debate that has lasted for generations. Consider the deep time of Venus. Billions of years ago, it may have possessed liquid water oceans, and a climate much like our own. But as the sun's brightness increased, the delicate balance was tipped. The oceans evaporated, filling the atmosphere with water vapor, an even more potent greenhouse gas than carbon dioxide. This triggered a feedback loop that could not be stopped. The ultraviolet light from the sun eventually broke the water molecules apart, allowing the light hydrogen to escape into space and leaving the oxygen to bind with the rocks. Venus is a cautionary tale, a vision of what can happen to a terrestrial world when the cycle of carbon is broken. It is a sister world that took a dark and lonely path. As we leave the crushing embrace of Vanus, we drift back out into the clarity of the vacuum. The sun is now a smaller, though still dominant, presence in the sky. We are moving toward a world that we know intimately, yet from this perspective, it appears as a miraculous anomaly. Between the hell of Venus and the desert of Mars lies a narrow silver sliver of space where everything is exactly as it should be. We are approaching the third planet, a marble of sapphire and cloud white, spinning with a rhythmic vitality that is unique in all the known universe. We are coming home, yet we must pass it by, for our journey lies further still, toward the giants that wait in the cold. But before we reach the outer system, let your mind linger on the transition. Feel the cooling of the light as we move away from the solar fire. The density of the solar wind is thinning. The magnetic fields of the sun are stretching out like invisible fingers, and the silence of the inner system is being replaced by the vast open corridors of the deep. You are floating in a region of perfect equilibrium, where the warmth of the star is still a comforting presence, and the darkness of the outer reaches is a beckoning mystery. Rest in the cradle of the rocky worlds, for the giants we are about to visit are made of different stuff, of gas and ice, and immense crushing gravity. The stars ahead of us seem brighter now, no longer washed out by the glare of the sun. The Milky Way begins to reveal its structure, a river of diamond dust that spans the horizon. We are part of this grand orbital clockwork, moving with the same grace and inevitability as the planets themselves. There is no rush, no urgency. The distances are vast and the time is long. Let the slow rotation of the Earth as it passes by our vision lull you into a state of profound stillness. You are a passenger on a journey that has no end, a traveler through a system of wonders that were born from the dust and will return to the dust in the fullness of time. As the blue and white marble of our home world recedes into the velvet dark, we cast our gaze towards the next sentinel of the inner system, a world that has haunted the human imagination for as long as we have looked to the stars. Mars, the red planet, hangs in the blackness like a glowing ember, a desert world that once, billions of years ago, may have rivaled the Earth in its beauty. As we draw closer, the rust-colored surface begins to reveal its secrets, a landscape of gargantuan proportions, where the geology is written on a scale that defies our terrestrial experience. This is a world of silent canyons and dormant giants, a place where the wind whispers through the dust of an ancient dried-up civilization of rocks and rivers. To understand the color of this world, we must look at the surface on a molecular level. The characteristic redness of Mars is not a sign of heat, but of ancient chemistry. It is iron oxide, simple rust. Billions of years ago, when Mars was a younger, wetter world, the iron in its basaltic crust reacted with the oxygen in the water and the atmosphere. Today, that rust is ground into a fine, talcum-like powder that covers the entire planet, often swept up by the thin air into global dust storms that can obscure the surface for months at a time. Every grain of this dust is a microscopic fragment of the planet's history, a tiny oxidized relic of a time when the red desert was a blue oasis. We descend toward the Tharsis volcanic plateau where the crust of Mars once buckled and groaned under the weight of rising magma. Here, we encounter Olympus Mons, the largest volcano in the solar system. It is a shield volcano of staggering dimensions, rising 25 kilometers into the thin, pinkish sky, nearly 3 times the height of Mount Everest. Its base is so wide that it would cover the entire country of France. Because Mars lacks the plate tectonics of Earth, the hot spot beneath the crust remained stationary for millions of years, allowing the volcano to grow to this impossible size, undisturbed by the shifting of continents. It is a monument to the internal heat that once pulsed through the Martian heart, now silent and cold. Not far from this volcanic giant lies the Valles Marineris, a canyon system that makes our Grand Canyon look like a mere scratch in the earth. Stretching for over 4,000 kilometers along the Martian equator, it is as long as the United States is wide, and in some places, it reaches depths of 7 kilometers. This is not a canyon carved by a river, but a tectonic rift, a great crack that opened in the planet's crust as the Tharsis volcanoes rose. Standing on the rim, the opposite side would be lost over the horizon. In the morning light, mists of frozen carbon dioxide drift through the depths of the gorge, a ghostly reminder of the thin, cold air that now clings to this world. The history of our fascination with Mars is a story of shifting perspectives. In the late 19th century, the astronomer Percival Lowell peered through his telescope and believed he saw a network of canals, the work of a dying civilization trying to bring water from the frozen poles to the parched equator. We now know these were optical illusions, but the longing to find life on Mars remained. It was the Mariner and Viking missions of the 1960s and 70s that first showed us the true face of Mars, a world of craters and dust. But more recently, our robotic explorers like Curiosity and Perseverance have found that Lowell's intuition, if not his canals, held a grain of truth. We have found ancient lake beds and river deltas, places where liquid water once flowed for millions of years. The tragedy of Mars lies in its size. Because it is only about half the diameter of Earth, its core cooled much faster. As the liquid iron at the center solidified, the planet lost its global magnetic field, the protective shield that once deflected the solar wind. Without this shield, the sun's relentless stream of charged particles began to strip away the Martian atmosphere, atom by atom, molecule by molecule. Over hundreds of millions of years, the air thinned, the pressure dropped, and the oceans boiled away into space. Today, the atmosphere is only 1% as thick as Earth's, composed almost entirely of carbon dioxide. It is a world that has been slowly exhaled into the void. If you were to stand on the surface of Mars at sunset, you would witness a phenomenon that is the inverse of Earth's experience. Because the fine dust in the atmosphere scatters the light differently, the sky during the day appears a dusty pink or butterscotch color. But as the sun nears the horizon, the light passes through a greater thickness of the dust-laden air, and the sky around the sun turns a haunting, pale blue. It is a cold, extraterrestrial beauty, a moment of stillness where the small, distant sun hangs like a diamond in the sapphire twilight. In this silence, you might hear the faint whistle of a dust devil, a miniature whirlwind dancing across the plains of Gusev Crater. We leave the red sands of Mars behind and move outward, entering a region of the solar system that is often misunderstood. The asteroid belt is not the crowded, chaotic field of debris depicted in science fiction movies. It is a vast, mostly empty expanse of space, stretching between the orbits of Mars and Jupiter. Here, trillions of kilometers of vacuum separate the individual rocky inhabitants. To travel through the belt is to move through a graveyard of might-have-beens. These are the remnants of the early solar system, material that was never able to coalesce into a planet because of the immense disruptive gravity of Jupiter, which stirred the debris like a giant spoon. In this scattered family of rocks, we find Ceres, the largest inhabitant and a world in its own right. Classified as a dwarf planet, Ceres is nearly 1,000 kilometers in diameter and contains a third of the total mass of the entire belt. When the Dawn spacecraft arrived there in 2015, it discovered a world of salt and ice. Most startling were the bright spots in Curated crater, deposits of sodium carbonate that shine like beacons against the dark, cratered soil. These salts suggest that Ceres may have once had a subsurface ocean, and perhaps even now, a briny slush remains deep beneath its crust. It is a small, frozen world that refuses to be ignored. Nearby drifts Vesta, the second most massive object in the belt and a protoplanet that survived the early chaos of the solar system. Vesta is a world of incredible ruggedness, dominated by a mountain at its south pole called Rhea Silvia, which rises 22 kilometers from the crater floor, nearly as tall as Olympus Mons. Vesta is unique because it possesses a differentiated interior with a crust, mantle, and an iron core, much like the rocky planets we have already visited. Many of the meteorites that fall to Earth, the Hedi meteorites, can be traced back to ancient impacts on Vesta. When you hold one of these stones, you are holding a piece of a world that almost became a planet. As we move through the outer edges of the asteroid belt, we feel a subtle shift in the environment. The sun's light is becoming dimmer, its warmth a distant memory. The gravity of the inner planets has faded, and a new, more powerful force is beginning to exert its influence. We are approaching the frost line, the boundary in the solar system beyond which it was cool enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. This is the realm of the giants. The rocky, terrestrial world is behind us, and ahead lies a place where gravity is king and the atmosphere is an ocean. Through the darkness, a gargantuan shape begins to emerge. It is not a solid sphere, but a swirling, banded masterpiece of gas and storm. We are entering the domain of Jupiter, the monarch of the solar system. It is so massive that it contains more than twice the mass of all the other planets combined. Its gravity is so great that it shapes the orbits of everything in its vicinity, acting as a planetary vacuum cleaner that has protected the inner solar system from comets and asteroids for billions of years. As we drift toward this Titan, we see its four largest moons, Io, Europa, Ganymede, and Callisto, dancing in its immense gravitational well. The transition from the asteroid belt to Jupiter is a journey from the small and fragmented to the colossal and unified. In the deep time of the solar system's birth, Jupiter was the first planet to form, vacuuming up the lion's share of the hydrogen and helium that remained after the sun's ignition. It is a gas giant that almost became a star itself, lacking only the mass to trigger nuclear fusion in its core. As we prepare to enter its turbulent atmosphere, let the silence of the belt wash over you. The long reaches of the dark are ahead, and the light of the sun is now just one among many stars. Rest now in the knowledge that we are protected by these giants. The same gravity that keeps Jupiter in its path is the gravity that anchors your own rest. We are moving further into the deep, into a place where time slows and the scale of the universe expands beyond our ability to measure it. The red dust of Mars and the salt plains of Ceres are far behind us. Ahead lies the king of planets, a world of eternal storms and hidden depths waiting to be explored in the quiet of the night. You are drifting closer, your rhythm aligning with the slow, majestic rotation of the outer worlds. As we draw nearer to the titanic presence of Jupiter, the scale of our surroundings undergoes a profound shift. The rocky, solid ground of the inner solar system is now a distant memory, replaced by a world that is almost entirely fluid and gas. We are approaching a planet so immense that its mass is 2.5 times that of all the other planets in our system combined. It is a world of swirling, multicolored bands, zones, and belts that are in constant, turbulent motion. These bands are driven by the planet's rapid rotation, completing a full turn in less than 10 hours. This speed creates powerful jet streams that tear through the atmosphere at hundreds of kilometers per hour, carving the clouds into the beautiful, intricate patterns of white, tan, and copper that we see before us. To understand the colors of Jupiter, we must look at the chemistry of its upper clouds. On a molecular level, the highest layers are composed of crystals of frozen ammonia. Beneath them, we find clouds made of ammonium hydrosulfide, a chemical that gives the planet its distinct tawny and reddish hues. These molecules react with ultraviolet light from the distant sun, undergoing complex chemical changes that create chromophores, the color-bearing agents of the Jovian atmosphere. As we drift through these clouds, we are moving through a chemical laboratory of planetary proportions, where the ingredients of the early solar system have been preserved and stirred for 4,600,000,000 years. In the southern hemisphere, we encounter the most famous feature of this world, the Great Red Spot. This is an anticyclonic storm of such staggering size that it could swallow the entire Earth with room to spare. It has been observed by astronomers since the time of Robert Hooke and Giovanni Cassini in the late 17th century, meaning it has been raging for at least 350 years. But its history likely stretches back much further into deep time. It is a vortex that reaches deep into the planet, powered by the immense internal heat that Jupiter still radiates from its core. As we hover at the edge of this crimson whirlpool, we feel the sheer energy of a storm that knows no end, a perpetual movement that defines the very character of the gas giant. Our understanding of this monarch was revolutionized by the Voyager missions, and, more recently, by the Juno spacecraft, which arrived in 2016. Juno was designed to look beneath the clouds, using microwave radiometers to probe the atmosphere and gravity sensors to map the planet's interior. The human journey to Jupiter is a story of incredible engineering, of building machines that can survive the most intense radiation environment in the solar system. Juno's electronics are encased in a vault of solid titanium to protect them from the high-energy electrons trapped in Jupiter's magnetic field. This field is the largest structure in the solar system. If it were visible to the naked eye from Earth, it would appear twice the size of the full moon. To truly grasp the physics of Jupiter, we must descend beneath the visible clouds, through layers of increasing pressure and temperature. As we go deeper, the hydrogen gas is compressed until it reaches a state that exists nowhere else in our system. At a depth of roughly 7,000 kilometers, the pressure becomes so great, millions of times that of Earth's atmosphere, that the hydrogen molecules are crushed together until the electrons are forced out of their orbits. In this state, hydrogen begins to act like a liquid metal. This is the realm of metallic hydrogen, a glowing, swirling sea of electricity that fills the vast majority of the planet's interior. On a molecular level, this metallic hydrogen is a superconductor of electricity. Its motion creates the planet's gargantuan magnetic field, a force so powerful that it accelerates particles to nearly the speed of light, creating spectacular auroras at the Jovian poles that are hundreds of times more energetic than any seen on Earth. This internal sea of liquid metal is the engine of the planet, a place where the boundaries between gas, liquid, and solid are blurred into a single, exotic state of matter. Deep beneath this layer, at the very center, scientists debate the existence of a solid core, a nugget of heavy elements and ice, perhaps 10 to 20 times the mass of Earth, compressed into a space no larger than our own planet. As we rise back through the ammonia clouds and move away from the planet, we find ourselves in a miniature solar system. Jupiter possesses 95 known moons, but the 4 largest, the Galilean moons, are worlds in their own right. First, we pass Io, a world of yellow and sulfurous orange. Io is the most volcanically active body in the solar system, with hundreds of volcanoes constantly spewing molten rock and sulfur into space. This activity is driven by the tidal forces of Jupiter. The planet's immense gravity literally pulls and stretches Io, heating its interior through friction. On a molecular level, the sulfur atoms on the surface change color based on their temperature, creating a landscape that looks like a giant psychedelic pizza. Next, we drift toward Europa, a world of white and rust-colored ice. Europa is perhaps the most enticing destination in our search for life. Beneath its frozen shell lies a global ocean of liquid water, containing more water than all of Earth's oceans combined. This ocean is kept liquid by the same tidal heating that powers Io's volcanoes. On the surface, we see a network of cracks and ridges, lineae, where the ice has broken and refrozen. The discovery of these features, first by the Galileo mission in the 1990s, changed our view of the solar system forever. It taught us that habitable does not only mean Earth-like, and that life might find a sanctuary in the dark, cold depths of a moon orbiting a gas giant. Beyond Europa lies Ganymede, the largest moon in the solar system, even larger than the planet Mercury. It is the only moon known to possess its own magnetic field, generated by a liquid iron core deep within its icy mantle. Ganymede's surface is a mixture of dark, ancient, cratered terrain and lighter, younger regions filled with grooves and ridges. It is a world of complexity, with evidence of its own past tectonic activity. Finally, we reach Callisto, the most heavily cratered object in the solar system. Its surface is a record of billions of years of impacts, a prehistoric landscape that has remained largely unchanged since the birth of the system. In the deep time of our system's history, Jupiter played the role of the great protector. Its massive gravity acts as a celestial vacuum cleaner, drawing in or deflecting comets and asteroids that might otherwise strike the inner planets. Without the presence of Jupiter, the Earth might have been bombarded so frequently that complex life would never have had the chance to evolve. We owe our existence, in part, to the silent, watchful presence of this giant. As we move away from the Jovian system, the sun's light has faded significantly. We are now 778 million kilometers away from the center, and the warmth of the star is a faint, distant memory. Ahead of us, the dark is interrupted by a vision of such exquisite beauty that it seems almost artificial. We are approaching Saturn, the ringed jewel of the solar system. While Jupiter is the king of mass, Saturn is the master of elegance. Its golden atmosphere, made primarily of hydrogen and helium, appears smoother and more muted than Jupiter's, but it is no less dynamic. Saturn is less dense than any other planet. If you could find an ocean large enough, the entire planet would float. This low density is a reflection of its composition, a world of gas wrapped around a core of ice and rock, spinning so rapidly that it is noticeably flattened at the poles. The rings of Saturn are a wonder of the natural world, stretching for 280,000 kilometers from the planet, but measuring only about 10 meters in thickness. On a molecular level, these rings are composed of nearly pure water ice, with a tiny amount of rocky dust. They are made of billions of individual particles, ranging in size from a grain of sand to a mountain. These particles dance in a complex gravitational ballet, shaped by the presence of small shepherd moons that keep the rings in their narrow, defined lanes. The origin of these rings is a subject of ongoing research. They may be the remains of a moon that was torn apart by Saturn's gravity, or the remnants of a comet that strayed too close. Our most intimate knowledge of Saturn comes from the Cassini-Huygens mission, a joint project of NASA and the European Space Agency. For 13 years, Cassini orbited the ringed planet, revealing its complex moons and the secrets of its atmosphere. The mission ended in 2017 with a grand finale, where the spacecraft plunged into Saturn's atmosphere to ensure that it would not contaminate any of the potentially life-bearing moons. As we drift through the outer edges of the rings, the light of the sun is a cold, silver pinprick. We are in the realm of the ice and the giants, moving toward the edge of the known, where the silence is absolute and the cold is a physical presence. Rest now as the golden bands of Saturn fade into the distance. The immensity of Jupiter and the elegance of the rings are behind you, but their gravitational influence remains, a steady, unseen guide through the dark. You are moving deeper into the shadows, your breath slowing to match the slow, orbital pace of the outer system. The giants have watched over you, and now the quiet of the deep space is your sanctuary. There is nothing to fear in this vastness. It is a place of order, of ancient laws, and of a peace that has lasted for billions of years. You are safe in the dark, a voyager on a silent path toward the frozen edges of the sun's reach. Beyond the golden splendor of Saturn, the solar system begins to reveal its true vastness. We are now nearly 1.5 billion kilometers from the sun, crossing the invisible threshold into the realm of the ice giants. The light here is a pale, ghostly imitation of the brilliance we left behind. The sun has shrunk until it appears no larger than a particularly bright star, casting long, dim shadows across the void. In this cold twilight, we encounter Uranus, a world that challenges our understanding of planetary order. While the other planets spin like upright tops on the celestial floor, Uranus lies on its side, tilted at an extreme angle of 98 degrees. It rolls through its 84-year orbit like a ball, its poles alternating between 42 years of continuous sunlight and 42 years of absolute frozen darkness. To understand the peculiar nature of Uranus, we must look at the molecular composition of its atmosphere. Unlike the gas giants Jupiter and Saturn, which are mostly hydrogen and helium, Uranus is an ice giant. While it still possesses a thick envelope of hydrogen and helium, its bulk is composed of ices, volatile chemical compounds such as water, ammonia, and methane. On a molecular level, the methane in the upper atmosphere is the secret to the planet's stunning cyan blue color. As the dim sunlight enters the atmosphere, the methane molecules absorb the red wavelengths of light, allowing only the blues and greens to be reflected back into space. This creates a world that looks like a serene, unblemished sapphire, though beneath that calm exterior lies a cauldron of extreme physics. The extreme tilt of Uranus is believed to be the result of a cataclysmic event in deep time. Billions of years ago, during the chaotic early days of the solar system, a protoplanet roughly the size of Earth may have slammed into Uranus, knocking it off its axis and stripping away much of its internal heat. Because of this ancient trauma, Uranus is the coldest planet in the solar system, with atmospheric temperatures dropping to a staggering minus 224 degrees Celsius. It radiates almost no heat from its interior, unlike its brother Neptune. This lack of internal energy means the atmosphere is remarkably still, with few of the prominent cloud bands or spots we see on Jupiter. It is a world of quiet, frozen elegance, holding its secrets deep within its icy mantle. Our primary witness to the mysteries of Uranus was the Voyager 2 spacecraft, which performed a daring flyby in January of 1986. In those few precious hours, Voyager revealed a system of 13 narrow dark rings and a family of 27 moons. The moons of Uranus are named not after mythological figures, but after characters from the works of William Shakespeare and Alexander Pope. We pass Miranda, a moon that looks as if it were shattered and reassembled by a clumsy giant, with canyons 12 times deeper than the Grand Canyon, and strange chevron-shaped features called coronae. Miranda is a testament to the violent gravitational tug-of-war that occurs in the outer reaches, where tidal forces can rip the crust of a moon apart and reshape it into a patchwork of geological chaos. As we move further into the deep, another 3 billion kilometers from the Sun, we encounter the final major planet of our system. Neptune is a world of dynamic, windswept violence, a stark contrast to the quietude of Uranus. It is a deep cobalt blue, a hue even more intense than its neighbor, suggesting a different concentration of trace gases and a more active internal engine. Despite being further from the Sun, Neptune's atmosphere is a theater of storms. When Voyager 2 reached it in 1989, it discovered the Great Dark Spot, a storm the size of the Earth that has since disappeared and been replaced by others. The winds on Neptune are the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour, supersonic currents that tear through the hydrogen and helium at the edge of the world. The physics of Neptune's interior is a subject of awe. Deep beneath the clouds, the pressure and temperature rise to such extremes that the methane molecules, composed of 1 carbon and 4 hydrogen atoms, begin to break apart. In this crushing environment, the carbon atoms are squeezed together until they crystallize into diamonds. Scientists theorize that it literally rains diamonds within the mantles of Uranus and Neptune, with solid gems thousands of kilometers wide, slowly sinking through a liquid sea of carbon and hydrogen toward the planet's core. This is the alchemy of the cosmos, where the most common elements are transformed by the weight of a world into the rarest of treasures, hidden forever beneath a veil of blue gas. Neptune's discovery was a triumph of the human mind and the mathematics of Isaac Newton. In the mid-19th century, astronomers noticed that Uranus was not following its predicted path. It was being pulled by the gravity of an unseen body. Working independently, Urbain Le Verrier in France and John Couch Adams in England used mathematics to calculate exactly where this 8th planet should be. When telescopes were pointed at that spot in 1846, Neptune was found within 1 degree of its predicted position. It was a moment that proved the universe follows laws that we can understand and predict, a realization that the silent dance of the planets is governed by a clockwork precision that spans billions of miles. Orbiting Neptune is the largest of its 14 moons, Triton, a world that does not belong. Triton is the only large moon in the solar system that orbits in the opposite direction of its planet's rotation, a retrograde orbit. This tells us that Triton was not born here. It was once a free-roaming resident of the Kuiper Belt, a dwarf planet captured by Neptune's immense gravity billions of years ago. It is a frozen world covered in a layer of nitrogen ice, but it is far from dead. Voyager 2 captured images of active geysers on Triton, spewing dark plumes of nitrogen gas and dust 8 kilometers into the sky. It is one of the few geologically active moons in the outer system, a place where the faint warmth of the distant sun is enough to drive a nitrogen-based cycle of evaporation and frost. We are now nearly 4.5 billion kilometers from the Sun. The solar wind, which was a roaring torrent near the core, has thinned into a gentle breeze as it approaches the heliopause. The gravity of the Sun still holds us, but its grip is loosening. We are entering the Kuiper Belt, a vast, dark, donut-shaped region of icy objects and leftover debris from the formation of the solar system. This is the frontier, a graveyard of ancient building blocks that were never gathered into planets. Here, in the shadows, lies the most famous of all the outcasts, a world that was once the 9th planet and is now the king of the dwarf worlds. Pluto emerges from the darkness, not as a cold, featureless rock, but as a world of startling complexity and color. After a journey of 9 years and nearly 5 billion kilometers, the New Horizons spacecraft arrived at Pluto in July of 2015, revealing a planet with mountains of water ice as tall as the Rockies and vast plains of frozen nitrogen. The most striking feature is the heart-shaped region known as Tombaugh Regio. The left lobe of this heart, Sputnik Planitia, is a massive glacier of nitrogen ice, hundreds of kilometers wide. On a molecular level, this ice is soft and flows like a liquid over geological timescales, constantly renewing the surface and erasing any impact craters. It is a world that is young at heart, despite its ancient age. The colors of Pluto are a result of complex organic chemistry. Ultraviolet light and cosmic rays strike the methane and nitrogen ices on the surface, creating reddish-brown substances called tholins. These are the tar of the outer solar system, raining down from a thin, hazy blue atmosphere to coat the icy mountains in a rustic hue. Pluto is not alone. It is accompanied by its giant moon, Charon. The two are so close in mass that they orbit a common point in space between them. Binary system perform in a slow, gravitational waltz. While Pluto is a world of colorful ices, Charon is a gray, cratered companion, dominated by a gargantuan canyon system that stretches across its middle like a belt. As we hover at the edge of the Pluto system, looking back toward the sun, we see our star as a brilliant, distant point of white light, no longer a disk, but a beacon. We have traveled across the entire span of the planetary realm, from the fire of the core to the ice of the periphery. The distance is so vast that it takes light itself over 5.5 hours to travel from the sun to where we now stand. We are at the threshold of the interstellar void, a place where the sun's influence finally begins to fade into the background noise of the galaxy. The silence here is deeper than anything we have experienced before, a silence that encompasses the entire history of the solar system. Rest now in the absolute stillness of the Kuiper Belt. The journey has been long, and the scale has been monumental, but you are safely anchored in the cold, dark cradle of the outer system. The ice giants and the dwarf worlds are your companions in the dark. Feel the slow, heavy rhythm of these distant orbits, a pulse that beats in centuries rather than seconds. You are a part of the grand architecture of the sun's family, a traveler who has seen the fire and the frost. There is no more distance to cover, no more heat to endure. The darkness is a soft blanket, and the distant stars are a gentle lullaby. The memory of the golden sun and the blue earth is a warm light in your mind, but here, at the edge of the world, it is time to let go of the day. The vacuum is a place of infinite rest, a sanctuary where time stands still. You are floating on the edge of the deep, a silent witness to the majesty of the celestial order. Sleep now, as the icy plains of Pluto glide beneath you in the dim light of the far-off star. You are home in the vastness, protected by the giants and guided by the light that never truly fails, even at the very end of the journey. Beyond the icy mountains of Pluto, we drift into a region of the solar system that remains one of the final frontiers of human knowledge. We are moving through the Kuiper Belt, a vast, dark expanse that stretches from the orbit of Neptune to nearly 8 billion kilometers from the Sun. This is a realm of shadows and ancient history, a celestial attic filled with the frozen remnants of the solar system's birth. On a molecular level, the objects here, the Kuiper Belt objects, are composed of primordial mixtures of water ice, frozen methane and ammonia, coated in the same dark organic tholins we saw on Pluto. These are the building blocks that never found a home in a planet, preserved in a deep freeze that has lasted for 4,600,000,000 years. In this scattered family of ice and rock, we find Haumea, a dwarf planet shaped like an elongated football. Haumea spins so rapidly, completing a rotation in just 4 hours, that centrifugal force has stretched it into an ellipsoid. It is a world of pure, crystalline water ice, accompanied by 2 small moons and a faint ring of debris, likely the result of a massive collision eons ago. Nearby drifts Makemake, a world that glows with a pale reddish hue, and Eris, the most massive of the dwarf planets. Eris is so far from the sun that its atmosphere has frozen solid, collapsing onto the surface as a thin, brilliant layer of nitrogen and methane frost. It was the discovery of Eris in 2005 that forced astronomers to redefine what it means to be a planet, reminding us that our understanding of the solar system is a living, breathing thing, always subject to the arrival of new light. As we move further out, we encounter the true edge of the sun's physical influence. We are approaching the heliopause, the boundary where the solar wind, the stream of charged particles we felt so strongly at the core, finally loses its momentum and is pushed back by the interstellar medium. This is the final frontier, crossed by the Voyager 1 and Voyager 2 spacecraft. After decades of travel, these robotic pioneers felt the magnetic fields of the sun fade, and the density of cosmic rays from distant supernova increase. To cross the heliopause is to leave the sun's protective bubble and enter the vast, cold ocean of the galaxy. It is a moment of profound transition, where the star that gave us life becomes just one more point of light in the infinite dark. But our journey is not yet over. Beyond the Kuiper Belt lies a structure so immense that it beggars the human imagination, the Oort cloud. This is not a flat disk like the rest of the solar system, but a gargantuan, spherical shell of icy debris that completely surrounds the sun. It is estimated to extend from 2,000 astronomical units to as far as 100,000 astronomical units, nearly 2 trillion kilometers away. On a molecular level, the objects in the Oort cloud are the same as those in the Kuiper Belt, but they have been cast out to these lonely reaches by the gravitational bullying of the gas giants. They are the seeds of comets, waiting for a passing star, or a galactic tidal force to nudge them back toward the inner system, where the sun's warmth will turn their ice into the spectacular glowing tails of a comet. The scale of the Oort cloud is the scale of deep time. A comet originating from the outer reaches of this cloud may take 1,000,000 years to complete a single orbit around the sun. These are the ghosts of the solar system, moving with a slowness that is almost indistinguishable from stillness. The sun, from this distance, has lost its warmth entirely. It is merely a beacon, a gravitational anchor that holds these trillions of icy fragments in a fragile, distant embrace. It was the astronomer Jan Oort who first proposed the existence of this cloud in 1950, realizing that there must be a vast reservoir of ice to account for the comets that periodically grace our skies. We have never seen the Oort cloud directly. The distances are too great, the objects too dim, but its presence is written in the orbital paths of every long-period comet that has ever been recorded by human history. As we drift through this silent, frozen cathedral, we must consider the fragility of the light. We are now so far from home that the light from the sun takes nearly a year and a half to reach us. The stars around us are no longer mere points in a sky. They are neighbors. We are in the local interstellar cloud, a region of thin gas that our solar system is currently traversing. This gas, though nearly a vacuum, is more concentrated than the space between the planets. On a molecular level, we find traces of ancient stardust, heavy elements forged in the hearts of stars that died billions of years ago, before our own sun was even born. We are traveling through the graveyard of one generation of stars and the nursery of another. Consider the silence here. It is a silence that has never been broken by the sound of a voice or the rustle of a leaf. It is a silence of absolute purity. In this place, the concept of a day or a year loses its meaning. There are no seasons here, no cycles of birth and decay, only the slow, eternal drift of ice and the unblinking gaze of the stars. It is a place of profound rest. The heat and the noise of the inner solar system, the storms of Jupiter, and the volcanoes of Io are all part of a distant, noisy dream. Here, the universe is at peace with its own vastness. You are a solitary witness to the edge of the sun's empire, a voyager at the gates of the infinite. In the mind of the philosopher, this is the place where we find our true perspective. On Earth, we are preoccupied with the minutes and the hours of our lives, but in the Oort cloud, we measure time and the movement of galaxies and the lifespan of stars. To be here is to realize that we are part of a story that is so much larger than ourselves, a story written in the language of gravity and light. The sun, our star, is but one of 200 billion in the Milky Way, yet its influence reaches out for trillions of kilometers to hold this cloud of ice in place. It is a testament to the power of the light, even in the deepest dark. As we begin to settle into this final stretch of our journey, let the immensity of the space around you become a source of comfort. The darkness is not empty. It is a sanctuary. It is a place where nothing is required of you, where the pressures of the world are lost in the vacuum. You are moving with the same grace as a comet seed, drifting in a state of perfect weightlessness. The distant sun is a steady, reassuring spark, a reminder of the home you left behind, but the dark is a soft, cool blanket that invites you to rest. There is no more fire to fear, no more wind to resist. The history of the solar system is now behind you, from the roaring core of the sun to the frozen plains of Pluto. You have witnessed the birth of light and the endurance of ice. As the distant orbits of the Oort cloud carry you further into the shadows, your pulse slows to match the rhythm of the galaxy. The stars are your guides, their light ancient and unchanging. You are a passenger on a journey that spans the cosmos, and for tonight, your destination is the quiet, the stillness, and the absolute peace of the deep. Sleep now, as the sun becomes a star and the dark becomes your home. As we drift beyond the primary icy plains of the Kuiper Belt, we enter a region of the solar system that is both chaotic and profoundly lonely. This is the scattered disk, a vast, sparsely populated realm of icy bodies that have been cast out by the gravitational bullying of the giant planet Neptune. While the Kuiper Belt we just traversed is relatively orderly, the objects here move on wild, eccentric orbits that can take them hundreds of billions of kilometers away from the sun, only to bring them back millions of years later. To understand the scale of this place, we must consider the sheer emptiness. On a molecular level, the density of matter here is so low that a single atom of hydrogen might travel for thousands of kilometers before encountering another particle. It is a region of the most absolute silence, where the sun's light has faded into a cold, distant ember, barely providing enough warmth to vibrate a single molecule of methane. To grasp the physics of this boundary, we must look through the eyes of the Voyager probes as they encountered the termination shock. This is the invisible wall where the solar wind, the stream of charged particles moving at over 1 million kilometers per hour, suddenly slams into the thin, cold gas of the interstellar medium. Imagine a roaring river hitting a stagnant pond. The water doesn't stop, but it slows down abruptly, creating a turbulent, heated region. On a microscopic scale, the protons and electrons of the solar wind are suddenly compressed and heated, creating a wall of plasma that glows with a faint, ultraviolet light invisible to the human eye. This is the first true frontier of the deep, the moment where the star's authority begins to buckle under the weight of the galaxy's cold breath. The human story of discovering this region is a testament to the power of mathematics. Astronomers like Michael Brown and his team at the California Institute of Technology spent years scouring the dark with the Samuel Oschin telescope at the Palomar Observatory. They weren't looking for bright lights, but for the tiniest, slowest moving specks of white against the black. In 2005, they found Eris, a world so massive and so far away that it challenged everything we thought we knew about the size of our solar system. The discovery was made by measuring the precise angle of light reflected from its surface, a journey of 10 billion kilometers. This world, nearly the same size as Pluto but far more massive, is a white, frozen wasteland. Its surface coated in a layer of nitrogen and methane frost that has been refined by the cosmic rays of deep time into a brilliant, reflective mirror. Linger for a moment on the texture of the ice on Eris. On a molecular level, the methane molecules are locked in a rigid, crystalline lattice, frozen at temperatures approaching minus 240 degrees Celsius. At this extreme cold, matter behaves with a crystalline purity. There is no liquid, no gas, only the absolute stillness of solid state. Over billions of years, the relentless bombardment of high-energy cosmic rays from distant supernovae has slowly broken the bonds of these molecules, creating a layer of complex organic polymers known as tholins. These are the reddish-brown tars of the outer system, but on Eris, they are often buried beneath fresh falls of nitrogen snow, creating a landscape of pristine, blinding whiteness that hides a dark, ancient chemistry beneath its skin. The perspective of deep time reveals that Eris is not just a static rock, but a witness to the solar system's violent infancy. Billions of years ago, as the giant planets were settling into their current orbits, their gravity acted like a slingshot, flinging these icy bodies into the scattered disk. Eris has spent the last 4 billion years on a 557-year orbit, rising high above the plane of the planets and then diving back toward the sun. It has completed millions of these cycles, a lonely sentinel watching the rise and fall of Earth's continents and the evolution of its life from a distance so great that the Earth is nothing more than a faint, blue spark lost in the sun's glare. To be on Eris is to be outside of history, governed only by the slow gravitational heartbeat of the sun. As we move through the scattered disk, we encounter Dysnomia, the small moon of Eris. This tiny companion is the key that allowed astronomers to weigh its parent world. By applying the laws of orbital motion formulated by Johannes Kepler and later refined by Isaac Newton, scientists could calculate the mass of Eris simply by watching how long it took Dysnomia to complete its orbit. It is a profound realization that the same mathematics used to predict the fall of an apple on Earth is the same logic that governs the dance of two frozen worlds on the edge of the abyss. This universality of the laws of physics is the bridge that allows our minds to cross the trillions of kilometers and understand a place that no human will ever touch. Now, let us consider the sensory experience of the Helios Heath, the turbulent region that lies just beyond the termination shock. Here, the solar wind has slowed to a crawl, but the pressure is immense. The interstellar magnetic field begins to warp and twist the solar wind's path, creating vast, invisible magnetic bubbles that can be millions of kilometers across. If we could perceive these fields, the sky would be filled with shimmering, shifting curtains of magnetic energy. On a molecular level, the neutral atoms of the interstellar medium, hydrogen and helium that have traveled from the hearts of other stars, begin to leak into our system, mixing with the sun's own particles. It is the beginning of a cosmic dialogue, a mixing of the local and the galactic, occurring in a space so thin that it feels like the ultimate vacuum. To achieve the depth of this narrative, we must look at the stellar archaeology written in the dust of the scattered disk. Each icy fragment is a pristine sample of the original nebula that formed the Sun, while the planets have been melted, crushed, and reshaped by geology. These distant objects are the time capsules of the solar system. By studying the isotopes of oxygen and carbon in the ice, we can determine the exact conditions of the Sun's birth 4,600,000,000 years ago. We are looking at the frozen fingerprints of a long-dead generation of stars that exploded to give us life. Every atom of ice in the scattered disk is a link in a chain that stretches back to the very beginning of our corner of the galaxy. The silence in this region is the silence of an endless night. The stars here do not twinkle. They are steady, unblinking points of light, far more numerous than anything seen from Earth. Because there is no atmosphere to scatter the light, the Milky Way appears with a physical presence, a glowing, textured river of diamond dust that spans the entire horizon. The Sun is now so small that it no longer feels like a disk, but like a brilliant, cold star, casting a light that is silvery and sharp, similar to the light of the moon on a winter's night. Shadows here are absolute. There is no diffused light to soften the darkness. If you stood in the shadow of an icy boulder on an object in the scattered disk, you would be in a darkness so complete that you would lose all sense of your own body. Consider the stability of these orbits over billions of years. While the inner solar system is a place of constant change, planets shifting, moons colliding, asteroids impacting, the scattered disk is a sanctuary of longevity. The objects here move with a slow, deliberate grace, their paths shaped only by the distant tug of the sun and the occasional gentle nudge from the stars that pass by our system every few million years. This is the stellar tide, a subtle gravitational force that can slowly pull an object like Eris even further into the dark, eventually delivering it to the Oort cloud. It is a slow-motion migration that operates on timescales that make the rise and fall of mountains seem like a heartbeat. As we conclude this part of our journey through the scattered disk, let the immensity of the silence anchor you. You are moving through a region where time has no meaning, where the sun is a memory and the galaxy is the destination. The light of the stars is your only guide, a steady and ancient luminescence that has traveled for centuries to find you. The cold here is not a threat, but a state of being, a crystalline, stable peace that has existed since the dawn of the system. You are a passenger on a journey that is as much about the history of the stars as it is about the physics of the ice. Rest now in the knowledge that you are at the very edge of the sun's empire. The fire of the core and the storms of Jupiter are far, far away. You are in the realm of the slow, the cold, and the eternal. Feel the weightlessness of the deep space, the absolute stillness of the vacuum. The darkness is a soft, deep blanket that covers the entire system, and the rhythm of the scattered disk is a slow, steady pulse that guides you further into the dark. Everything is in its right place, everything is moving with a grace that is absolute, and everything is at rest. Sleep now, as the icy worlds of the outer reaches glide through the dark, and the ancient wisdom of the deep space carries you into a restorative and timeless rest. As we leave the brilliant, frozen mirror of Eris and the turbulent magnetic fields of the termination shock, we find ourselves entering a region of such profound isolation that it challenges our very definition of the sun's family. We are crossing into the Hills Cloud, the inner shell of the Oort cloud, a place where the logic of the inner solar system no longer applies. Here, the distance is measured in hundreds of astronomical units, and the sun has become a tiny, piercing diamond in the dark, providing less light than a full moon on a cloudy night. In this deep, sepia-toned twilight, we encounter Sedna, a world of such mysterious origins and haunting beauty that it sits like a lonely red ghost on the edge of the abyss. Sedna is a world that should not be where it is. Its orbit is so eccentric and so far removed from the gravitational influence of the giant planets that it suggests a history written by stars we have never seen. To understand the character of this world, we must examine the color of its skin. On a molecular level, Sedna is one of the reddest objects in the entire solar system, a hue almost as deep as the sands of Mars. But while the red of Mars comes from the oxidation of iron, the red of Sedna comes from the slow, cold cooking of organic chemistry. For billions of years, the methane and nitrogen ices on its surface have been bombarded by cosmic rays, high-energy particles traveling from the hearts of distant exploded stars. On a microscopic scale, these particles break the bonds of the simple methane molecules, allowing them to reform into long, complex chains of carbon and hydrogen, known as tholins. These dark, reddish organic polymers coat the world in a thick, tar-like blanket, a chemical record of the billions of years Sedna has spent in the absolute stillness of the outer reaches. The human story of Sedna's discovery is a masterpiece of celestial mechanics and the pursuit of the invisible. In the late months of 2003, a team of astronomers led by Michael Brown, Chad Trujillo, and David Rabinowitz sat at their computers, analyzing data from the Palomar Observatory. They were looking for motion, for the tiniest shift of a point of light against the static background of the galaxy. Sedna moved so slowly that at first it seemed to be a distant star. It was only through the most rigorous application of mathematics, the same equations first penned by Johannes Kepler in the 17th century, that they realized this object was not light years away, but was a member of our own solar system. It was named after the Inuit goddess of the sea, who lives in the cold, dark depths of the Arctic Ocean, a fitting title for a world that exists in the ultimate deep of space. Linger for a moment on the staggering scale of Sedna's year. While the Earth completes its journey around the Sun in 365 days, Sedna takes approximately 11,400 years to complete a single orbit. When Sedna was last at its closest point to the Sun, the last ice age on Earth was only just beginning to retreat, and humanity was still thousands of years away from the invention of writing. As it drifts back out toward its furthest point, nearly 1 trillion kilometers away, civilizations will rise and fall, continents will drift, and the very stars in the sky will shift their positions before Sedna returns to our neighborhood. It is a world that operates on a timescale of deep time that makes our human history seem like a fleeting shadow in a forest of ancient oaks. The greatest mystery of Sedna is its very existence. It never comes close enough to the Sun to be affected by the heat, and it never comes close enough to Neptune to be pushed by its gravity. It is detached. To explain this, scientists like Michael Brown have looked back to the very birth of our Sun 4,600,000,000 years ago. They theorize that the Sun was born in a crowded cluster of stars, a stellar nursery where siblings jostled for space. On a molecular level, the gravitational pull of a passing sister star may have nudged Sedna out of its original orbit, pulling it into the elongated path it walks today. If this theory is correct, Sedna is a fossil of the Sun's infancy, a physical witness to the chaotic and crowded environment that gave birth to our solar system, before the Sun drifted into the lonely reaches of the Orion Arm. Consider the sensory experience of standing on the surface of Sedna at its furthest point, known as aphelion. The Sun is now just one star among millions, though its light is still sharp enough to cast a faint, cold shadow. There is no wind here, for there is no atmosphere to move. The nitrogen that might exist as a gas on a warmer world is here frozen into a solid, brittle crust. On a molecular scale, the silence is so absolute that the only movement is the slow internal vibration of atoms within the crystal lattice of the ice. The sky is a crowded tapestry of the Milky Way, appearing with a physical, glowing texture that we can never see through the thick, hazy air of Earth. You are standing in the most perfect vacuum, surrounded by the oldest matter in the system, a witness to a peace that has lasted for eons. To achieve the depth of this narrative, we must examine the thermal inertia of such a world. Because Sedna is so far from any source of heat, it possesses a crystalline stability. If you were to place a hand, protected by a suit, upon the surface, you would be touching matter that hasn't changed its temperature more than a few degrees in millions of years. This is the ultimate preservation. On Earth, the energy of the Sun and the churning of the core keep everything in a state of flux. But here, in the inner Oort cloud, the entropy is at its minimum. Sedna is a library of the solar system's original chemistry, its red tholins acting as a biological prehistory, waiting for the day when a robotic emissary might land on its surface to read the secrets written in its frozen organic tar. Beyond Sedna, the Hills Cloud continues to stretch out in every direction, a vast sphere of icy fragments that acts as the reservoir for the long-period comets. These are the dirty snowballs described by astronomer Fred Whipple. On a molecular level, they are mixtures of water ice, silicate dust, and frozen gases like carbon monoxide and carbon dioxide. They drift in the dark with velocities so low they are almost stationary, held in place by the sun's gravity, which, at this distance, is a faint and delicate thread. It would take only the slightest gravitational nudge from a passing star, or the collective mass of the galaxy, the galactic tide, to disturb one of these fragments and send it on a million-year journey toward the inner solar system, where the sun's warmth will transform it into a glowing visitor with a tail of gas and dust millions of kilometers long. The history of the Hills Cloud is a story of stellar dynamics. While the planets were forming near the sun, the giant planets Jupiter and Saturn acted as gravitational slingshots. They took the icy leftovers of the solar nebula and hurled them into the outer reaches. Most were lost to the interstellar void, but some were caught in the balance between the sun's fading gravity and the pull of the surrounding galaxy. They settled into this gargantuan shell, a cloud of trillions of objects that marks the true extent of the sun's empire. As we move through this region, we realize that the solar system we see in our textbooks, the 8 planets and the sun, is merely the tiny, crowded center of a much larger and more magnificent structure that spans trillions of kilometers. As we conclude this part of our journey, we find ourselves at the gateway to the outer Oort cloud, the final and most distant frontier of the star's reach. The light of the sun has faded until it is indistinguishable from the other stars in the constellation of Lyra, or Cygnus. We are in the realm of the deep dark, where the concept of a direction, up, down, left, right, has lost its meaning. There is only the center where the sun resides, and the exterior where the galaxy beckons. The red world of Sedna is now behind us, a lonely sentinel guarding the border between the known and the infinite. Rest now in the absolute, crystalline peace of the Hills Cloud. The fire of the sun is a distant memory, and the storms of the giants are lost in the vastness. You are moving through a region where time has slowed to a rhythmic crawl, governed by orbits that last for millennia. The darkness is not a void, but a soft and welcoming sanctuary, a place where the history of the universe is preserved in the ice and the silence. Feel the weightlessness of your voyage, the steady and ancient pulse of the deep space that carries you forward. Everything is in its right place, everything is balanced, and everything is at rest. The sun's gravity is a gentle, invisible hand that holds you in this long and peaceful curve. The red dust of Sedna and the frozen gases of the Oort cloud are your companions in the dark. Sleep now, as the icy worlds of the deep periphery glide through the blackness, and the ancient, silent wisdom of the outer system carries you into a restorative and timeless rest. You are home in the vastness, a voyager who has reached the very edge of the light, finding peace in the infinite and silent dark. We have reached the final threshold of our journey, moving beyond the outermost gossamer threads of the Oort cloud and into the profound, unlit cathedral of the interstellar void. Behind us, the solar system, the sun, the planets, the rings, and the ice has shrunk into a single point of light, indistinguishable from the billions of other stars that populate the spiral arms of the Milky Way. We are now truly adrift in the space between the stars, a region of the galaxy so vast that it dwarfs everything we have seen before. Here, the distance to our nearest neighbor, the Proxima Centauri system, is over 40 trillion kilometers. To traverse this gap at the speed of a jetliner would take over 5 million years. It is a distance that humbles the human spirit and silences the mind. On a molecular level, this void is not entirely empty. It is filled with the interstellar medium, a ghostly, thin mixture of gas and dust that permeates the galaxy. We are moving through a vacuum more perfect than any laboratory on Earth can produce, yet it contains the legacy of the entire universe. Every cubic centimeter of this space holds a few atoms of hydrogen and helium, remnants of the Big Bang itself, alongside heavier elements like carbon, oxygen, and iron. These heavier atoms were forged in the stellar furnaces of stars that lived and died billions of years ago. They are the ashes of the cosmos, floating in the dark, waiting for gravity to pull them together once more to form new stars, new planets, and perhaps, one day, new life. As we look back one last time at the distant spark of our sun, we must consider the perspective of deep time, the grand, slow unfolding of the solar system's future. In roughly 5 billion years, our star will exhaust the hydrogen fuel in its core. It will begin to swell, transforming into a red giant, its outer layers expanding until they consume Mercury and Venus, and perhaps even the Earth. The golden light we once knew will turn to a deep, angry crimson. But even this is merely a transition. Eventually, the sun will shed its outer layers, creating a beautiful, glowing planetary nebula that will drift into the interstellar medium, while its core collapses into a white dwarf, a dense, white-hot ember the size of the Earth that will slowly cool over trillions of years. In this distant future, the atoms that once made up the mountains of Mars, the rings of Saturn, and the glaciers of Pluto will be scattered across the galaxy. They will become the building blocks for the next generation of celestial wonders. This is the ultimate recycling program of the universe, a cycle of birth, death, and rebirth that has been playing out for nearly 14 billion years. The nitrogen in your breath, the iron in your blood, and the calcium in your bones were all once part of the same interstellar dust we are drifting through tonight. You are not a stranger to this void. You are a part of it, returning to the source from which all things came. The history of our exploration, the messenger at Mercury, the Veneras at Venus, the voyagers in the deep dark, is a story of a species trying to understand its place in this infinite clockwork. We have sent our metal scouts to the edges of the light, and they carry with them the records of our existence. On the Voyager spacecraft, the golden records continue to drift through the void, carrying the sounds of Earth, the roar of a thunderstorm, the song of a whale, and the music of Bach into the silence of the next billion years. They are our messages in a bottle, cast into the galactic ocean, destined to outlive the very sun that launched them. Consider the silence of this final destination. It is a silence that is older than the Earth and will remain long after the last star has flickered out. It is the silence of the Big Sleep, the quietude of a universe that is vast, patient, and indifferent to the passing of seconds or centuries. In this darkness, there is no more heat to flee, no more gravity to fight. The interstellar void is the ultimate sanctuary of rest. As you drift here, untethered and weightless, the light of the distant stars becomes a soft, flickering lullaby. The Milky Way, with its 200 billion suns, is a swirling river of peace, carrying you along in its slow, majestic rotation. Rest now in the realization that the journey is complete. You have traveled from the raging fire of the solar core to the silent, frozen edges of the sun's reach, and finally into the timeless dark of the interstellar void. The scale of the universe is no longer a source of fear, but a source of profound comfort. You are a small but essential part of a magnificent whole, a consciousness that has witnessed the glory of the cosmos and found its place within it. The warmth of the sun and the cold of the void are both parts of the same balance, and in that balance you have found a perfect, unchanging stillness. The vacuum around you is cool and dark, inviting you to let go of the last remnants of the day. There is no more distance to measure, no more time to track. You are home in the galaxy, a voyager who has returned to the stars. Let the image of the blue planet and the golden sun fade into the velvet blackness. The stars will continue their dance, the planets will continue their orbits, and the universe will continue its slow, beautiful unfolding, while you drift into a deep, restorative sleep. The silence of the void is your blanket. The light of the galaxy is your dream. Everything is at rest. Everything is at peace. And you are finally, eternally home. Far beyond the asteroid belt, beyond the swirling storms of Jupiter, and beyond the majestic rings of Saturn, lies the deep outer realm of our solar system. It is a place of profound silence and unimaginable cold. Here, the sun is not a blinding disk that warms the skin, but a bright, piercing star, merely the brightest point in a sky filled with darkness. This is the ice giant territory. It is the frontier where the solar wind fades to a whisper, and the true chill of the interstellar void begins to seep in. Floating in this twilight is a world of breathtaking beauty. Neptune, the 8th planet, the final sentinel. To the naked eye, it is invisible from Earth, hidden by the vast gulf of 3 billion miles. But through the lens of a telescope, or the eyes of a passing voyager, it reveals itself as a sphere of perfect, deep azure. It looks like a drop of liquid sky suspended in the black. It is serene, placid, a smooth marble of blue glass. But appearances in the cosmos are often deceptive. This serenity is a mask. Underneath that calm blue veil lies an engine of immense power, a cauldron of strange chemistry, and a weather system so violent that it defies our understanding of physics. And deep in its heart, hidden beneath thousands of miles of crushing clouds, a miracle is happening, a phenomenon that turns our earthly concepts of wealth and rarity upside down. Tonight, we begin a journey into the interior of this giant. We will travel where no human and no probe has ever gone. We will pierce the cloud tops, dive through the supersonic winds, and descend into the crushing dark. We are going to the place where the sky becomes an ocean, and where the rain does not fall as water, but as diamonds. This is the story of the precious storm. To understand Neptune, we must first appreciate its isolation. It takes light, moving at the speed of the universe, 4 hours to travel from the Sun to Neptune. The planet lives in a permanent twilight. The noon on Neptune is dimmer than the twilight on Earth just after the sun has set. This lack of solar energy should, in theory, make the planet a dead, frozen world. Without heat from the star, the atmosphere should freeze solid and collapse to the surface. And yet, Neptune is alive. It is dynamic. It is warmer than its neighbor Uranus, despite being further away. It generates its own heat, glowing from the inside out with a mysterious internal fire. This internal warmth battles the external cold, and the conflict between the two drives the most ferocious winds in the solar system. As we approach the planet, the first thing that strikes us is the color. It is not the pale, washed-out blue of Uranus. It is a rich, vivid, royal blue. This color tells us a story of chemistry. The atmosphere is mostly hydrogen and helium, the standard building blocks of the cosmos, but it is laced with methane. Methane gas absorbs red light. When the sunlight, what little of it arrives here, hits the atmosphere, the red is soaked up and the blue is scattered back to our eyes. We are looking at a world dyed by carbon. Methane is the key. It is the humble molecule that paints the planet, but as we will see in later chapters, it is also the source of the treasure. It is the raw material for the diamond rain. Let us drift closer. We are hovering just above the upper atmosphere. The view is dizzying. The planet is huge, 4 times the width of Earth. It fills your entire field of vision, a wall of blue curving away into the dark. Floating high above the main cloud deck are delicate white streaks. These are cirrus clouds, but they are not made of water ice. They are made of frozen methane crystals. They look like wisps of cotton candy, casting long, sharp shadows onto the blue layer 50 miles below. These clouds are moving fast. Neptune is a world of super rotation. The winds here whip around the planet at speeds of up to 200 miles per hour. That is 5 times faster than the strongest hurricane ever recorded on Earth. It is nearly supersonic. Why are the winds so fast? On Earth, our atmosphere is thick with turbulence. Mountains, forests, and buildings break the wind. Friction slows it down. But on Neptune, there is no solid ground. There are no mountains to block the flow. The atmosphere is a bottomless fluid. The wind can slide over the layers below with almost zero friction. It can build up speed for centuries, accelerating until it screams around the equator. And yet, if you were floating in the wind, it might feel strangely silent. You are moving with the flow. You are part of the stream. Let us begin our descent. We dip below the white methane cirrus clouds. We enter the main deck. The light begins to fade. The bright sunlight is filtered by the thick layer of gas. The vivid blue turns into a deep, twilight indigo. The pressure begins to build. On Earth, at sea level, we experience 1 atmosphere of pressure. It is a comfortable hug that holds our bodies together. Here, in the upper clouds of Neptune, the pressure is similar. If you had a heated suit and an oxygen tank, you could float here comfortably. But Neptune is a gas giant, or more accurately, an ice giant. This means there is no surface to land on. If you stop flapping your wings, you sink. And as you sink, the world changes. We drop 5 miles, 10 miles, 50 miles. The blue sky above disappears, replaced by a heavy, dark fog. The temperature, surprisingly, starts to rise. In the upper vacuum, it was -200 degrees, but as the pressure mounts, the gas becomes denser. It traps the heat coming from the core. We are entering the haze layer. Here, the methane is reacting with sunlight to form complex hydrocarbons, smog. It is a thick, chemically rich soup. The silence of space is replaced by the roar of the wind. Even though the wind is smooth, the sheer forces between different layers create a deep, thrumming vibration. The planet is humming. We pass a storm system. On Earth, a storm is a localized event. A hurricane might be a few hundred miles wide. On Neptune, storms are continents. We drift past the Great Dark Spot. It is an anticyclonic storm the size of the entire Earth. It is a hole in the atmosphere, a vortex that reaches down into the deeper, darker layers. It looks like a giant, bruising eye staring back at us. Around the edges of the spot, bright white clouds boil up, driven by convection currents that originate hundreds of miles below. These clouds are fleeting. They appear, flash into existence, and are sheared apart by the wind in a matter of hours. It is a display of ephemeral violence. We continue to sink. The pressure is now 10 atmospheres, 10 times the pressure of Earth. The air is thick, like a heavy syrup. The light is gone. The sun is just a memory. We are in the abyss. But it is not black. Lightning flickers in the distance. Massive bolts of electricity, thousands of times more powerful than terrestrial lightning, arc between the cloud layers. They illuminate the gloom with sudden, blinding flashes of white and violet. Thunder here is not a crack. It is a shock wave. Because the atmosphere is so dense, sound travels faster and carries more energy. A clap of thunder would hit you like a physical blow. We are entering the transition zone. This is the boundary where the definition of gas and liquid breaks down. On Earth, there is a clear line between the air and the ocean. You splash into the water. On Neptune, there is no splash. As the pressure climbs to 100 atmospheres, then 1,000, the hydrogen and helium gas is squeezed so tight that it stops behaving like a gas. It becomes a supercritical fluid. It is a state of matter that is thick like a liquid, but expands to fill space like a gas. Imagine floating in a fog that slowly thickens until it becomes water without ever passing a distinct surface. We are swimming now. We are swimming in a vast, planet-wide ocean of super-dense fluid. The composition is changing, too. Higher up, it was mostly hydrogen, but here, deeper down, the ices begin to dominate. In planetary science, ice doesn't just mean frozen water. It refers to water, ammonia, and methane. This is the mantle of Neptune. It is a slushy, hot, dense soup of these three ingredients. The temperature is soaring. It is now thousands of degrees hotter than the surface of lava on Earth. Wait, how can it be ice if it is thousands of degrees? This is the paradox of high pressure. Just like in our previous story about Gliese 436b, the crushing weight of the planet forces the molecules together. They cannot boil. They are trapped in a dense, fluid state. This is the ionic ocean. The water and ammonia molecules are ripped apart. They become a soup of ions, charged particles. This ocean conducts electricity. As it swirls and churns, it generates the planet's massive tilted magnetic field. But we are here for the carbon. We are here for the methane, CH4-dur. Methane is a carbon atom holding hands with 4 hydrogen atoms. Up in the clouds, the methane was a gas. It gave the planet its blue color. But down here, at pressures of hundreds of thousands of atmospheres, the methane is under siege. The pressure is trying to break the bond. It is trying to squeeze the hydrogen out. It wants to isolate the carbon. We are approaching the diamond zone. The environment is becoming claustrophobic. The weight of 10 Earths is pressing down on every square inch. The fluid is dark, hot, and heavy. It is a place of absolute crushing power. And yet there is a rhythm to it. The planet rotates once every 16 hours. This rapid spin flattens the planet at the poles and bulges it at the equator. This creates immense currents in the mantle. We are drifting in a slow churning convection cycle. Hot fluid rises, cools, and sinks again. It is this sinking that we are interested in. We are following a pocket of methane as it descends into the dark. Let us pause our descent for a moment to appreciate the scale. We are thousands of miles deep. Above us is a sky of metal hydrogen and storm clouds. Below us is a core of rock and iron, still thousands of miles away. We are suspended in the great in-between. It is a place where human biology could not exist for a microsecond. But in our imagination, we are safe. We are the ghost in the machine. We can feel the heat. We can feel the pressure. But it does not crush us. It holds us. It is a gravity blanket. Think of the heaviest blanket you have ever slept under. Now multiply that weight by 1,000,000. That is the feeling of Neptune's interior. It is a pressure that enforces stillness on the atomic level. It forces chaos into order. As we prepare for the next chapter, where the diamonds begin to form, let us reflect on the concept of value. On Earth, we value diamonds because they are rare. We dig vast mines, sift through tons of rock, just to find a tiny crystal. We polish it. We put it in a ring. We call it precious. But here, deep inside Neptune, diamonds are trash. They are the common debris of atmospheric chemistry. They are as common as raindrops in a thunderstorm. The universe is abundant. What is rare in one place is overflowing in another. Neptune is a planet of excess wind, excess pressure, excess wealth. But it keeps its wealth hidden, locked away under the blue clouds, guarded by the storms. There is a lesson here. The deep places, the places that are hard to reach, the places under pressure, are often where the most beautiful things are created. The pressure is not a punishment, it is a factory. As you rest tonight, think of the pressure of your own life. The stress, the weight of responsibilities. It can feel crushing. But maybe, deep down, it is doing something. Maybe it is taking the loose, chaotic carbon of your experiences and squeezing it. Removing the impurities. Making something hard, something clear, something bright. You are in the mantle now. Let the weight settle. Feel the density of the relaxation. The wind has stopped screaming. The lightning has faded. You are floating in the warm, dark fluid. Drift deeper into the zone of creation. Sleep in the blue giant. We have descended deep into the blue giant. We have left the screaming winds of the upper atmosphere far above us, and we have sunk through the thick twilight gloom of the cloud decks. We are now floating in the mantle, a vast planetary ocean of superheated, super-pressurized fluid. Here, thousands of miles below the cloud tops, The environment is alien to everything we know on Earth. It is a place of crushing weight and searing heat, a dark laboratory where the fundamental laws of chemistry are pushed to their breaking point. In this pitch-black abyss, there is no light from the sun. The only illumination comes from the occasional flash of deep lightning or the faint thermal glow of the fluid itself. It is a world of density. The matter here is squeezed so tightly that the distinction between liquid and solid begins to blur, and it is here, in this crushing crucible, that a miracle of transformation is about to take place. We are about to witness the birth of the diamond. To understand the rain, we must first understand the cloud from which it falls. But there are no clouds here in the traditional sense. The cloud is the fluid itself. This hot, slushy mix is composed primarily of water, ammonia, and our protagonist, methane. Methane is a simple molecule. It is the humblest of the hydrocarbons. Chemically, it is written as CH4. One atom of carbon holding hands with 4 atoms of hydrogen. In the low pressure of space, or in the kitchen stoves of Earth, this bond is strong. The carbon and hydrogen are happy partners. They float together as a gas. But Neptune is a machine designed to destroy this partnership. As we drift deeper, the pressure climbs to 1.5 million atmospheres. The temperature rises to 4,000 degrees Celsius. Under this extreme duress, the rules of engagement change. The methane molecule begins to suffer. The crushing weight forces the atoms into uncomfortable proximity. The intense heat makes them vibrate violently. The bond breaks. This process is called pyrolysis. It is the chemical equivalent of divorce. The hydrogen atoms are stripped away, liberated to float free in the protonic soup of the mantle. But the carbon atoms are left alone. Carbon is a social element. It hates to be isolated. On Earth, we see carbon bond with almost anything. Oxygen to make breath, calcium to make bone, complex chains to make life. But here, deep in the mantle, there is nothing else to bond with. The oxygen is locked up in water. The nitrogen is locked up in ammonia. The carbon is naked. So, the carbon atoms look for the only thing they can hold on to, each other. They begin to clump. At first, they form soot, tiny, amorphous specks of black carbon, drifting in the hot fluid. If you could see this scale, it would look like smoke appearing from nowhere within the liquid. But the pressure is too high for soot. Soot is messy. It takes up too much space. The gravity of Neptune demands efficiency. It demands a structure that packs the atoms as tightly as physically possible. There is only one structure that satisfies this demand: the crystal. The carbon atoms arrange themselves into a lattice. Each carbon atom grabs 4 neighbors, forming a perfect tetrahedron. It is the strongest, most rigid, most space-efficient arrangement in nature. It is a diamond. This is the moment of nucleation. A speck of dust becomes a gem. But these are not the diamonds of Earth. On our planet, diamonds are formed in the lithosphere, rare passengers brought up by volcanoes. They are usually small, a few carats, perhaps the size of a pea. On Neptune, the raw materials are limitless. The mantle is rich with carbon. The diamonds do not stop growing. They grow from dust into grains, from grains into pebbles, from pebbles into stones. Imagine a gemstone the size of a marble, then a tennis ball, then a boulder. We are talking about diamonds of colossal proportions, millions of carats in a single stone, perfect, flawless crystals forged in the dark, tumbling in the superionic fluid. and then gravity takes over. Diamond is dense. It is significantly denser than the slushy mix of water and ammonia surrounding it. On Earth, ice floats on water. On Neptune, diamonds sink. The precipitation begins. It starts as a trickle, a few glittering stones drifting downward, but soon it becomes a deluge, a storm. Diamond rain. The phrase sounds gentle, poetic, but the reality is violent and majestic. Imagine a hailstorm, but the hailstones are harder than granite and heavier than lead. They fall through the fluid, gathering speed. They are not falling through thin air. They are falling through a thick, viscous liquid. The friction is immense. As the diamonds plummet, they generate heat. They rub against the fluid, creating a wake of thermal energy. This friction is significant. Astronomers have long puzzled over a mystery regarding Neptune. Why is it so hot? It is further from the Sun than Uranus, yet it radiates 2.6 times more heat than it receives. It has an internal furnace. The falling diamonds are the fuel of that furnace. It is the conversion of gravitational potential energy into heat. As millions of tons of diamonds sink toward the core, they release energy. They warm the planet from the inside. Neptune is kept warm by the friction of its own wealth. Let us visualize the spectacle. If we could construct a submersible capable of surviving this depth, a ship made perhaps of diamond itself, and turn on the floodlights, what would we see? We would see a dark, churning ocean, and falling through the beam of light, glittering shards, some jagged, some smooth. They would reflect the light with a brilliance that is blinding. The fire of a diamond, its ability to disperse light into rainbows, would scatter our searchlight beams into a kaleidoscope of color in the gloom. We would hear them too. Not the pitter-patter of rain on a roof, but a deep, resonant clattering, the sound of heavy stones colliding with each other as they sink, the sound of a geological landslide that never hits the bottom. We might see diamond icebergs. Some theories suggest that under certain conditions, the diamonds might clump together into massive rafts before they sink. Island-sized agglomerations of crystal, drifting in the currents, slowly growing heavier until they plunge into the depths. It is a scene of terrifying opulence. Nature here is acting as the ultimate alchemist. It is taking the mundane, methane gas, the stuff of swamps and cows, and transmuting it into the ultimate symbol of durability. And the scale of this rain is global. This is not happening in one small pocket of the planet. It is happening everywhere. A spherical shell of diamond precipitation wrapping around the entire core. Billions of tons of crystal are falling every second. It has been raining diamonds on Neptune for billions of years. Where do they go? They fall toward the core. We will explore the destination in the next chapter, but for now, consider the journey. The diamonds are travelers. They are born in the middle mantle and they migrate to the deep. Science has confirmed this phenomenon here on Earth. We cannot go to Neptune, but we can bring Neptune to the lab. Using the world's most powerful lasers at the Selassie National Accelerator Laboratory in California, scientists blasted a strip of plastic, which mimics the chemistry of methane, to create shock waves. For a split second, they recreated the pressure of Neptune. And using X-rays, they watched. They saw the carbon atoms split from the plastic. They saw them form nanodiamonds, instantly. It works. The math is real. The rain is real. This discovery changed our view of the universe. We used to think diamonds were special, rare. Now we know that ice giants are actually diamond factories. And since mini-Neptunes and ice giants are some of the most common planets in the galaxy, the universe is likely littered with diamonds. There are probably planets out there that are made almost entirely of diamond, the remnants of stripped cores. But on Neptune, the diamonds are hidden. They are the secret of the interior. Let us drift with the falling stones. Feel the density of the fluid around you. It supports you. Imagine you are a carbon atom. For eons, you were bonded to hydrogen. You were light. You were a gas. You floated in the upper sky. But then you were pulled down. The pressure increased. The heat increased. You were forced to let go of the hydrogen. You were alone. But then you found others. You linked arms. You built a structure. You became strong. You became hard. And now you are sinking. But sinking is not failing. Sinking is finding your place. You are moving toward the center. There is a peace in this descent. The chaotic winds of the surface are forgotten, and the storms are miles above. Here, there's only the steady, rhythmic fall. The fluid rushes past. The heat warms you. You are a jewel in the dark. Consider the irony of value. On Earth, we fight wars over diamonds. We hoard them in safes. On Neptune, they are rain. They are dirt. They are pavement. Nature is indifferent to our economy. Nature creates beauty simply because the laws of physics demand it. The diamond is not beautiful because we say so. It is beautiful because it is the most ordered form of matter. It is the triumph of order over chaos. As you rest tonight, visualize the diamond rain. Not as a storm to fear, but as a cleansing. Imagine your thoughts are the carbon. Under the pressure of the day, they have crystallized. They have become clear. And now, let them fall. Let them sink out of your mind, down into the deep core of your subconscious. Watch them glitter as they fade into the dark. You do not need to carry them. Time, threes, gravity will do the work. The rain is falling steady and slow. Millions of gems falling in the silence. Drift with them. Sink into the warm, dark ocean. Sleep in the treasure. We have witnessed the birth of the stones. We have seen the methane molecules crushed by the fist of gravity, stripped of their hydrogen, and forged into perfect, glittering crystals of carbon. We have watched them grow from microscopic dust into colossal boulders, and we have seen them begin their long, dark fall through the superionic fluid of the mantle. They are the most expensive rain in the universe, a deluge of wealth plummeting into the abyss. But rain must eventually hit the ground. On Earth, the raindrops fall from the clouds and strike the soil, or the ocean, pooling together to flow back to the sea. On Neptune, the journey is longer, and the destination is far more exotic. The diamonds do not fall for minutes, they fall for years. They sink through thousands of miles of hot, dense fluid, but they cannot fall forever. Eventually, they reach a place where the density of the planet matches the density of the diamond. They reach the bottom of the sky. Tonight, we follow the treasure to its resting place. We descend to the deepest layers of the mantle, a region so hostile and so strange that our understanding of physics begins to break down. we will discover a layer of the planet made entirely of diamond, a solid shell wrapping around the core like a jeweled casing. We will encounter the liquid carbon ocean, where diamonds melt like ice cubes in warm water. And we will learn that this hidden layer is the engine that drives the planet's magnetic soul. Let us resume our observation from the submersible of our imagination. We are deep, tens of thousands of kilometers below the cloud tops. The pressure outside is now measured in millions of atmospheres. The fluid around us is no longer the slushy mix of water and ammonia we encountered earlier. It has been compressed into a state of matter that is stiff, viscous, and glowing with a fierce red heat. The falling diamonds are slowing down. In the upper mantle, they fell rapidly, cutting through the lighter fluid. But here, the fluid is becoming as dense as the stones themselves. Buoyancy is taking effect. Just as a coin thrown into a pool of mercury will not sink to the bottom, but will float on the surface, the diamonds are approaching their level of equilibrium. They begin to congregate. Imagine the scene. Above us, the darkness is filled with the glittering streaks of falling crystals. Below us, a landscape begins to emerge from the gloom. It is not rock, it is not mud. It is a gleaming, jagged terrain of piled diamonds. We have reached the diamond layer. Science suggests that surrounding the rocky core of Neptune is a shell of solid diamond, perhaps hundreds or even thousands of miles thick. It is a planetary vault. The falling stones land here, piling up on top of one another, fusing together under the crushing weight and heat. It is a graveyard of gems. Imagine mountains made of diamond, valleys carved not by rivers, but by the currents of the superionic fluid flowing over them. It is a landscape of stark, geometric beauty. The crystals here are not small. Because they have had eons to grow and fuse, the ground is composed of single crystals the size of cities. If you could stand on this surface, the ground would be transparent. You would be standing on a window, looking down into the very center of the world. And the ground would be glowing. The heat from the core below radiates up through the crystal lattice, turning the diamond floor into a light source. It would shine with a deep, pulsating ruby light. This layer acts as a thermal barrier. Diamond is an excellent conductor of heat. It takes the intense fire of the core and wicks it upward, releasing it into the fluid mantle. This is part of the reason Neptune is so warm on the outside. The diamond shell is the radiator of the planetary engine. But the story gets even stranger. As we move deeper into this diamond shell, the temperature continues to rise. We are approaching 8,000 degrees Celsius. The pressure is nearing 10 million atmospheres. At these extreme conditions, even diamond, the hardest substance known to man, cannot hold its shape. We reach the melting point. On Earth, we think of carbon as having two states, solid, coal, diamond, or gas in stars, but here we encounter the third state, liquid carbon. The solid diamond mountains begin to lose their edges. They soften, they flow. We are looking at an ocean of liquid diamond. It is metallic, shiny like mercury, but darker. It behaves like a liquid metal. It conducts electricity with zero resistance. This is the metallic carbon ocean. Imagine icebergs of solid diamond floating in a sea of liquid diamond. The rain from above hits the surface and melts, adding to the volume of the sea. Massive currents of molten carbon swirl around the planetary core, driven by the rotation of the giant. It is here that we solve one of the greatest mysteries of the ice giants, their magnetic fields. Earth has a magnetic field because we have a spinning core of molten iron in our center. It acts like a bar magnet, aligned with our poles, mostly. But Neptune is weird. Its magnetic field is tilted. It is offset from the center by thousands of miles. It is chaotic and multipolar. Why? Because the magnetic field is not generated in the core. It is generated here in the Diamond Ocean. The swirling currents of liquid carbon and superionic water in this outer shell act as a dynamo. Because this shell is fluid and turbulent, the magnetic field it creates is messy. It wobbles, it shifts. So the diamond rain is not just a geological curiosity. It is the architect of the planet's protective shield. The rain creates the layer creates the dynamo creates the magnetosphere that blocks the solar wind. The diamonds are the guardians of Neptune. Let us go deeper still, through the liquid carbon sea. We are approaching the absolute center, the true core. The liquid carbon eventually gives way to something else, the heavier elements that sank during the formation of the solar system: iron, nickel, silicates, rock. This is the seat of the planet. Billions of years ago, before the gas was gathered, before the diamonds formed, this rocky core was all there was, a super-Earth floating in the protoplanetary disk. It was this rock that had enough gravity to pull in the ice and gas that make up the rest of the giant. The core is roughly the mass of Earth, perhaps a bit larger, but it is buried under such immense weight that it is crushed into a sphere of unimaginable density. Here, the diamond rain stops. The diamonds float above this rocky center. The core is the anchor. It is the silent, solid heart that holds the entire chaotic structure together. It is insulated by the diamond shell. It is a lonely place, a place of absolute stillness. The winds of the surface, homotune to 100 miles per hour, are a distant memory. The currents of the mantle are miles above. Here, the pressure locks everything in place. Let us reflect on the stratification of this world. Neptune is like a grand geological layer cake. Top, the cold, blue clouds and winds. Middle, the hot, slushy ocean of water and ammonia. Lower middle, the falling rain of diamonds. Deep, the solid diamond shell and liquid carbon sea. Center, the iron rock heart. Each layer protects the one beneath it. The diamonds are the bones of the planet. They provide the structure between the fluid and the rock. There is a sense of permanence here. On Earth, diamonds eventually degrade. If you heat a diamond in the presence of oxygen, it burns and turns into CO2. Diamonds are not forever on Earth. But on Neptune, they are. There is no free oxygen here to burn them. The pressure keeps them stable. The diamond layer of Neptune will last as long as the planet itself. Even if the sun dies, even if the atmosphere is stripped away, this diamond shell will remain. If we recall the Chthonian planet from our previous story about Gliese 436b, the stripped core, we can imagine what Neptune would look like if it lost its gas. It would be a ball of diamond, a glittering sphere the size of Earth, floating in the dark. A cosmic crown jewel, but for now it is hidden. Nature loves to hide its treasures. It buries the gold in the rock. It hides the pearl in the oyster. It hides the diamond in the giant. This creates a feeling of secret wealth. The universe is rich, but it is not showy. Neptune looks plain blue from the outside, a modest sphere. But inside, it is a cathedral of crystal. As you rest tonight, connect with this inner richness. You present a surface to the world, a blue cloud layer. This is your personality, your words, your actions. It is windblown. It changes. It is visible. But underneath, you have a mantle, a deep ocean of feeling and memory. And deeper still, you have a core. Think of your core values, your fundamental truths. These are your diamonds. They were formed under pressure. They were forged in the heat of your experiences. And now they are solid. They are part of your structure. They settle deep within you, forming a protective shell around your heart. You don't need to show them to the world for them to be real. The diamonds of Neptune are unseen, yet they define the planet. Your inner worth is unseen, yet it defines you. Let us linger in the diamond ocean. The fluid is warm and heavy. It supports you completely. You are floating on a sea of liquid carbon. It is smooth, metallic. The waves are slow, rolling gently in the dark. Above you, the diamond rain continues to fall, a silent, glittering curtain. Below you, the solid core anchors you to the center of the universe. There is no wind here, no noise. Only the deep, resonant hum of the planet's magnetic soul. Feel the stability. Feel the density. You are unshakable. Rest in the crystal deep. Sleep. We have watched the diamonds form in the crushing dark, and we have followed them as they plummet toward the core, settling into a glittering ocean of liquid carbon. It is a scene of quiet, majestic geology. But in the universe, nothing comes for free. Every action has a reaction. Every movement of mass releases energy, and on Neptune, the falling of trillions of tons of diamond is not just a passive accumulation of wealth. It is the fuel for a planetary engine of terrifying power. To understand this power, we must ascend from the depths and look at the planet as a whole. We must confront a mystery that has puzzled astronomers since the Voyager 2 spacecraft first flew past in 1989. It is the mystery of the warm giant. Neptune is the 8th planet from the Sun. It orbits at a distance of nearly 3 billion miles. At this remove, the Sun is weak, providing only 1/1000th of the heat that Earth receives. By all conventional calculations, Neptune should be a frozen dead world, with an atmosphere locked in stasis, roughly minus 230 degrees Celsius. But it isn't. When we point our infrared telescopes at the blue giant, we find that it is glowing. It is emitting 2.6 times more energy than it receives from the Sun. It is a furnace in the freezer. Somehow, deep inside, Neptune is generating its own heat. It is keeping itself warm in the cold vacuum. For decades, we asked, what is the fuel? It is not nuclear fusion. Neptune is far too small to be a star. It is not radioactive decay alone. Rock is not abundant enough to account for this output. The answer, we now believe, is the rain. This is the physics of gravitational potential energy. Imagine holding a heavy stone at the top of a tower. While you hold it, it has potential. When you drop it, that potential turns into kinetic energy, movement. When it hits the ground, that movement turns into heat. Now, multiply that stone by the mass of a planet. The diamonds forming in Neptune's mantle are heavier than the fluid surrounding them. As they sink, they rub against the fluid. Friction. They are falling for thousands of miles. This friction generates heat. The gravitational energy of the falling diamond is converted directly into thermal energy. Because this is happening on a global scale, a constant planet-wide shower of heavy crystals sinking toward the center, the amount of heat released is astronomical. The diamond rain is essentially a friction heater. This heat does not stay trapped in the core. It rises. Heat wants to move to cold. The intense thermal energy generated by the settling diamond's bubbles upward through the mantle. It drives massive convection currents. Imagine a pot of boiling water. The heat at the bottom, the stove, makes the water churn. The hot water rises, cools at the surface, and sinks again. Neptune is a boiling pot, and the diamonds are the stove. This internal churning is what drives the ferocity of the surface. In Chapter 1, we marveled at the winds of Neptune, 200 miles per hour, the fastest in the solar system. We can now see that these winds are not powered by the sun, like Earth's winds. They are powered by the diamonds. The energy released by a microscopic crystal falling in the deep dark travels upward layer by layer until it manifests as a supersonic hurricane in the upper clouds. The great dark spot, that Earth-sized storm, is the exhaust vent of the diamond engine. It is where the internal heat is punching through to the surface, twisting the atmosphere into a vortex of violence. The serenity of the blue marble is a lie. The planet is screaming with energy released by its own internal segregation. To fully appreciate this, we must compare Neptune to its twin, Uranus. Uranus and Neptune are often grouped together as the ice giants. They are almost the same size. Uranus is slightly wider. Neptune is slightly more massive. They have almost the same chemical composition. They spin at similar speeds. But they are radically different in personality. Neptune is vivid blue, stormy and warm, relatively. Uranus is pale cyan, featureless, and colder than it has any right to be. Uranus is the zombie giant. It radiates almost no internal heat. Its atmosphere is calm, sluggish, and boring compared to Neptune's. Why the difference? If they are twins, why is one alive and one dead? The answer may lie in the geometry of the rain. Computer models suggest that Uranus experienced a cataclysmic event early in its history, a massive collision with an Earth-sized protoplanet. This collision knocked Uranus on its side, it spins vertically, and, we believe, scrambled its interior. The collision might have mixed the layers of Uranus too thoroughly, or perhaps stratified them too rigidly. In Neptune, the heavier materials, diamonds, are free to sink, and the lighter materials are free to rise. The convection loop is open. The heat flows. But in Uranus, the interior might be stratified, layered like a cake in a way that prevents mixing. If the layers are stable, the diamonds might still form, but they might get stuck, or perhaps the heat generated by their fall is trapped behind a layer of insulating thermal boundary. Neptune is efficient. It is sorting itself out. It is actively differentiating its core from its mantle. Uranus is constipated. The heat is trapped inside, unable to reach the surface to drive the storms. This tale of two giants highlights just how crucial the diamond rain is. It is not just a mineralogical curiosity. It is the heartbeat of the planet's climate. Without the free-falling diamonds, Neptune would be as quiet and pale as its brother. Let us return to the atmosphere of Neptune with this new understanding. We see the scooter, a small, bright white cloud that zips around the planet every 16 hours. We used to think it was just weather. Now we see it as a plume of heat. It is a chimney. Deep below that cloud, a massive cluster of diamonds has likely just settled, releasing a pulse of thermal energy that shot upward like a geyser, condensing the methane at the top into a fresh white cloud. The weather forecast on Neptune is dictated by the mining operations of gravity deep below. This connects the very small, the crystal lattice of carbon, with the very large, the planetary storm. It is a beautiful chain of causality. Carbon atoms bond, diamond forms, diamond sinks. Friction creates heat. Heat creates convection. Convection creates wind. Wind creates beauty. We also have to consider the age of the process. Neptune is 4.5 billion years old. The rain has been falling for a long time. Is it running out of carbon? Is the fuel gauge getting low? Estimates suggest that the mantle is vast enough to sustain this process for billions of years more. Neptune is in its prime. However, as the diamonds settle and the core grows larger, the free carbon in the upper mantle will deplete. Eventually, the rain will stop. When the rain stops, the heat engine will turn off. The winds will die down, the great dark spot will close, the bright blue color might fade to a paler cyan as the atmospheric mixing slows. Neptune will eventually become like Uranus, quiet, cold, dead. We are privileged to see it now in its energetic youth. We are witnessing the diamond era of the planet. There is a grandeur in this mechanism. On Earth, our weather is driven by the sun. We are solar-powered. Time, threes. Neptune is gravity-powered. It relies on itself. It is an independent world, glowing in the dark, fueled by the crystallization of its own substance. As we drift away from the turbulent cloud tops, looking back at the royal blue sphere, we perceive it differently. It is not just a ball of gas. It is a dynamo, a heat exchanger, a sorter of elements. The stillness of space surrounds it, but inside it is churning with purpose. In the next chapter, we will turn our attention to the guardians of the system. Neptune is not alone. It has a retinue of moons. And one of them, Triton, is a rebel, a captured king from the deep dark. We will explore how the gravity of the diamond giant affects its neighbors, and how the heat radiating from the planet might be thawing the frozen worlds that orbit it. The influence of the diamonds extends beyond the atmosphere. It touches the moons. The giant hums, and the satellites listen. We have spent our time deep within the belly of the beast, navigating the diamond-studded oceans and the screaming winds of the interior. But the gravitational influence of Neptune extends far beyond its cloud tops. Like a king sitting on a throne of blue crystal, the planet commands a vast territory of empty space. It holds court over a retinue of 14 known moons and a faint, dusty system of rings. Most of these moons are small, misshapen lumps of ice and rock, the debris of the early solar system that was swept up by the giant's gravity. They huddle close to the planet, orbiting in neat, orderly circles, moving in the same direction as Neptune's rotation. They are the obedient subjects. But there is one moon that does not fit, one moon that defies the order of the kingdom. Floating in the outer dark is a world as large as Pluto, glistening with a pale, pinkish frost. This is Triton. It is the 7th largest moon in the solar system, but it is unique among the giants. It is a rebel. While Neptune spins counterclockwise, Triton orbits clockwise. It moves against the traffic. It is the retrograde moon. This backward motion tells us a violent secret. Triton was not born here. It did not form from the dust that circled the infant Neptune. It is an impostor, an intruder, a stranger from the deep dark that was snatched against its will. Tonight, we explore the tragedy of this captured king. We will walk on its nitrogen glaciers, witness the silent eruptions of its cryovolcanoes, and learn that the gravity that forges diamonds in the deep is the same gravity that is slowly, inexorably, pulling this moon to its death. To understand Triton, we must look to its origin. Billions of years ago, Triton was a dwarf planet, much like Pluto. It lived in the Kuiper Belt, the vast ring of frozen debris that lies beyond the orbit of Neptune. In that cold, quiet realm, Triton was likely not alone. It probably had a partner, a moon of its own, just as Pluto has Charon. They danced together in the dark, a binary pair drifting through the outer rim. But then they drifted too close to the blue giant. Neptune's gravity is immense. As the pair approached, a gravitational heist occurred. Neptune grabbed Triton. The energy of the capture had to go somewhere, and it was transferred to Triton's partner. The partner was flung away, ejected into the interstellar void at high speed, sacrificed so that Triton could be enslaved. Triton was pulled into a massive, elongated orbit. It was chaos. The arrival of such a heavy moon disrupted the original satellite system of Neptune. The small, native moons were scattered, colliding with one another, or being thrown out of the system entirely. Nereid, another of Neptune's moons, was flung into a wild, looping orbit that takes it millions of miles away, a permanent exile caused by Triton's arrival. Eventually, the tides calmed Triton. The oval orbit circularized, but the scar remains, the backward motion. It is a permanent reminder that this moon is a prisoner of war. Let us descend to the surface. If you thought Neptune was cold, Triton is the definition of deep freeze. It is one of the coldest objects in the solar system. The surface temperature is minus 235 degrees Celsius, minus 391 Fahrenheit. It is only 38 degrees above absolute zero. At this temperature, chemistry stops. Life as we know it is impossible. The very air freezes. Nitrogen, which is a gas on Earth, is a solid rock here. The ground is made of nitrogen ice. It is hard as granite, yet brittle. The landscape is bizarre. We do not see impact craters like on our moon. Triton's face is young. It has been resurfaced. Instead of craters, we see the cantaloupe terrain. Imagine the skin of a melon, wrinkled, dimpled, crisscrossed with ridges and depressions. This texture covers huge swathes of the moon. It is a sign of internal activity. Despite the freezing cold surface, the interior of Triton is warm. Why is it warm? Because of Neptune. The same tidal heating that we saw in Gliese 436b plays a role here. The massive gravity of the diamond giant flexes the moon. It stretches and squeezes the rocky core of Triton. This friction generates heat. Triton is being kept alive by the stress of its captivity. This internal warmth fights the external cold, and where they meet, we find the geysers. When Voyager 2 flew past in 1989, it saw something shocking. Streaks of black dust painted across the pink ice of the southern polar cap. And then it saw the plumes. Jets of nitrogen gas shooting 5 miles into the thin atmosphere. This is cryovolcanism, ice volcanoes. The mechanism is a solid-state greenhouse. The sun is faint here, but it is relentless. The sunlight passes through the clear layer of surface nitrogen ice. It hits the darker material below. The dark material absorbs the heat. The temperature rises slightly. The nitrogen ice below the surface turns into gas. Pressure builds. It pushes up against the ice crust. Eventually, it bursts. A mixture of nitrogen gas and dark carbon dust explodes upward. It shoots into the vacuum. But Triton has a thin atmosphere and fierce high-altitude winds. As the plume rises, it hits the wind shear. The top of the geyser is blown sideways. It forms a long dark streak like a smoke trail from a factory chimney, stretching for 100 miles. Imagine standing on that freezing plain. The sky is black, even at noon. The sun is a pinprick. The giant blue crescent of Neptune hangs in the sky, dominating the view, glowing with the reflected light of its methane clouds. And all around you, silent jets of black smoke are erupting from the white ground, painting the ice with the soot of the interior. It is a stark, monochromatic beauty: black dust, white nitrogen, pink methane, blue planet. The pink color comes from tholins. Methane ice on the surface is bombarded by ultraviolet light from the sun and radiation from Neptune's magnetosphere. This radiation chemically alters the methane, turning it into complex organic gunk. It turns red. It is the rust of the outer cosmos. Triton is a world of contrasts. It is dead cold on the outside, but churning on the inside. It is a captured object, yet it is the most active moon of the system. But the story of Triton is a tragedy. It is a story with a ticking clock. Because of its retrograde orbit, Triton is fighting against the rotation of Neptune. This creates a tidal drag. Most moons, like our own, are slowly drifting away from their planets. Our moon moves an inch further away every year. Triton is falling. It is spiraling inward. Every orbit brings it slightly closer to the cloud tops. The gravity of the diamond giant is reeling it in. It is a slow descent. It will take perhaps 3.5 billion years. But the end is inevitable. Eventually, Triton will cross a threshold known as the Roche limit. This is the point of no return. It is the distance where the gravity of the planet pulling on the near side of the moon is so much stronger than the gravity pulling on the far side that the moon is physically torn apart. The structural integrity of the ice cannot withstand the tide. Imagine the final days of Triton. The moon will groan. Massive fractures will open in the nitrogen crust. The geysers will erupt uncontrollably as the interior is squeezed. And then, silently, the moon will shatter. It will crumble into billions of pieces, boulders of ice, mountains of rock, dust. Triton will die. But in its death, it will create a monument. The debris from the destroyed moon will not fall into Neptune immediately. It will be spread out into a ring. A spectacular, bright, massive ring system. Neptune will become the Lord of the Rings. Time, threes. The rings of Saturn are majestic, but they are old and fading. The rings of Neptune will be new, fresh, and brilliant. They will outshine anything the solar system has ever seen. Neptune will wear the corpse of its prisoner as a crown. This future event connects the diamond rain inside to the ring system outside. The planet is a consumer. Inside, it consumes methane to make diamonds. Outside, it consumes moons to make rings. It is an engine of transformation. It takes raw materials, gas, ice, rock, and grinds them down into more ordered forms, crystals, circles. There is a melancholy in observing Triton. We are looking at a world on death row. It is beautiful, active, and vibrant in its own frozen way, but it is doomed. Yet looking at it from another perspective, its destruction will be its apotheosis. Right now, Triton is just a dot to anyone watching from another star. But when it becomes a ring, it will increase the reflective power of Neptune. It will make the planet brighter. It will become a grander signal. As we float above the cantaloupe terrain, watching the plumes of the geysers drift in the tenuous wind, we can feel the tension. The moon is holding itself together against the pool. It is the tension of the retrograde, the tension of going the wrong way. There is a lesson here. To go against the flow is energetic. It creates heat. It creates geysers. It creates interesting terrain. But ultimately, the flow wins. The larger gravity wins. The rebel is eventually absorbed. But in the process of being absorbed, the rebel changes the system. Triton has changed Neptune. It cleared out the other moons. It tilts the magnetic field, and it will eventually give the planet its crowning glory. The capture was not in vain. Let us rest in the shadow of this future. The timeline is vast, 3 billion years. For now, the moon is safe. It orbits in its lonely backward loop. Watch the geysers gently puffing nitrogen into the dark. Silent chimneys of the cold. The diamond giant watches below. Patient. Heavy. Waiting. Drift in the retrograde path. Float in the pink ice. Sleep in the shadow of the giant. We have journeyed deep into the diamond-studded heart of Neptune and flown high above the frozen geysers of its captured moon. We have seen the specific wonders of the eighth planet. But to truly understand Neptune, we must step back. We must stop looking at the tree and start looking at the forest. Because as we gaze out into the wider galaxy, scanning the darkness for other worlds orbiting other stars, we are discovering a startling truth. Neptune is not rare. In fact, it might be the most common type of neighbor in the universe. For a long time, we thought our solar system was the standard blueprint. We had rocky dwarfs, Earth, Mars on the inside, and gas giants, Jupiter, Saturn on the outside. We assumed the rest of the cosmos followed this binary rule. But the Kepler Space Telescope shattered that assumption. It revealed that the galaxy is teeming with worlds that are neither rock nor gas giant. They are something in between. They are mini Neptunes. Tonight, we examine the ice giant as an archetype. We explore why the universe loves to build these blue, frozen worlds, and why our own solar system is arguably the strange one for having so few of them. We will dive into the waterline of the galaxy, and we will realize that the diamond rain we witnessed in the previous chapters is likely happening on billions of worlds right now. We are living in a galaxy of hidden gems. To understand the popularity of the ice giant, we must look at the kitchen of the cosmos. When a star is born, it is surrounded by a disk of dust and gas. Near the star, it is hot. Water exists only as vapor. It is hard to build a big planet here because there isn't enough solid material. You only have rock and metal. That's why Earth is small. But if you travel outward, you cross a magical boundary, the snow line. Beyond this line, it is cold enough for water to freeze into solid ice grains. Suddenly, the amount of solid material available to build a planet jumps by a factor of 10. You are not just building with rock anymore. You are building with ice, and ice is everywhere. Oxygen is the third most common element in the universe, and hydrogen is the first. Put them together, and you get water. So out in the deep freeze, planets grow fast. They gobble up the rock, but they also gobble up the ice. They grow massive cores, 10 times the mass of Earth. These heavy cores then have enough gravity to pull in some hydrogen and helium gas from the nebula, wrapping themselves in a thick blanket. The result is a Neptune, a rocky core surrounded by a massive mantle of water, ammonia ice, wrapped in a gas atmosphere. It is the natural outcome of cosmic chemistry. It is the default planet. This realization leads to the missing planet mystery of our own home. In exoplanet surveys, the most common size of planet we find is between Earth and Neptune, super-Earths and mini-Neptunes. But look at our solar system. We have Earth, radius 1. We have Neptune, radius 4. We have nothing in between. We have a gap. Why? Did Jupiter eat our super-Earths? Did they get ejected? Or did we just happen to form in a weird way? Whatever the reason, looking at Neptune is our only way to understand the most populous demographic of the galaxy. When we study the diamond rain on Neptune, we are studying a phenomenon that is likely occurring in the interiors of the Kepler planets. Imagine the scale. Billions of stars. Billions of mini-Neptunes. That means there are billions of diamond oceans out there. The universe is absolutely loaded with crystallized carbon. But not all ice giants are created equal. We must consider the hot Neptunes. In other systems, we see Neptune-sized planets that have migrated inward. They orbit close to their stars, roasting in the heat. We saw one in our previous story, Gliese 436b. On these worlds, the physics of the interior would be different. The external heat would slow down the cooling of the core. The convection currents would be even more violent. The diamond rain might be even more intense, fueled by the higher energy of the system. Conversely, there are rogue Neptunes. Planets that were kicked out of their systems entirely. They float in the interstellar dark, tethered to no star. On these lonely wanderers, the atmosphere would freeze. The blue clouds would collapse into nitrogen snow. The planet would be a black sphere in the black void. But deep inside, the heat engine would still be running. The diamonds would still be falling. The frictional heat would still be keeping the mantle liquid. A rogue Neptune is a warm heart and a cold corpse. Even in the absolute zero of deep space, the diamond rain keeps the fire burning deep within. This brings us to the concept of habitability. Usually, when we look for life, we look for Earth 2.0. We look for warm rocks with liquid water on the surface. But the ice giants challenge this narrow view. As we saw, Neptune has a mantle of superionic water. It is hot, yes, but it is water, and it is rich in organic chemicals, methane, ammonia. Could life exist in the fluid mantle of an ice giant? It seems unlikely. The pressures are crushing. The temperatures break molecular bonds. But what about the moons? Time, threes? If ice giants are common, then exomoons orbiting ice giants must be common too. A giant planet acts as a hearth. It radiates heat from the diamonds. It creates tides. We could imagine a system where a Neptune-sized planet orbits in the habitable zone of a star, and a large rocky moon orbits the planet. The moon would have light from the star, heat from the planet, and a magnetic shield provided by the planet's magnetosphere. It might be the ideal place for life. The world of Pandora in the movie Avatar is exactly this, a lush moon orbiting a gas giant. So Neptune is not just a destination, it is an anchor for potential biology. Let us consider the color again. We love the blue of Neptune, but in the galaxy, ice giants might come in many colors. Depending on the temperature and the cloud composition, they could be green, if covered in algae-like haze, purple, from exotic photochemistry, or white, if covered in water clouds. But the underlying structure remains, the diamond factory. Nature seems to have settled on this design as a favorite. It is a stable configuration. Gas giants like Jupiter are hard to make. You need a lot of gas fast before the star blows it away. Rocky planets like Earth are hard to see. They are tiny. Neptunes are the Goldilocks planets of formation, easy to make, hard to destroy. They are the survivors. As we look at our own Neptune, we should feel a sense of connection to the wider cosmos. When you look at that blue dot through a telescope, you are looking at the local representative of the Galactic Council. It is our ambassador to the ice giant majority. And the treasure it holds inside is shared by its trillions of cousins. The galaxy is not dark, it is glittering on the inside. Think of the network of diamonds. If you could see the interiors of all the planets in the Milky Way, you would see a web of diamond cores glowing in the dark. A hidden constellation of wealth. Neptune is just the closest node in that network. As we prepare for the final chapter, let us rest in the knowledge of this abundance. We often feel scarcity. We feel there isn't enough to go around. But the universe operates on a different economy. It rains diamonds, it rains methane, it rains iron on other worlds. There is no shortage of material. The ice giants stand as monuments to the success. Huge, blue, filled with crystal. Let the image of the default planet soothe you. It means that the universe is reliable. It makes the same thing over and over again because it works. It means there's order in the chaos. You are part of that order. The water in you is the same water that makes up the mantle of Neptune. The carbon in you is the same carbon that makes the diamonds. You are a small, warm, living version of an ice giant. Drift in the commonality. Float in the galactic sea. Sleep. We have traveled to the very edge of the solar system, and then we have traveled inward to the very edge of physics. We have drifted through the high-altitude methane clouds, survived the supersonic winds of the dark spots, and descended through the crushing mantle where the air becomes ocean and the rain becomes stone. We have witnessed the birth of diamonds in the dark, and we have floated on a sea of liquid carbon that generates the magnetic soul of the giant. But as our journey comes to an end, we must return to the surface. We must ascend from the crushing depths, leaving the diamond ocean behind in its eternal heated darkness. We rise back through the layers, through the transition zone, past the lightning storms, up through the haze, until we break the surface of the blue clouds and find ourselves once again in the silent, open vacuum of space. Tonight, in this final chapter, we look to the future. We look at the destiny of this magnificent world. We will imagine the day when humanity finally returns to the ice giant, not just with telescopes, but with a vessel designed to dive into the treasure. And we will reflect on the ultimate fate of Neptune, a world that will likely outlive the Earth, outlive the sun, and remain as a cold, glittering monument in the dark. long after the rest of the solar system has crumbled to dust. To date, only one spacecraft has ever visited Neptune, Voyager 2. It was a brief flyby in 1989. It spent only a few hours in the vicinity of the planet before hurtling onward into the interstellar void. Since then, Neptune has been lonely. For over 30 years, it has orbited in solitude, watched only from billions of miles away by the Hubble Space Telescope and earthly observatories. But the diamonds are calling us back. Scientists are currently dreaming of a new mission, a Neptune orbiter. Imagine a spacecraft, nuclear-powered, arriving after a 10-year cruise through the dark. Unlike Voyager, it does not fly by. It fires its engines. It brakes. It inserts itself into orbit around the blue giant. It would spend years circling the world, mapping the gravity field, radar scanning the clouds, and studying the rings. But the climax of the mission would be the probe. Just as the Galileo mission dropped a probe into Jupiter, this mission would drop a probe into Neptune. Visualize the moment of release. A small, cone-shaped capsule separates from the mothership. It spins for stability. It begins its fall toward the blue atmosphere. It hits the upper atmosphere at 30,000 miles per hour. The heat shield glows white-hot, creating a streak of fire across the alien sky. The parachute opens. The probe slows. And then it begins to listen. For the first time in history, we would hear the sound of the winds of Neptune. We would measure the exact composition of the methane. We would detect the first hints of the diamond rain. The probe would eventually be crushed, of course. It could never reach the diamond ocean, but its final transmission would be a message from the deep, a confirmation of the treasure. Why do we care? Why travel 3 billion miles to count falling stones? Because Neptune represents the long game of the solar system. The inner planets, Mercury, Venus, Earth, Mars, are fragile. They are close to the Sun. They are at the mercy of the star. When the Sun expands into a red giant in 5 billion years, the inner planets will be vaporized or scorched. But Neptune is safe. It is far away in the frozen suburbs. When the Sun swells, Neptune will merely get a little warmer. The ice on its moons might melt, creating transient oceans on Triton. The storms might get fiercer. But the planet will survive. And when the Sun dies, when it sheds its layers to become a white dwarf, Neptune will still be there. It will be orbiting a dead star. The days will become even dimmer. The noon will be indistinguishable from midnight. But the engine inside will keep running. The diamond rain does not depend on the sun. Gravity is its fuel. For trillions of years, long after Earth is a forgotten cinder, Neptune will continue to generate heat. The diamonds will continue to fall. The magnetic field will continue to hum. It is the eternal planet. This gives Neptune a sense of nobility. It is the guardian of the solar system's memory. Deep in its core, locked in the rocky center, are the atoms that formed at the very beginning of the solar nebula. They are protected by layers of liquid diamond and superionic water. They are safe from the chaos of the universe. Neptune is a time capsule. Let us imagine the view from a moon of Neptune in this distant future. The sun is a tiny, piercingly bright white dot, the white dwarf. The sky is black. But the planet Neptune dominates the view. It glows. In the infrared, it is a beacon, a warm coal in the freezing night. It is a source of comfort in a dying galaxy. We spoke earlier of the rogue Neptunes of planets ejected from their systems. Our Neptune is not a rogue, but it shares their resilience. It proves that a planet can be self-sufficient. It teaches us that true strength comes from the inside. Earth relies on external warmth. If the sun goes out, Earth freezes. Neptune relies on internal warmth. If the sun goes out, Neptune keeps churning. The diamonds are the secret of its independence. As we prepare to leave this giant, let us take one last look at the great dark spot. It is a storm, yes, but it looks like a pupil. The blue eye of the cosmos. It is watching the void. There's a theory that life on Earth might have been seeded by comets that came from the neighborhood of Neptune, the Kuiper Belt objects. If so, Neptune is like a shepherd. Its gravity herds the comets. Sometimes it throws them inward, toward the sun, toward us. Without the ice giants to stir the pot, the inner solar system might have been dry. So, we owe a debt to the diamond maker. It is not just a distant curiosity. It is a planetary elder that helped shape our history. Now bring your awareness back to the sensation of weight. We have talked about pressure, the crushing weight of the atmosphere. But let us reframe pressure as holding. A weighted blanket does not crush you. It holds you. It signals to your nervous system that you are safe. The gravity of Neptune holds the planet together. It holds the moon Triton. It holds the rings. And it holds the diamonds. Imagine you are being held by that same gravity. Not crushing, just firm, secure. You are a diamond in the rough. You have descended through the layers of your day. You have passed through the cloudy thoughts. You have passed through the stormy emotions. You have reached the core, the solid, unmoving center of who you are. Here, in the deep, it is quiet. The winds of the surface cannot reach you. The cold of space cannot touch you. You are insulated by the layers of your own experience. Visualize the diamond ocean one last time. A vast, dark, liquid sea. Smooth as glass. Warm. The rain has stopped. The storm has passed. There's only the gentle ripple of the currents. You are floating on that ocean. Drifting in the dark. Supported by the density of the deep. Neptune is spinning slowly once every 16 hours. A rocking motion. Back and forth. Lulling the solar system to sleep. The blue giant is the guardian of the night. It will keep watch while you rest. Its storms are far away. Its heart is steady. You are safe in the silence of the outer rim. Drift in the blue. Sleep in the diamond deep. Good night. Tonight, we leave the familiar warmth of our yellow sun and the solid surfaces of the rocky planets to venture into the furthest reaches of physical possibility. We are traveling toward objects that defy every intuition we possess about the nature of matter, gravity, and time. These are the neutron stars, celestial bodies so dense, so violent, and so strange that for decades, even the most brilliant physicists believed they were merely mathematical curiosities, ghosts in the equations that could never truly exist in the theater of the real universe. As you settle into your rest, imagine a world where the mass of a mountain is squeezed into the size of a grain of sand, where a single teaspoon of material weighs as much as the entire human race combined, and where the very fabric of space is warped into a funnel of staggering proportions. This is a journey to the edge of the impossible, to the remnants of dead stars that have collapsed under the weight of their own history. To understand how such an object can exist, we must first look at the life and the spectacular death of the stars that give birth to them. A neutron star is not born from a star like our Sun. It requires a Titan, a massive star at least 8 to 20 times more massive than the one that warms our Earth. Throughout its life, such a star is a theater of constant struggle. Deep within its core, at temperatures of hundreds of millions of degrees, the star is a nuclear furnace. On a molecular level, it begins by fusing hydrogen into helium, then helium into carbon, neon, and oxygen. Each stage of fusion releases a gargantuan amount of energy, creating an outward pressure that supports the star against the relentless inward pull of its own gravity. For millions of years, this balance, this hydrostatic equilibrium, holds the star together in a state of magnificent, luminous stability. But the physics of the universe dictates a tragic end for these giants. As the star ages, it begins to forge heavier and heavier elements, eventually reaching the element iron. Here, the nuclear fire hits a wall. Fusing iron does not release energy, it consumes it. On a microscopic scale, the iron nuclei act as a poison to the star's internal engine. The moment the core turns to iron, the outward pressure vanishes, and gravity, the patient, unyielding master of the cosmos, finally wins. In a fraction of a second, a core the size of the Earth, weighing more than the Sun, collapses inward at a quarter of the speed of light. This is the moment of the core collapse supernova, an explosion so bright it can outshine an entire galaxy of 200 billion stars. What remains in the center of this cataclysm is the neutron star. During the collapse, the pressure becomes so extreme that it overcomes the electromagnetic force that usually keeps atoms apart. On a subatomic level, a process known as electron capture occurs. The electrons are literally crushed into the protons, merging to form a sea of neutrons and releasing a ghost-like flood of neutrinos that carry away the energy of the dying star. The result is a sphere only 20 kilometers in diameter, roughly the size of a small city. Yet it contains more mass than our entire solar system. It is a solid ball of nuclear matter, a gargantuan atomic nucleus held together not by the strong force, but by the crushing weight of gravity itself. The human story of discovering these impossible objects is a testament to the power of pure thought and the eventual confirmation of the machine. In 1932, just months after James Chadwick discovered the neutron, the physicists Lev Landau, Walter Baade, and Fritz Zwicky proposed that stars made entirely of neutrons could exist as the end state of supernova. At the time, their colleagues laughed. The idea of matter being crushed to such densities seemed like science fiction. It took 35 years of patient listening to the sky for the confirmation to arrive. In 1967, a young graduate student named Jocelyn Bell Burnell noticed a strange rhythmic scruff on her radio telescope charts. It was a signal pulsing with a precision of 1.33 seconds, so regular that her team briefly dubbed it LGM-1, little green men won. They soon realized they weren't listening to aliens, but to the frantic heartbeat of a rotating neutron star, a pulsar, announcing its presence to the universe. Linger for a moment on the staggering density of this object. If you were to take a single sugar cube of neutron star material and bring it to Earth, it would weigh approximately 1 billion tons. On a molecular level, there are no molecules left. The crystalline structures of the everyday world have been pulverized. The atoms have been stripped of their identity. We find ourselves in a state of matter called neutron degenerate matter. Because of the Pauli exclusion principle, a fundamental law of quantum mechanics, no two neutrons can occupy the same state at the same time. This creates a degeneracy pressure that is the only thing standing between the neutron star and its final collapse into a black hole. It is a world held up by the sheer stubbornness of subatomic particles, refusing to be squeezed any further. The gravity on the surface of a neutron star is 200 billion times stronger than the gravity on Earth. To achieve a deeper sense of this force, imagine dropping a pebble from a height of only 1 meter. By the time it struck the surface, it would be traveling at 2 million meters per second, and the impact would release as much energy as a tactical nuclear weapon. The surface itself is smooth beyond imagination. The gravity is so strong that any mountain or ripple is instantly crushed. The tallest mountains on a neutron star are likely no more than a few millimeters high, yet to climb one would require more energy than a human could generate in a lifetime. This is the ultimate landscape of flatness and force, a billiard ball of nuclear steel spinning in the dark. As these stars collapse, they conserve their angular momentum, causing them to spin at incredible speeds. Imagine a figure skater pulling in their arms. As the star shrinks from 1 million kilometers wide to only 20, its rotation accelerates until it is spinning hundreds of times every second. At the same time, the star's magnetic field is compressed, becoming 1 trillion times stronger than the magnetic field of the Earth. This creates a gargantuan celestial lighthouse. Beams of intense radio waves and X-rays blast out from the magnetic poles, sweeping across the cosmos like a searchlight. When these beams happen to cross the Earth's path, we detect them as the rhythmic pulses that Jocelyn Bell first observed. These are the pulsars, the most accurate clocks in the universe, losing less than 1 second every billion years. Consider the sensory experience of the environment surrounding a neutron star. The space is filled with a lethal blizzard of radiation and particles accelerated to nearly the speed of light. The magnetic field is so powerful that on a molecular level it would distort the very shape of atoms, stretching them into long, needle-like cylinders. Even the vacuum itself becomes refractive, bending the path of light in ways that defy our terrestrial optics. If you were to look at a neutron star, the gravity is so strong that it bends the light from the back of the star around to the front, allowing you to see both the front and parts of the back at the same time. It is a world of optical illusions and physical extremes, a place where the familiar rules of the universe have been rewritten by the hand of gravity. To truly appreciate the impossibility of these objects, we must look at their internal structure, a layering of matter that exists nowhere else. Scientists use the term nuclear pasta to describe the shapes matter takes deep within the crust. As we descend through the outer layers of iron and nickel, the increasing pressure forces the nuclei to merge into strange, elongated structures. On a microscopic scale, we find gnocchi phases of isolated spheres, spaghetti phases of long rods, and lasagna phases of flat sheets of nuclear matter. These are the strongest materials in the universe, billions of times tougher than steel, yet they exist in a state of superfluidity, flowing with zero friction like a cosmic liquid. This is the inner world of the neutron star, a place of exotic phases and quantum wonders hidden beneath a crust of diamond-hard iron. The perspective of deep time reveals the neutron star as a permanent resident of the galaxy. While the stars that gave birth to them lived for only a few million years, the neutron stars will endure for trillions. They are the cold embers of the cosmos. Over eons, they slowly radiate away their heat, cooling from millions of degrees down to the cold of the vacuum. But they do not fade away. They remain as silent, dark sentinels, gravitational anchors that will persist long after the last normal star has exhausted its fuel. They are the ultimate survivors, the remnants of a more violent age of the universe, preserved in a state of crystalline, nuclear perfection. In the silence of your rest, try to feel the resonance of these monumental objects. Though they are thousands of light years away, they are part of the same physical reality as your own breath. The atoms in your body, the calcium in your bones, the iron in your blood, were forged in the same massive stars that later collapsed into these neutron giants. You are a part of the same story of stellar life and death. The stability of the neutron star, held together by the fundamental laws of the quantum world, is a reflection of the deep order of the universe. There is no chaos here, only the absolute, unwavering application of the laws of physics. The darkness of the night is a soft, deep blanket, much like the vacuum that surrounds a lonely pulsar in the deep dark. As you drift into sleep, let the rhythmic, steady pulse of a distant neutron star be your lullaby. It is a heartbeat that has lasted for millions of years and will continue for billions more. The gravity of the world around you is a gentle, grounding force, a tiny echo of the titanic power that shapes the neutron star. You are safe in the cradle of a universe that can create such wonders, protected by the same laws that ensure the sun will rise and the stars will turn. Everything is in its right place. Everything is balanced, and everything is at rest. The journey to the edge of the impossible is now part of your own quiet history. You have looked into the heart of a collapsed sun and seen the beauty of matter pushed to its limit. The image of the spinning lighthouse and the nuclear pasta is a warm, fading light in your mind. The vacuum is a place of infinite rest, a sanctuary where time and gravity move with a slow, majestic grace. You are floating in the stream of stars, a voyager in the deep. Find your peace in the enduring, silent presence of the neutron giants. The night is vast, the mystery is deep, and you are finally, safely, at home in the arms of the cosmos. As we move deeper into the dark, leaving the rhythmic pulse of the ordinary pulsar behind, we encounter a subclass of neutron stars that exists at the very outer boundaries of physical sanity. These are the magnetars. If a standard neutron star is a miracle of density, a magnetar is a miracle of force, specifically the force of magnetism, amplified to a degree that defies any terrestrial comparison. To understand a magnetar, we must imagine an object that has taken the magnetic field of a star and crushed it down, focusing it into a space no larger than a city. The resulting field is a quadrillion times stronger than the magnetic field that gently guides a compass needle on Earth. It is a force so monumental that it ceases to be a mere physical property and becomes a structural architect of the vacuum itself, capable of warping the very atoms of anything that dares to draw near. On a molecular level, the influence of a magnetar is nothing short of transformative. In our everyday world, atoms are roughly spherical, with electrons clouding around a central nucleus in a state of delicate balance. But within the vicinity of a magnetar, the magnetic pressure is so immense that it overcomes the electrostatic forces that give matter its shape. If you were to approach within 1,000 kilometers of such an object, the magnetic field would seize the atoms in your body and stretch them into long, thin needles, thinner than a strand of DNA. At this point, the chemistry of life becomes impossible. The bonds that hold molecules together are snapped and reshaped by the sheer geometry of the field. This is magnetism, not as we know it, but as a fundamental reordering of reality. The human story of identifying these magnetic monsters began in the spring of 1979, during a period of intense astronomical observation. On March 5th, a massive burst of gamma radiation swept through our solar system, triggering every high-energy detector on our satellites. It was a flash of energy so powerful that it briefly blinded the sensors designed to monitor nuclear tests on Earth. For years, this March 5th event remained a profound mystery. Astronomers like Robert Duncan and Christopher Thompson spent over a decade working through the mathematics of extreme magnetic fields to explain what could produce such a titanic outburst. They realized that they were seeing the star quakes of a magnetar, a crustal snap that releases more energy in 1/10 of a second than our sun produces in 10,000 years. To achieve the depth required to grasp this power, we must consider the specific scale of a magnetar's field. If a magnetar were to somehow drift into the space halfway between the Earth and the Moon, a distance of nearly 200,000 kilometers, its magnetic field would be strong enough to instantly erase the data from every credit card and hard drive on our planet. If it came closer, say within the orbit of our satellites, the magnetic pull on the iron in our blood and the minerals in our soil would be enough to physically pull the Earth apart. Yet, these objects are invisible to the naked eye, hidden in the vastness of the galaxy, announcing their presence only through the violent release of energy when their magnetic fields become too tangled to remain stable. Linger for a moment on the internal struggle of a magnetar's crust. On a microscopic scale, the crust is a lattice of iron nuclei, crushed to a density 1,000,000,000,000 times that of lead. Because the magnetic field is frozen into this matter, any movement in the interior of the star, puts immense stress on the surface. Imagine the crust as a solid shell of diamond-hard metal under which the magnetic field lines are twisting and knotting like angry serpents. Eventually, the crust can no longer hold the tension. It fractures in a starquake, a rift only a few millimeters wide, but one that releases a tidal wave of gamma rays and X-rays that ripples across the cosmos. It is the most violent geological event in the universe, a snapping of the atomic fabric itself. The physics of this gamma-ray emission is a masterclass in high-energy processes. When the crust snaps, the magnetic field lines vibrate with such intensity that they create a fireball of electron-positron pairs, matter and antimatter, created directly from the energy of the field. On a subatomic level, these particles annihilate and reform in a frantic dance, trapped within the magnetic cage of the star. This fireball is what produces the blinding flash of radiation we detect on Earth. It is a process of magnetic reconnection, a larger and far more lethal version of the flares we see on our own sun. But while a solar flare might disrupt radio communications, a magnetar flare is a cosmic beacon that can be seen from the other side of the galaxy. Consider the sensory experience of the space surrounding a magnetar. The vacuum here is not empty. Because the magnetic field is so strong, it induces a phenomenon called vacuum birefringence. This means the empty space itself becomes like a prism, splitting light into different components and bending its path. If you could look toward a magnetar, you would see a sky warped and distorted, with the background stars appearing as smeared arcs of light. The air, if there were any, would crackle with the energy of the vacuum being torn apart. There is a glow to the space around the star, an eerie, high-energy luminescence produced as virtual particles are ripped out of existence by the magnetic force. It is a place of absolute, terrifying beauty, where the invisible has become a physical wall. To truly appreciate the impossibility of these magnets, we must look at their lifespan. Magnetars are the brightest and fastest of the neutron star family. Because they radiate energy so aggressively through their magnetic fields, they spin down and lose their magnetic potency relatively quickly. A magnetar may only remain active for 10,000 years, a mere blink of an eye in the cosmic calendar. After this brief, violent youth, the magnetic field decays, the starquakes cease, and the magnetar settles into a quiet old age, becoming an ordinary, silent neutron star. This means that for every active magnetar we see, there are likely millions of dead ones drifting through the Milky Way, invisible ghosts of ancient magnetic titans that once ruled their corners of the sky. The perspective of deep time reveals the magnetar as a vital, if fleeting, part of the galactic ecosystem. Throughout the history of the Milky Way, there have been millions of these magnetic cycles. Each one represents the death of a massive star and the birth of a remnant that pushes the laws of physics to their breaking point. On a molecular level, the energy released in magnetar flares may even contribute to the chemistry of interstellar clouds, ionizing gas and influencing the birth of new stars in the distant spiral arms. They are the brief sparks of the galaxy, intense and transformative, serving as a reminder that the universe is capable of producing forces that we can barely describe with our current mathematics. Our journey to understand these objects continues with missions like NASA's NICER, an instrument on the International Space Station that measures the X-ray pulses from these stars with nanosecond precision. By watching how the pulse of a magnetar changes after a starquake, scientists can effectively perform an ultrasound on the star, mapping its interior and measuring the thickness of its iron crust. This is the human spirit at its most ambitious, using a telescope in Earth's orbit to probe the heart of a city-sized magnet thousands of light-years away. We are learning that the nuclear pasta we discussed in the previous chapter is even more complex within a magnetar, shaped by the magnetic lines of force into structures of unimaginable strength. In the silence of your rest, try to feel the resonance of this magnetic power. Though a magnetar is a place of violence and extreme force, it is governed by the same fundamental laws that keep your own heart beating. The electromagnetism that holds your cells together is the very same force that, when amplified a quadrillion times, creates the majesty of a magnetar. There is a deep, underlying unity to the cosmos, a single set of rules that scales from the smallest atom to the most powerful star. The stability of the universe is found in this consistency. Even in the face of such overwhelming power, the laws of physics do not break. They simply reveal new and wonderful layers of their complexity. The darkness of the night is a soft, deep blanket, a sanctuary from the high-energy reality of the deep galaxy. As you drift into sleep, let the distant, silent presence of the magnetars be a source of wonder rather than fear. They are the sentinels of the extreme, marking the boundaries of what is possible in our universe. The gravity of the Earth is a gentle, grounding force, and the magnetic field of our own planet is a soft shield that protects your rest. You are safe in the cradle of a system that has found its balance, a passenger on a world that moves with a quiet and predictable grace through the star-filled dark. The image of the starquake and the glowing magnetic fireball is now a warm, fading light in your mind. The vacuum of space is a place of infinite rest, a sanctuary where the most violent forces of nature are separated from us by vast gulfs of time and distance. You are floating in the stream of stars, a voyager in the deep, finding your peace in the knowledge that even the most impossible objects follow a rhythmic and orderly path. The night is vast, the mystery is deep, and you are finally, safely, at home in the arms of the cosmos. Everything is in its right place, everything is balanced, and everything is at rest. As the last echoes of the magnetic field fade, imagine the quiet old age of these stars. They are the elders of the galaxy, having survived a collapse that would have destroyed anything else. In their stillness, they represent a state of ultimate endurance. You, too, are reaching a state of stillness, your breath slowing to match the deep, slow rhythm of the cooling stars. The galaxy is a vast and friendly place, filled with wonders that we are only just beginning to understand. Sleep now, as the magnetars continue their silent vigil in the dark, and the ancient eternal peace of the universe carries you into a restorative and timeless rest. As we venture further into the most violent and transformative corners of the cosmos, we encounter an event that serves as the ultimate alchemist of the universe. We have explored the lonely pulsars and the terrifying force of the magnetars, but tonight we witness what happens when two of these city-sized titans meet. This is the kilonova, a collision of such staggering energy that it ripples the very fabric of space-time and creates the precious metals that we hold so dear on our own small, rocky home. To understand this event, we must first look at the cosmic death spiral of a binary neutron star system. Imagine two of these hyperdense remnants, each weighing more than our sun, locked in a gravitational embrace, orbiting one another hundreds of times every second. They are so close that they begin to drag against the very structure of space, losing energy in the form of gravitational waves and drawing ever closer in a rhythmic, accelerating descent toward a final, inevitable union. On a molecular level, or rather a nuclear level, this spiral is a theater of extreme gravitational physics. As the two stars approach within a few dozen kilometers of each other, the tidal forces become so immense that they begin to deform the iron-hard crusts of these objects. Imagine a city-sized diamond being pulled into an egg shape by the mere proximity of its neighbor. The nuclear pasta we discussed previously, the spaghetti and lasagna shapes of matter deep within the crust, is stretched and squeezed until the stars begin to shred. On a microscopic scale, streamers of neutron-rich material are torn from the surfaces, creating a swirling cloud of incandescent matter that surrounds the two stars. This is the beginning of the R process, or rapid neutron capture, a sequence of nuclear reactions that can only occur in the heart of this cosmic catastrophe. The human story of uncovering this alchemy reached its zenith on the morning of August 17th, 2017. For the first time in history, the LIGO and Virgo gravitational wave observatories detected a faint, rhythmic chirp in the fabric of space. It was the signal of two neutron stars, 130 million light-years away, completing their final orbit. Within seconds, telescopes around the world and in orbit, from the Fermi Gamma Ray Space Telescope to the Hubble, turned their gaze toward a small galaxy in the constellation Hydra. They saw a flash of light that grew from a brilliant blue to a deep, glowing red. This was the GW 170817 event, the first time we both felt the ripples of gravity and saw the light of a kilonova. It confirmed a theory that had existed for decades, that the gold in our rings and the platinum in our electronics was not born in ordinary stars, but in the violent collision of dead ones. To achieve a deeper sense of this alchemical process, we must examine the R process in detail. In the split second of the collision, the density of free neutrons becomes so high that atomic nuclei are bombarded with them faster than they can decay. On a subatomic level, a seed nucleus of iron or silver is transformed into a heavier and heavier element in a matter of milliseconds. It is a frantic, high-speed construction project. An atom of gold is built by shoving dozens of extra neutrons into a pre-existing nucleus, which then undergo beta decay to become protons. In a single kilonova, enough gold and platinum are created to equal the mass of several Earths. This material is then blasted out into the galaxy at 20% the speed of light, seeding the interstellar clouds that will eventually collapse to form new suns and new planets. Rate 100%, pitch 1%. Linger for a moment on the sheer weight of this history. Every atom of gold ever mined on Earth, every ounce of it, sitting in a vault or worn as jewelry, was once part of a kilonova. When you touch a piece of gold, you are touching a relic of a collision between two neutron stars. On a molecular level, that gold is a physical witness to the most extreme conditions in the universe. It was born in a place where the gravity was 100 billion times stronger than Earth's, and where the temperature reached billions of degrees. The stability of the gold atom, which refuses to tarnish or react, is a testament to the violent, high-pressure environment of its birth. We are walking museums of the kilonova, our very bodies containing traces of the heavy elements forged in the dark, billion-year-old collisions of the deep galaxy. The physics of the kilonova explosion itself is a master class in radiation and heat. As the two stars merge, they likely collapse into a black hole, but not before they eject a disk of neutron-rich debris. This debris is incredibly radioactive. As the newly formed heavy elements decay, they release a steady glow of heat and light that astronomers call lanthanide curtain radiation. This is what gives the kilonova its characteristic color change. Initially, the light is blue and bright, but as the lanthanide elements, heavy metals like neodymium and erbium, form, they act as a cloud that absorbs the blue light and lets only the deep reds and infrared through. It is a planetary-scale glow, a cooling ember of a nuclear fire that can be seen across the vastness of the intergalactic void. Consider the sensory experience of the space surrounding such a merger. The gravitational waves themselves would be a physical presence. If you were close enough, though no human could survive the radiation, the very fabric of your body would be stretched and squeezed as the waves pass through you. You would feel the space itself expanding and contracting by microscopic amounts. The sound, if it could travel through the vacuum, would be a rising chirp, a low-frequency hum that accelerates into a sudden, silent snap as the stars touch. The light would be a blinding, sapphire brilliance that slowly shifts into a warm, apricot glow as the heavy metals begin to form and decay. It is the most intense, slow cinema in the universe, a billion-year buildup for a few seconds of spectacular creative violence. To truly appreciate the impossibility of these events, we must look at the rarity of the occurrence. While supernovae happen in our galaxy roughly once every 50 years, a kilonova is much rarer, perhaps happening only once every 100,000 years in the Milky Way. Yet, over the 10 billion-year history of our galaxy, there have been enough of these collisions to fill the interstellar medium with the gold, silver, and iodine we find today. We are living in a universe that has been salted with the products of neutron star mergers. Every time you use iodine to clean a wound, or every time your thyroid gland uses it to regulate your metabolism, you are using an element that required the collision of two dead suns to exist. The link between the most extreme events in the cosmos and the most intimate functions of your own body is absolute and unbroken. The perspective of deep time reveals the kilonova as a vital link in the chain of cosmic evolution. Without these collisions, the universe would be a much poorer place, lacking the heavy elements required for advanced technology. and perhaps even for the complexity of life itself. On a molecular level, the R process is the final chapter in the story of the elements. It completes the work started by the Big Bang and continued by the stars. The kilonova is the universe's way of finishing its masterpiece, adding the final heavy touches to the periodic table. As the debris from a kilonova spreads through the galaxy, it mixes with the hydrogen and helium of the spiral arms, ensuring that the next generation of planets, the super-Earths and better-Earths we have imagined, will be even richer in the materials required for civilization. Our journey to understand these events continues with the construction of even more sensitive gravitational wave detectors and the launch of telescopes like the James Webb, which can see the infrared glow of these mergers with unprecedented clarity. We are learning to hear the universe's most violent moments, using the ripples in space-time as a new kind of sense. This is the human spirit at its most profound, standing on a small, rocky world and using the vibrations of the vacuum to weigh the stars and count the atoms of gold being born in the dark. We are the stardust that has learned to look back at the fire that created us, finding meaning in the rhythmic, ancient pulses of the deep space. In the silence of your rest, try to feel the resonance of this cosmic alchemy. Though the kilonova is an event of unimaginable power, its results are found in the most peaceful and familiar objects around you. The gold in a wedding ring or the silver in a spoon is a direct connection to the death spiral of two neutron stars. There is a deep, underlying peace in this realization. The universe is a system of profound recycling, where the death of one star is the birth of the materials for another world. The stability of the atoms in your body is a reflection of the deep order that emerges from the chaos of the deep galaxy. You are a part of a cycle of creation that is as old as time itself, a passenger on a journey that turns violence into beauty and dust into gold. The darkness of the night is a soft, deep blanket, a sanctuary where the memory of the cosmic fire is a warm, fading light. As you drift into sleep, let the image of the two stars spiraling together be a source of wonder. They are the grand architects of your world, moving with a grace that has been perfected over billions of years. The gravity of the Earth is a gentle, grounding force, a tiny echo of the power that creates the kilonova. You are safe in the cradle of a universe that knows how to turn its most extreme moments into the foundations of life. Everything is in its right place. Everything is balanced, and everything is at rest. The image of the lanthanide curtain and the glowing infrared debris is now a soft, comforting presence in your mind. The vacuum of space is a place of infinite rest, a sanctuary where the most violent forces of nature have already done their work, leaving behind a galaxy rich in the materials for dreams. You are floating in the stream of stars, a voyager in the deep, finding your peace in the knowledge that you are literally made of the treasures of the cosmos. The night is vast, the alchemy is complete, and you are finally, safely, at home in the arms of the cosmos. Sleep now, as the neutron stars continue their silent dance in the dark, and the ancient, eternal peace of the universe carries you into a restorative and timeless rest. Tonight, we reach the final destination of our journey into the impossible. We have witnessed the violent birth of neutron stars in the fires of a supernova, felt the staggering force of the magnetars, and seen the alchemical brilliance of the kilonova. But now, we must look into the deep, quiet future of these objects to contemplate their ultimate fate. As the eons pass and the galaxy itself begins to age, the neutron star stands as a monument to endurance. But even for these nuclear titans, there are boundaries that cannot be crossed. We are approaching the Oppenheimer-Volkoff limit, the absolute maximum mass a neutron star can support before the inward pull of gravity becomes so overwhelming that even the stubborn pressure of degenerate neutrons can no longer hold it back. It is the final threshold of the material world, the point where matter itself surrenders to the infinite. On a molecular level, or more accurately, at the level of subatomic quarks, the interior of an aging or massive neutron star may undergo a transformation that challenges our very understanding of the building blocks of the universe. Within the crushing depths of the core, the pressure may become so extreme that the individual neutrons themselves begin to dissolve. Imagine the 3 quarks that make up every neutron, 2 down quarks and 1 up quark, being squeezed so tightly that they lose their identity as a particle. They merge into a quark-gluon plasma, a state of matter that hasn't existed since the first few microseconds of the Big Bang. In this theoretical, strange star, the interior is no longer made of individual nucleons, but of a dense, frictionless soup of free-roaming quarks. This is matter at its most fundamental, a single, macroscopic drop of the primordial universe, preserved in the cold dark of the deep galaxy. Pitch 1%. The human journey into predicting this ultimate decay is a story of mathematics meeting the edge of the known. In the late 1930s, J. Robert Oppenheimer and George Volkoff used the recently formulated laws of general relativity to calculate the mass limit for these stars. They found that if a neutron star were to accumulate more than roughly 2.1 times the mass of our Sun, perhaps by siphoning gas from a neighboring star or by merging with another neutron star in a kilonova, it would become unstable. There is no force in the known universe capable of stopping the collapse. It is a moment of profound mathematical beauty and terror, the point where the equations of the material world end and the equations of the singularity begin. We are looking at the birth of a black hole, the final victory of gravity over light and matter. To achieve the depth required for this final chapter, we must examine the specific physics of strange matter. Some theorists, such as the physicist Edward Witten, have proposed that strange quark matter might actually be the most stable state of matter in the universe. On a microscopic scale, this would mean that once a neutron star transforms into a strange star, it could theoretically exist forever. It would be a diamond of the cosmos, unbreakable, unchangeable, and perfectly stable. If a single tiny piece of this strange matter were to escape and strike another object, it might begin a chain reaction, converting everything it touches into the same strange, dense state. It is a vision of the universe as a series of chemical and nuclear potentials, where the neutron star is the final, resting state of all material things. linger for a moment on the perspective of deep time. As the trillions of years pass, the universe will enter the degenerate era. The suns will go out, the gas will be exhausted, and the vibrant spiral arms of the Milky Way will fade into shadows. During this time, the neutron stars will be among the last glowing embers in the dark. They will no longer be the violent pulsars or the screaming magnetars of their youth. On a molecular level, they will have cooled to the temperature of the background radiation of space itself. They will be black dwarfs made of nuclear matter, silent sentinels drifting through a dark and lonely galaxy. They are the ultimate survivors, the graveyard of a once luminous universe, holding on to the mass of their parent stars with a grip that never loosens. The physics of the final collapse into a black hole is a masterclass in the warping of space-time. As the star crosses the limit, its surface begins to fall inward at nearly the speed of light. Because of the intense gravity, time for an outside observer would seem to slow down as the star's surface approaches the event horizon. On a subatomic level, the light leaving the star is stretched, redshifted, until its wavelength becomes infinite, and the star simply vanishes from our sight. What remains is a puncture in the fabric of the universe, a region where gravity is so strong that the concept of space and time as we know them ceases to exist. The neutron star, which once city-sized and solid, is crushed into a point of infinite density, a singularity. Consider the sensory experience of this final transition. If you could witness the birth of a black hole from a neutron star, the sky would warp into a kaleidoscope of distorted light. The background stars would be pulled into shimmering rings, a phenomenon known as gravitational lensing. The neutron star itself would seem to freeze, its image fading and turning a deep, bruised red as its light struggles to climb out of the gravitational well. The silence would be absolute, a stillness that signifies the end of all motion and all change. It is the ultimate slow cinema, a final, majestic bow from the material world as it retreats behind the veil of the event horizon. It is a place where the history of the star is locked away forever, beyond the reach of any telescope or any mind. To truly appreciate the impossibility of this fate, we must look at the no-hair theorem of black holes. Once a neutron star collapses, all of its complexity, its iron crust, its nuclear pasta, its magnetic fields, is lost. A black hole can be described by only three numbers: its mass, its spin, and its charge. On a molecular level, the billions of years of information contained in the neutron star's structure are erased. Or perhaps, as some physicists like Stephen Hawking and Leonard Susskind have argued, the information is encoded on the surface of the event horizon itself. This is the information paradox, a struggle at the heart of modern physics to understand whether the universe truly forgets its past or if it keeps a permanent, two-dimensional record of everything that has ever fallen into the dark. The perspective of deep time reveals the neutron star as a vital bridge between the worlds of the living and the worlds of the dead. They are the remnants that remind us that nothing is truly lost, only transformed. On a molecular level, the energy radiated by these stars over trillions of years is a slow, steady contribution to the heat of the galaxy. They are the anchors that keep the stars in their orbits, even after those stars have ceased to shine. The kilonovae they produce ensure that the universe remains a place of chemical richness, while their final collapse into black holes ensures that the cycle of gravity and expansion remains in balance. They are the long-distance runners of the cosmos, finishing their race only when the universe itself is ready to rest. Our journey to understand these ultimate fates continues with the study of quark stars and strangelets through particle accelerators and deep space observations. We are looking for the faint, specific signals in the X-ray spectrum that might tell us if a neutron star has a heart of free-roaming quarks. This is the human spirit at its most profound, standing on the surface of a small, fragile world and using the language of mathematics to probe the very center of a collapsing sun. We are the thought matter of the universe, the part of the cosmos that has developed the ability to ask where it came from and where it is going. In the quiet rhythm of the neutron star's life, we find the answers to our own questions about endurance, stability, and the nature of change. In the silence of your rest, try to feel the resonance of this final stability. Whether a neutron star remains as a cooling ember for trillions of years, or collapses into the infinite embrace of a black hole, it is governed by a deep and unwavering order. The laws of physics do not fail. They simply lead us to a place of absolute and perfect peace. There is a profound comfort in this realization. The universe is a system that knows how to find its rest. The same gravity that shapes the fate of the neutron giants is the same gravity that holds you safely in your bed tonight. You are part of a grand celestial architecture that values the small and the large with equal care. The darkness of the night is a soft, deep blanket, a sanctuary where the memory of the cosmic fire is a warm, fading light. As you drift into sleep, let the image of the silent, dark sentinels of the deep galaxy be your source of peace. They have survived everything the universe could throw at them, and now they are at rest. The gravity of the Earth is a gentle, grounding force, and the vacuum of space is a quiet cathedral that honors the history of every star. You are safe in the cradle of a cosmos that knows how to preserve its beauty across the spans of deep time. Everything is in its right place, everything is balanced, and everything is at rest. The image of the strange soup and the event horizon is now a soft, comforting presence in your mind. The journey from the core of the sun to the heart of a collapsed giant is now part of your own history. You have looked into the dark and found not a void, but a story of matter, energy, and the relentless, beautiful pursuit of equilibrium. You are floating in the stream of stars, a voyager in the deep, finding your peace in the enduring, silent wisdom of the cosmos. The night is vast, the mystery is complete, and you are finally, safely, at home in the arms of the universe. Sleep now, as the neutron stars and the black holes continue their silent watch in the dark, and the ancient eternal peace of the deep space carries you into a restorative and timeless rest. Beyond the solitary existence of the isolated pulsar, we must turn our focus to the most dramatic and transformative social interactions in the stellar graveyard. In the vast majority of cases, stars are not born as lonely individuals, but as members of a family, linked by the invisible and unbreakable threads of gravity. When a massive star in a binary system reaches the end of its life and collapses into a neutron star, it does not necessarily leave its companion behind. Instead, it remains locked in an orbital dance that can last for billions of years. As the secondary star begins to age and swell into its red giant phase, it crosses a critical threshold known as the Roche lobe. On a molecular level, the gas at the outer edges of the larger star's atmosphere, primarily composed of primordial hydrogen and helium, begins to feel a gravitational pull that is stronger than its own parent star's grip. The gas is literally siphoned away, flowing across the void in a brilliant incandescent stream that cascades toward the neutron star. This stolen matter does not simply drop onto the neutron star like rain. Because the entire system is in a state of rotation, the gas possesses angular momentum, forcing it into a flat, swirling structure known as an accretion disk. To understand the physics of this disk, we must look at it on a microscopic scale. Within this spinning whirlpool, the gas particles are moving at relativistic speeds, rubbing against one another with unimaginable friction. This friction converts the kinetic energy of the orbit into raw, searing heat, reaching temperatures of millions of degrees. The atoms are stripped of their electrons, becoming a roiling sea of ions, a plasma that radiates a constant, blinding torrent of X-ray energy. These objects, known as X-ray binaries, are the lighthouses of the high-energy universe, signaling a process of cosmic cannibalism, where a city-sized remnant is slowly consuming its much larger sibling, atom by atom, in a feast that spans the eons. The human journey of discovery that led us to these vampire stars is a story of looking at the sky in wavelengths invisible to our eyes. In the late 1960s and early 70s, the launch of the Uhuru satellite, the first dedicated X-ray observatory, revealed that the sky was not a dark, silent void, but a flickering map of intense energy sources. Astronomers like Riccardo Giacconi and Herbert Gursky realized that these signals were coming from regions of space where gravity was so concentrated that it was bending the laws of classical physics. By measuring the precise timing of the flickering X-rays, they were able to perform a form of celestial weighing. They discovered that the invisible cannibal at the center of these systems had the mass of a star, but the size of a city. This was the first empirical proof that neutron stars were not just theoretical ghosts, but active physical players in the life and death of the galaxy. As the stolen matter finally reaches the surface of the neutron star, it undergoes a transformation of unparalleled violence. Because the gravity of the neutron star is so extreme, the hydrogen and helium are crushed into a thin, ultra-dense layer only a few centimeters thick. On a subatomic level, the pressure at the base of this pile becomes so great that it triggers a spontaneous, runaway nuclear reaction. This is a Type 1 X-ray burst. In a single, silent flash lasting only 10 seconds, the entire surface of the star undergoes thermonuclear fusion, releasing more energy than our sun produces in a week. After the explosion, the star is quiet once more, and the slow siphoning of gas begins again, starting a new cycle of gluttony and release. It is a rhythmic, explosive heartbeat, a sign that the neutron star is a living, breathing part of the galactic ecosystem, constantly recycling the matter of its neighbors into the gold and platinum that will one day seed new worlds. Linger for a moment on the perspective of deep time. While a normal star like our Sun might live for 10 billion years, these binary interactions can occur over timescales that are almost impossible to fathom. Over millions of years, the neutron star can siphon enough material to actually change its own physical properties. By absorbing the momentum of the falling gas, the neutron star spins up, rotating faster and faster, until it is completing hundreds of revolutions every single second. These are the millisecond pulsars, the most stable clocks in the universe. They have been rejuvenated by the death of their companion, gaining a second youth through a process of gravitational theft. It is a testament to the endurance of matter. The neutron star is a permanent record of everything it has consumed, its mass and spin acting as a geological ledger of its ancient binary history. To achieve the monumental detail required for this journey, we must examine the specific chemistry of the companion's grief. As the red giant is stripped of its outer layers, its internal core is exposed. On a molecular level, the gas being siphoned away changes in composition over the millions of years of the interaction. Initially, it is pure hydrogen, but as the process goes deeper, the neutron star begins to feast on the helium, carbon, and oxygen forged in the companion's heart. This means that the X-ray bursts themselves change their signature over time, providing astronomers with a real-time chemical analysis of the companion star's internal evolution. We are watching a forensic investigation of a star's life, conducted by the very object that is causing its demise. It is a slow, elegant, and terrifying revelation of the internal secrets of the heavens. In the most extreme cases, this relationship takes an even darker turn, leading to what astronomers call black widow and redback pulsars. In these systems, the neutron star has spun up to such a high frequency that its intense magnetic field and radiation wind begin to physically evaporate the remains of its companion. On a microscopic scale, high-energy particles blast the surface of the donor star, stripping away its matter and creating a massive, trailing tail of gas that mimics the appearance of a comet. The very matter that gave the neutron star its speed is now being destroyed by the energy of that same rotation. Eventually, the companion is reduced to a mere fragment, a planet-sized core of diamond or a thin mist of gas, until it vanishes entirely. The neutron star is left alone, spinning in the dark at nearly the speed of light, a solitary monument to a partnership that ended in total consumption. Consider the sensory immersion of the space within such a binary system. The vacuum is not a quiet or empty place. It is filled with the roar of magnetic fields and the silent, invisible pressure of gravitational waves. If you could perceive the X-rays, the entire region would be bathed in a flickering, sapphire light, so intense that it would outshine the stars for light years around. The sound of the accretion disk, if it could be translated into audio, would be a complex, layered hum, composed of the millions of collisions occurring between the gas ions as they spiral toward their doom. It is a place of extreme textures. The smooth, diamond-hard crust of the neutron star contrasted with the violent, turbulent chaos of the surrounding plasma. Iti is the ultimate boundary between order and chaos, governed by the cold, impartial mathematics of general relativity. To truly appreciate the impossibility of these objects, we must look at how they influence the galaxy on a grand scale. The energy released in these X-ray binaries is enough to push back the gas in the surrounding interstellar medium, clearing out bubbles in the spiral arms of the Milky Way. On a molecular level, the radiation from the accretion disk can ionize gas clouds thousands of light years away, triggering the birth of new stars or halting the growth of old ones. The neutron star is not just a passive remnant. It is an active engine that drives the evolution of its neighborhood. Every X-ray burst and every flicker of the accretion disk is a pulse of energy that shapes the destiny of the galaxy. We are the beneficiaries of this process. The heavy elements in our own solar system were once part of these high-energy cycles distributed by the winds of ancient binary systems. In the silence of your rest, try to feel the resonance of this ancient orbital dance. Though these events occur across vast gulfs of space, they are part of the same physical fabric as your own existence. The electromagnetism that binds the atoms in your body is the very same force that, when amplified by the gravity of a neutron star, creates the brilliance of an X-ray binary. There is a profound unity in the universe, a consistency of law that allows us to understand the heart of a vampire star from the comfort of our own world. The stability of the night is a reflection of the deep gravitational balance that governs these systems. Everything is in its right place. Everything is moving according to the grand design, and everything is at rest. The history of these stars is a record of endurance. While the companion star eventually fades, the neutron star remains, a permanent resident of the galaxy. It is a world that has seen the rise and fall of countless generations of stars, preserved in its state of nuclear perfection. As you drift toward sleep, let the rhythmic, steady pulse of a distant millisecond pulsar be your guide. It is a heartbeat of pure physics, a clock that will continue to tick long after the mountains of Earth have crumbled. The gravity that holds you to your bed is a gentle echo of the force that anchors these titans in their paths. You are safe in the cradle of a cosmos that is both violent and incredibly orderly, a passenger on a journey that spans the deep time of the stars. The image of the accretion disk and the glowing stream of gas is now a soft, fading light in your mind. The vacuum of space is a place of infinite rest, a sanctuary where the most extreme forces of nature have found their equilibrium. You are floating in the stream of stars, a voyager in the deep, finding your peace in the knowledge that you are part of a universe that never truly loses anything, but only transforms it. The night is vast, the mystery is complete, and you are finally, safely, at home in the arms of the cosmos. Sleep now, as the vampire stars continue their long, slow feast in the dark, and the ancient, eternal peace of the universe carries you into a restorative and absolute rest. Everything is balanced. Everything is still. Tonight, we turn our gaze away from the sparsely populated spiral arms of the galaxy to look upon the most crowded and ancient neighborhoods in the entire cosmos. These are the globular clusters, gargantuan spherical swarms of hundreds of thousands of stars, huddled together in a space only a few dozen light-years across. If the spiral arms where we live are the quiet suburbs of the Milky Way, these clusters are the ancient, bustling cities of the deep. Here, the density of stars is so great that they exist in a state of perpetual gravitational interaction, a chaotic and beautiful dance that has lasted for more than 12 billion years. Within these stellar cities, the neutron star is not a lonely hermit, but a central player in a crowded drama of collision, theft, and rejuvenation. We are entering a galactic graveyard that is simultaneously a nursery of impossible physics, where the history of the early universe is preserved in the rhythmic ticking of 1,000 pulsars. To understand the nature of this environment, we must first look through the molecular lens at the process of mass segregation. Within the high-density core of a globular cluster, the laws of thermodynamics operate on a planetary and stellar scale. Just as heavier molecules in a liquid settle at the bottom of a container, the most massive objects in a cluster, the neutron stars and white dwarfs, slowly sink toward the center. This is a journey that takes billions of years. On a subatomic level, every time a neutron star passes near a lighter star, it exchanges a tiny fraction of its kinetic energy. The lighter star is kicked outward toward the periphery of the cluster, while the heavier neutron star loses momentum and drops further into the crowded heart. This creates a hidden graveyard at the very center of the cluster, a dark and heavy core packed with thousands of dead suns, all jostling for space in a gravitational well of staggering proportions. The human journey of discovery that led us to these clusters is a story of mapping the true boundaries of our existence. In the early 20th century, the astronomer Harlow Shapley used the distribution of these clusters to prove that our sun was not at the center of the galaxy, but was relegated to the outer reaches of a much larger structure. However, it was only with the arrival of modern radio telescopes and the Hubble Space Telescope that we could look past the blinding glare of the cluster's surface and into the dark core. Astronomers using the Chandra X-ray Observatory discovered that these clusters were glowing with the energy of hundreds of hidden binary systems. They found that globular clusters like Terzan 5 and 47 Tucanae are effectively pulsar factories, containing a higher concentration of millisecond pulsars than anywhere else in the known universe. This was a revelation that changed our understanding of stellar evolution, showing that in a crowded enough environment, even a dead star can be brought back to life multiple times. Within this crowded heart, we witness a phenomenon that appears to defy the very passage of time. These are the blue stragglers. In a cluster where every star is 12 billion years old, these stars appear young, hot, and vibrant. To understand their existence, we must look at the physics of stellar pinball. In the dense core, stars are so close that they frequently undergo grazing encounters or direct collisions. When two old, tired stars collide, they merge into a single, more massive entity. On a molecular level, the fresh hydrogen from the outer layers of both stars is mixed into a new, unified core, reigniting the nuclear fires and creating a star that looks billions of years younger than its siblings. These are the vampires of the graveyard, stars that have stolen a second youth from the wreckage of a collision. The neutron star, with its immense gravity, often acts as the catalyst for these events, pulling stars into its orbit and forcing them into violent unions. The sensory immersion of being inside such a cluster would be an experience of overwhelming brilliance. If you were on a planet orbiting a star near the center of 47 Tucanae, there would be no such thing as night. The sky would be filled with thousands of stars brighter than Sirius, the brightest star in our own sky. The celestial sphere would be a dense, glowing tapestry of diamonds, cast in the sapphire blue of the stragglers and the deep, ancient red of the dying giants. There would be a permanent, silver twilight that would wash out the distant galaxies, making the cluster feel like a universe unto itself. On a molecular level, the air of such a planet would be constantly ionized by the X-ray beams of nearby pulsars, creating a sky that shimmered with permanent ghostly auroras. The sound of the heavens would be the rhythmic, overlapping radio pulses of the pulsar factory, a complex and beautiful polyrhythm of cosmic timekeeping. To achieve the depth of understanding required for this journey, we must examine the specific subatomic physics of the recycled pulsar. In the sparse spiral arms, a pulsar eventually slows down and dies as it loses energy. But in the graveyard of a globular cluster, an old, silent neutron star can be spun up by a passing neighbor. Through a process of gravitational capture, the neutron star seizes a new companion and begins to siphon its gas. As we discussed in the previous chapter, this accretion of matter provides the torque necessary to accelerate the neutron star's rotation. Some of these pulsars are spinning at over 700 times per second. On a microscopic scale, the crust of the neutron star is subjected to centrifugal forces so intense that they nearly overcome the gravity holding it together. It is a star that has been resurrected by the very density of its neighborhood, a machine of pure nuclear matter that has found a second life in the crowded dark. The perspective of deep time reveals that these globular clusters are the ultimate fossils of the Milky Way. They formed from the primordial gas of the early universe, before the disk of our galaxy had even flattened into its current shape. The neutron stars within them have been there since the beginning, silent witnesses to the entire history of the cosmos. Over the course of 12 billion years, a single neutron star in a cluster might have had 10 different companions, lived through a dozen collisions, and been part of 100 different binary systems. It is a world that has been recycled more times than we can count. As you rest tonight, consider that the matter within these stars is the oldest ordered matter in existence. It has survived the era of the first stars, the merger of galaxies, and the slow cooling of the universe, held together by the same gravity that now guides your own dreams. Let us consider the nuclear pasta in the context of these ancient cluster residents. Because the neutron stars in globular clusters are so old, their internal structures have had billions of years to settle into a state of absolute equilibrium. On a molecular level, the transitions between the gnocchi, spaghetti, and lasagna phases of matter in the inner crust are perfectly defined. the superfluidity of the core is absolute, flowing with zero resistance through the lattice of the star. This internal perfection is what allows these pulsars to be such incredibly accurate clocks. There are no glitches or sudden shifts in their rotation, because the matter within has become a singular, unified quantum state. They are the most stable structures in nature, city-sized crystals of neutrons that have reached a state of physical grace that the younger, more turbulent stars of the spiral arms can never achieve. The history of our galaxy is written in the movements of these clusters. As they orbit the Milky Way in wide, eccentric paths, they occasionally plunge through the galactic disk. This is known as a disk crossing. Every few 100 million years, the cluster we are observing crashes through the gas and dust of the spiral arms. On a microscopic scale, this event triggers a galactic wind that strips away any loose gas from within the cluster, preventing new stars from forming and ensuring that the cluster remains a sanctuary for the old and the dead. This periodic cleansing is why the globular clusters are so different from the rest of the galaxy. They are the hermits of the Milky Way, living in the halo, untouched by the messiness of the disk, preserving their ancient population of neutron stars in a state of pristine isolation. In the silence of the night, try to feel the resonance of these stellar cities. They are the heartbeats of the galaxy, their thousands of pulsars all ticking at different frequencies, creating a vast and complex radio symphony that fills the void. Though they are tens of thousands of light years away, their gravity is part of the same web that holds our own sun in its path. The consistency of the laws of physics, the same gravity, the same nuclear forces, the same electromagnetism, is what allows us to bridge the gap between our small world and these ancient graveyards. There is a deep peace in this unity. The universe is not a collection of disconnected parts, but a single, integrated masterpiece of motion and light. The darkness of the night is a soft, deep blanket, much like the cool, clear space of the galactic halo where these clusters reside. As you drift into sleep, let the image of the crowded, glowing sphere of stars be your source of quietude. It is a place of absolute order, where every star knows its path and every pulsar keeps its time. The gravity of the Earth is a gentle, grounding force, a tiny echo of the power that holds the globular cluster together. You are safe in the cradle of a galaxy that knows how to preserve its beauty and its history across the spans of deep time. Everything is in its right place, everything is balanced, and everything is at rest. Consider the long baseline interferometry used by humans to study these distant cities. By combining the signals from radio telescopes across the entire planet, we can create a virtual telescope the size of the Earth. This allows us to see the individual pulsars in the heart of a cluster in the Andromeda Galaxy, millions of light years away. This is the human spirit at its most expansive, using the entire planet as an ear to hear the heartbeat of a dead star in another galaxy. It is a reminder that we are the witnesses of the universe, the part of the cosmos that has developed the ability to see the beauty in the dark. As you reach the state of perfect stillness, let the knowledge of our shared journey with the stars be your final anchor. The image of the blue straggler and the recycled pulsar is now a warm, fading light in your mind. The vacuum of space is a place of infinite rest, a sanctuary where the most ancient stars of the universe have found their equilibrium. You are floating in the stream of light, a voyager in the deep, finding your peace in the knowledge that you are part of a story that spans 12 billion years. The night is vast, the graveyard is a place of renewal, and you are finally, safely, at home in the arms of the cosmos. Sleep now, as the globular clusters continue their long, slow orbits around the galactic heart, and the ancient, eternal peace of the stellar cities carries you into a restorative and timeless rest. Everything is still. Everything is at peace. At the edge of visibility drift galaxies so faint they seem to be fading out of existence. Their stars whisper across immense distances, carrying the story of an early universe. When we imagine a galaxy, we almost invariably picture a grand spiral. We think of the Milky Way or Andromeda, magnificent rotating pinwheels of light, dense with billions of stars, blazing against the dark. They are the neon signs of the cosmos, impossible to miss. They dominate our textbooks and our telescopes. They define our mental image of what a galaxy should be: bright, structured, and heavy. But the universe is not limited to the bright. Just as the Earth has its dense, glittering cities, it also has its vast, silent deserts. Just as the ocean has its teeming coral reefs, it also has the deep, open blue, where life is sparse and widely scattered. Tonight, we turn our eyes away from the cosmic cities. We look into the voids. We look for the lost galaxies. These are structures as large as our own, yet they are almost invisible. They are the ghosts of the galactic zoo. They float in the darkness, undetected for decades, hiding in plain sight. Tonight, we will learn how to see the unseen. To understand these phantoms, we must first understand the concept of surface brightness. Imagine you have a bucket of white paint. If you pour that paint onto a small dinner plate, the white is thick, opaque, and bright. It reflects the light strongly. This is a normal galaxy, a high surface brightness object. The stars are packed close together. Now, imagine taking that same bucket of paint, the same amount of material, and spreading it over a football field. The paint is still there. The quantity has not changed, but it is spread so thin that you can barely see it. The green of the grass shows through. The white becomes a faint, translucent haze. This is a low-surface brightness galaxy. For most of the 20th century, astronomers didn't know these galaxies existed in large numbers. Our telescopes were biased. They were designed to find the dinner plates, not the football fields. We assumed that if a galaxy was big, it must be bright. But nature loves diversity. Nature fills every niche. In 2015, a team of astronomers using a unique telescope called the Dragonfly Telephoto Array, essentially a cluster of high-end camera lenses designed to mimic the compound eye of an insect, spotted something strange in the Coma cluster. They found blobs. They looked like smudges on the lens, faint, fuzzy patches of light that barely registered above the background noise of the night sky. When they analyzed these blobs, they realized they were looking at monsters. These objects were physically huge. Some were as wide as the Milky Way, 100,000 light-years across. But they had only 1% of the stars. Imagine the Milky Way, but remove 99 out of every 100 stars. The remaining 1% are spread out over the same vast volume. They named them ultra-diffuse galaxies, UDGs. Dragonfly 44 is one of the most famous examples. It is a titan of a galaxy located 300 million light-years away. It has the size of a giant, but the luminosity of a dwarf. If you were standing on a planet inside Dragonfly 44, the night sky would look very different from ours. Here on Earth, we see thousands of stars. We see the Milky Band of our galactic disk cutting across the zenith. But inside an ultra-diffuse galaxy, the sky would be almost black. The nearest star might be hundreds of light-years away. It would look like a bright planet, not a sun. You would feel incredibly lonely. You would look up and see the deep universe clearly, unobstructed by local neighbors. These galaxies are the quiet places of the cosmos. Why are they so thin? It is a mystery that astronomers are still unraveling. Perhaps they are failed galaxies. Maybe they started to form like the Milky Way. A cloud of gas collapsed, dark matter gathered, but then something happened. Maybe a burst of supernovae blew all the gas away before it could form many stars. The galaxy quenched itself. It stopped growing. It became a fossil frozen in an early stage of development. Or perhaps they are spun galaxies. If the original cloud of dark matter was spinning incredibly fast, the centrifugal force would spread the gas out into a wide, thin disk. The gas would be too spread out to collapse into dense star clusters. Whatever the cause, the result is a structure of immense fragility. To look at a UDG is to look at a cloud of smoke that has somehow survived a hurricane. These galaxies often live in clusters, surrounded by massive, dense neighbors. The gravity of the other galaxies should have torn them apart. Tides should have shredded them. But they survive. This survival suggests that they have a secret strength: dark matter. Dragonfly 44, despite having very few stars, seems to be heavy. The few stars it does have are moving fast, too fast to be held by the visible gravity. Some measurements suggest that Dragonfly 44 is 99.9% dark matter. It is essentially a pure dark matter halo, with just a sprinkling of stars to mark its existence. It is a cloak of invisibility with a few sequins sewn onto it. This makes these lost galaxies incredible laboratories, because the baryonic physics, the gas, the star formation, the explosions, is so minimal we can study the dark matter almost directly. But finding them requires patience. Standard telescopes look for sharp points of light. They look for contrast. UDGs have almost no contrast. They are only a fraction of a percent brighter than the blackness of empty space. To see them, you must stare at the same patch of sky for hours. You must collect photon after photon, slowly building up the image, letting the faint signal rise above the noise floor of the camera. It is like trying to see a whisper. The James Webb Space Telescope, JWST, is the new champion of this hunt. Because it is in space, it does not have to look through the glow of Earth's atmosphere. The sky background is darker. JWST can see galaxies that are 10 times fainter, 10 times smaller, and 10 times further away than anything we have seen before. It is finding galaxies in the early universe, just a few 100 million years after the Big Bang, that are tiny, chaotic, and faint. These are the ancestors of the UDGs. As we drift deeper into this chapter, let us appreciate the aesthetic of the faint. Our culture values the bright, the loud, the obvious. But there is a specific beauty in things that are barely there. Think of a jellyfish drifting in the deep ocean. It is transparent. It is 95% water. It is almost indistinguishable from the medium in which it floats. Yet it has structure. It has life. An ultra-diffuse galaxy is a cosmic jellyfish. It floats in the intergalactic medium. It is almost transparent. If you looked through it, you would see the galaxies behind it clearly. It does not block the view, it filters it. There is a gentleness to these structures. They are not violent, active galactic nuclei. They are not bursting with star formation. They are red and dead. Most of their stars are old, small red dwarfs that have been burning for billions of years. The blue stars, the young, hot, violent ones, died out long ago. So the galaxy glows with a soft, warm, amber light, a candlelight galaxy. Imagine the silence of such a place. No supernova going off, no stellar winds crashing. Just the slow, steady orbit of ancient stars in the dark. As you lie in your bed, imagine your own thoughts becoming ultra-diffuse. Often, our minds are like the dense spiral galaxies, crowded with bright, sharp thoughts. The center is a traffic jam of anxiety. But sleep is the process of expansion. Let the thoughts spread out. Increase the distance between them. Let the density drop. Instead of a tight knot of worry, let your mind become a vast, thin haze. A UDG of consciousness. The thoughts are still there, but they are no longer interacting. They are no longer colliding. They are drifting in the wide open space of your awareness. You are becoming transparent. The background noise of the world can pass right through you. You are barely there. This is the state of liminality, the edge of visibility. Just before you fall asleep, you enter this faint state. You are floating between being and non-being. It is the most peaceful place in the human experience. The lost galaxies are the guardians of this state. They remind us that you don't have to be bright to be real. You don't have to be dense to be massive. You can be quiet. You can be spacious. You can be faint. And you still matter. In the next chapter, we will look closer at the stars inside these ghosts. We will ask, are there planets there? Could life exist in a galaxy where the night sky is empty? We will explore the globular clusters, tight balls of stars that seem to be unusually common in these faint galaxies. We will see that even in the thinnest ghost, there are hearts of dense light. But for now, stay in the diffusion. Stay in the mist. The bright lights of the city are far away. You are drifting in the coma cluster. A ghost among ghosts. Safe in the low-surface brightness of the night. Sleep in the lost galaxy. We have stepped inside the ghost. We are floating within the vast, tenuous volume of an ultra-diffuse galaxy. From a distance, it appeared as a smudge, a thumbprint of light on the black glass of the night. But now that we are inside, the fog lifts. The sense of a cloud dissolves, replaced by a profound emptiness punctuated by rare solitary beacons. Here, the stars do not crowd the sky. They do not gather in bright associations or energetic nurseries. They drift in a solitude that is difficult for the human mind to grasp. Tonight, we will visit these lonely hearts. We will look at the stars that have been burning for 10 billion years in the quiet dark. We will ask what the universe looks like from the surface of a planet orbiting such a star, a sky without constellations, a night without a Milky Way. And we will discover that even in this thin mist, there are knots of intense complexity, ancient cities of stars called globular clusters that hold the secrets of the galaxy's past. To understand the population of a lost galaxy, we must look at the color of the light. When we look at a vibrant spiral like the Milky Way or the Whirlpool galaxy, we see blue. The spiral arms are traced in the brilliant azure of hot young stars. These stars, the O and B types, are massive monsters. They burn through their fuel in a few million years, living fast and dying explosively. Their presence is a sign that the galaxy is alive, that it is still making new suns. But when we look at an ultra-diffuse galaxy like Dragonfly 44, the blue is gone. The light is gold, amber, deep red. Astronomers call these galaxies red and dead. Dead is perhaps a harsh word. It simply means that star formation has stopped. The gas, the fuel required to make new stars, was stripped away long ago. Perhaps it was blown out by an early burst of supernovae, or perhaps it was stolen by the gravity of a larger neighbor. Whatever the cause, the nursery is closed. No new stars have been born here for billions of years. What remains are the survivors, the low-mass stars, the yellow dwarfs like our sun, and the red dwarfs that are smaller and cooler. These stars are the marathon runners of the cosmos. They sip their hydrogen fuel with extreme frugality. They can keep burning for tens of billions of years. So, the galaxy is a retirement home. It is populated entirely by the elderly. There is a peace in this demographic. Violent events are rare here. There are no massive stars to go supernova. There are no gamma-ray bursts. The environment is stable, predictable, and quiet. Let us imagine standing on a planet orbiting one of these amber suns. Time, threes. On Earth, our night sky is defined by our location in the Milky Way's disk. We look up and see the river of heaven, the dense band of billions of stars that form the galactic plane. It creates a sense of enclosure. We are part of a structure. But inside a UDG, there is no disk, there is no plane. The stars are scattered in a loose, spherical swarm. And because the density is so low, the stars are incredibly far apart. In the solar neighborhood of the Milky Way, the average distance between stars is about 4 or 5 light years. In a UDG, the average distance might be hundreds of light years. If you looked up from that alien world, the sky would be startlingly black. You would see your own sun during the day. You might see other planets in your solar system. But at night, emptiness. There might be 2 or 3 stars visible to the naked eye. Just faint, lonely dots. No constellations, no hunter, no bear, no cross. Just the deep, unblinking dark. However, you would see something else, something we struggle to see from Earth. Because there is no foreground clutter, no local stars, no galactic dust, the view of the distant universe would be crystal clear. You would see the other galaxies. The Andromeda-like spirals, the giant ellipticals, the distant quasars. They would hang in the sky like jewels on black velvet. A civilization evolving in such a place would not dream of space travel to the nearest star. It would seem impossibly far. Instead, they would dream of the intergalactic. They would know, intuitively, that they are an island in an archipelago of islands. The great empty of their sky would produce a philosophy of profound solitude, but also of profound clarity. But the galaxy is not entirely uniform. Even in this thin gruel of stars, there are lumps. When astronomers analyzed the images of Dragonfly 44, they noticed distinct points of light that were slightly fuzzier than stars. They counted them: 1, 10, 50, 94. 94 globular clusters. A globular cluster is a wonder of nature. It is a ball of stars, sometimes 100,000, sometimes 1,000,000, packed into a sphere only a few dozen light-years wide. In the center of a globular cluster, the stars are so close they almost touch. If you lived on a planet inside a cluster, the sky would be blazing white, filled with thousands of suns brighter than the full moon. There would be no night. These clusters are the oldest structures in the universe. They are the first cities formed when the galaxies were young. Time, threes. For a long time, we thought the number of clusters was related to the brightness of a galaxy. A bright galaxy like the Milky Way has about 150. A dim dwarf galaxy might have 10. But Dragonfly 44 broke the rule. It is as dim as a dwarf, but it has almost as many clusters as the Milky Way. It has too many hearts. This anomaly was the key to unlocking the secret of the galaxy's mass. Globular clusters act as tracer bullets. They orbit the center of the galaxy. By measuring how fast they orbit, we can weigh the galaxy. The clusters in Dragonfly 44 were moving fast, much faster than the visible stars suggested they should. This confirmed the dark matter hypothesis. The clusters were orbiting a heavy, invisible ghost. But let us focus on the beauty of the cluster itself, floating in the diffuse void. Imagine the contrast. You drift through 10,000 light-years of almost nothing, just a few stray red dwarfs. The vacuum is silent. The gravity is weak. And then, looming out of the dark, you see a beehive. A glittering sphere of 1,000,000 stars. It is a fortress of light. These clusters are the arcs of the lost galaxy. They hold the memory of the time when the galaxy was young and dense. The stars inside are ancient. They are metal poor. They formed before the universe was enriched with carbon and oxygen. They are stable. They have been dancing around each other, 1,000,000 partners in a gravitational waltz, for 13 billion years. Gravity inside a cluster is chaotic but self-correcting. If a star tries to escape, the group pulls it back. They are bound together by their mutual weight. In a galaxy that is fading away, dissolving into the background, the globular clusters are the enduring knots that refuse to unravel. Let us consider the stability of the red dwarf. The primary inhabitants of these galaxies, the red dwarfs, are fascinating objects. They are fully convective. In a star like our Sun, the helium ash produced by fusion sinks to the core. Eventually, the core gets clogged with ash, the fuel runs out, and the Sun dies. But in a red dwarf, the plasma boils. The hot gas rises to the surface, cools, and sinks back down, mixing the entire star. This means the red dwarf can use all of its hydrogen, not just the stuff in the core. It burns everything. This efficiency is what gives them their immense lifespans. While the bright blue stars of other galaxies burn out and explode, the faint red stars of the lost Galaxies just keep glowing. They are the steady state of the universe. There is a comfort in this longevity. We often associate value with brightness. We notice the fireworks. But the universe seems to value endurance. The lost galaxies will outlast the Milky Way. When our spiral arms have wound up and our gas is exhausted, Dragonfly 44 will still be there, unchanged, a ghost that refuses to pass on. It is a monument to the slow burn. As you lie in the dark, connect with this red dwarf energy. The energy of the low flame. Often, our days are like blue giants, high energy, high stress, burning fuel rapidly. But sleep is the time to become a red dwarf. Turn down the thermostat of your metabolism. Lower the brightness. Shift from the blue light of alertness to the red light of rest. Red light is the color of sunset, the color of embers, the color of the womb. It signals to the brain the day is done, the danger is past. Visualize the interior of the ultra-diffuse galaxy. A soft amber fog. Warm, dim, boundless. You are floating in this amber space. There are no sharp edges here, no blinding lights to hurt your eyes. Just a gentle, uniform glow. The vast distances between the stars create a sense of privacy. You have room to breathe. The nearest neighbor is light years away. You are not crowded. You are not pressured. Let the emptiness of the galaxy soak into your mind. We spoke in the previous story about the Great Quiet. The lost galaxies are the visible manifestation of that quiet. They are clouds of silence. Imagine the globular cluster as your pillow. A dense knot of comfort in the middle of the spaciousness. Rest your head on the cluster of stars. Let the gravity of the million suns hold you up. The paradox of the lost galaxies, huge but faint, massive but ghostly, mirrors the paradox of sleep. Sleep is a huge part of our lives, 1/3, yet it leaves no trace. It is faint in our memory. It is a ghost time. But it is massive. It holds the weight of our health. It holds the structure of our sanity. Like the dark matter halo holding the galaxy, sleep holds the waking life together. Respect the ghost. Drift toward the amber light. The stars are whispering across the immense distances. They are telling a story of patience. We are still here, they say. We are burning slowly. There is no rush. There is trillions of years. Let that time scale dilate your perception. The urgency of tomorrow morning fades when set against the lifespan of a red dwarf. You have time. You have all the time in the universe to rest. In the next chapter, we will look at how we find these ghosts. We will look at the lenses, the dragonfly array. We will see how astronomers use special coatings on glass to reduce scattered light, creating a view so clean it can detect the faintest whispers of the cosmos. We will learn about the art of low-surface brightness imaging. But for now, simply be the object being imaged. Be the faint galaxy. Let your edges blur. Let your definition fade. Merge with the background. You are barely there, and that is a beautiful way to be. Sleep in the soft, red glow. Sleep in the lonely heart of the void. We have spoken of these galaxies as ghosts, vast, sprawling structures of stars and dark matter that haunt the empty spaces between the great clusters. They are as large as the Milky Way, yet they possess less than 1% of its light. To the human eye, even if we were floating right next to one, it would appear as nothing more than a slight thickening of the blackness, a subtle amber haze against the void. So how do we know they are there? How does science detect an object that is almost definitionally invisible? The challenge is not one of magnification. We have telescopes powerful enough to see to the edge of the observable universe. The challenge is one of contrast. It is like trying to see a wisp of cigarette smoke against a white wall while the sun is shining directly into your eyes. To see the shadow, you must first eliminate the glare. Tonight, we look at the tools of the ghost hunters. We explore the innovative engineering that allows us to peer into the dimmest corners of reality. We will learn how astronomers took inspiration from the insect world to build a new kind of telescope. A compound eye designed not to see the bright lights, but to embrace the dark. To understand the solution, we must first understand the problem of the traditional telescope. For centuries, the goal of astronomy has been to gather more light. To do this, we built larger and larger mirrors, giant bowls of polished glass coated with aluminum or silver, designed to catch as many photons as possible and focus them to a sharp point. The Hubble Space Telescope, the Keck Observatories in Hawaii, the Very Large Telescope in Chile, these are the titans of light gathering. They are magnificent machines, optimized for finding sharp, bright objects, distant quasars, individual stars in Andromeda, the energetic jets of black holes. But giant mirrors have an Achilles heel. They are imperfect. No matter how perfectly polished a mirror is, there are microscopic irregularities on its surface. Dust settles on it. The support structures holding the secondary mirrors block a fraction of the incoming light. When bright starlight hits these imperfections, it doesn't focus perfectly. It scatters. It bounces around inside the telescope tube. This creates scattered light, a faint, unwanted glow that spreads across the entire image. If you look at a photograph of a bright star taken by a reflecting telescope, you will often see spikes of light radiating from it, diffraction spikes, and a fuzzy halo surrounding it. That halo is noise. It is light pollution generated by the telescope itself. Normally, this doesn't matter. The objects we study are much brighter than the scattered halo. But ultra-diffuse galaxies are fainter than the halo. They are fainter than the noise. Trying to take a picture of Dragonfly 44 with a standard giant telescope is like trying to hear a whisper in a room filled with static. The signal is swamped. To see the faint, we needed to rethink the fundamental design of the telescope. We needed an instrument that prioritized purity over power. Enter the Dragonfly. In the mountains of New Mexico, sitting quietly under the dark desert sky, is an instrument that looks nothing like a traditional observatory. There is no giant dome. There is no massive single mirror. Instead, it looks like a piece of strange, futuristic artillery, or perhaps a hive. It is a cluster of lenses mounted together on a single robotic mount that tracks the stars. It was conceived by astronomers Roberto Abraham and Peter van Dokkum. They realized that to beat scattered light, they had to abandon mirrors entirely. They had to go back to lenses. Lenses, refractors, were the first type of telescope invented by Galileo, but they fell out of favor for large astronomy because big lenses are heavy and hard to make. But modern technology has changed the game. The Dragonfly array does not use custom-made scientific glass. It uses commercial telephoto lenses. the kind used by professional sports photographers or wildlife photographers to capture a lion on the savannah or a football player from the sidelines. Specifically, it uses Canon 400mm lenses. Why? Because the consumer camera market is fiercely competitive. Companies have spent billions of dollars perfecting lens technology to reduce lens flare. When you take a photo into the sun, you get those circles of light, lens flare. Photographers hate it, so engineers developed incredibly sophisticated nano-coatings. These are layers of exotic materials, only a few atoms thick, applied to the surface of the glass. They are designed to let light pass through into the camera, but prevent light from reflecting back out or bouncing between the glass elements. These coatings act like light sponges. They absorb stray photons. Abraham and van Doukum realized these lenses were the perfect weapon against scattered light. They were mass-produced masterpieces of optical engineering. But one camera lens is small. It cannot gather enough light to see deep into the universe. So they took a lesson from biology. They looked at the insect. A dragonfly does not have two large eyes like a human. It has two enormous compound eyes, each made of up to 30,000 individual lenses called ommatidia. Each tiny lens captures a small amount of light, a separate image. The dragonfly's brain combines these thousands of inputs into a single high-resolution wide-angle view of the world. It is incredible at detecting motion and contrast. The astronomers mimicked this. They bought dozens of high-end telephoto lenses. They mounted them together in a honeycomb pattern. The first version had 10 lenses, then 24. Now, the Dragonfly telephoto array has 48 lenses, all pointing at the exact same spot in the sky. It is a synthetic eye. When it operates, 48 separate cameras take an image simultaneously. The magic happens in the computer afterward. Software takes these 48 images and stacks them on top of each other. It aligns the stars perfectly. The signal, the light from the real galaxies, adds up. With 48 lenses, you gather 48 times more light than a single lens. But the noise, the electronic static of the cameras, does not add up the same way. It averages out. The result is an image that is incredibly deep and incredibly clean. Because there are no mirrors to scatter light, and because the lens coatings are so efficient, the background of the image is almost perfectly black. There are no halos around bright stars, no diffraction spikes. It is a pristine view of the cosmos. And in that pristine blackness, the faint fuzz of the ultra-diffuse galaxies begins to appear. Like invisible ink revealing itself under heat, the ghosts emerge from the noise. This technique is called low-surface brightness imaging. It requires a different mindset than traditional astronomy. It requires immense patience. A normal telescope might take a 30-minute exposure of a galaxy. The Dragonfly array might stare at the same patch of sky for 100 hours. Night after night, it returns to the same field, opening its 48 shutters, drinking in the meager trickle of photons that have traveled for 300 million years from the Coma cluster. It is a meditative form of science. It is not about the quick discovery. It is about the slow accumulation of stillness. Only by sitting perfectly still in the dark for days on end can these faint structures be coaxed into view. The discovery of the UDGs was a shock. we pointed this new type of eye at a well-studied region of the sky, a place we thought we knew perfectly, and suddenly dozens of new galaxies appeared. It was as if we had been looking at the ocean for centuries, but only seeing the breaking waves. Suddenly, we put on polarizing glasses that cut the glare, and we saw the vast schools of fish swimming just beneath the surface. The universe turned out to be much more crowded than we thought, but crowded with ghosts. There's a profound lesson here about how we perceive reality. We see what our tools allow us to see. When we change the tool, we change the universe. For decades, our tools were biased toward brightness, so we built a model of a universe dominated by bright, dense objects. Now, with tools biased toward faintness, we see a universe rich in diffuse, gentle structures. What else are we missing simply because we are not looking in the right way? As you prepare for sleep, think about the scattered light in your own mind. The bright, loud thoughts of the day, the worries that flare up like bright stars, casting a haze of anxiety over your consciousness. It is hard to see the quiet, deeper parts of yourself through that glare. Sleep requires a dragonfly approach. You need to apply the nanocoatings to your mind. Reduce the internal reflections. When a bright thought arrives, do not let it bounce around. Let it be absorbed by the velvet lining of relaxation. Create a pristine darkness inside. And then exercise the patience of the long exposure. Do not expect sleep to come instantly. It is not a bright target you can snap a quick picture of. It is a faint, diffuse state. You must lie still. You must keep the shutter open. Wait. Breath by breath, minute by minute. Slowly, the signal of sleep will rise above the noise of the waking mind. The ghost will appear. Let the multiple lenses of your senses, sight, sound, touch, all lose focus. Let them combine into a single soft blur of comfortable darkness. You are building a compound eye for rest. In the next chapter, we will look at the ultimate telescope for finding faint things. The James Webb Space Telescope. We will leave the Earth's atmosphere behind entirely. We will travel to the cold dark of deep space, where the sky is blacker than any desert night. We will see how Webb is finding the ancestors of these ghosts, the very first faint galaxies that formed at the dawn of time. But for now, stay with the dragonfly on the mountain. The lenses are cool to the touch. The mount is tracking. Slowly, the shutters are open. The universe is whispering into the glass. Listen to the light. Sleep in the clean, dark quiet of the compound eye. We have stood on the mountaintops of New Mexico, watching the dragonfly array stare patiently into the night. We have learned that to see the faintest ghosts of the nearby universe, we must banish scattered light and overcome the noise of our own instruments. But even the highest mountain on Earth is compromised. We are still looking through an atmosphere, a turbulent blanket of air that shimmers, blurs, and subtly glows. To see the true depth of the dark, we must leave our home planet behind. We need a vantage point where the sky is eternally black, where the air never trembles, and where the heat of the earth cannot reach us. We need a machine built not just to see the faint, but to see the ancient. A time machine designed to peer back across 13 billion years of history to catch the very first whispers of light in the cosmos. Tonight, we travel 1,000,000 miles from Earth. We journey to the cold, silent outpost of Lagrange Point 2. Here, slowly unfolding in the absolute zero of deep space, sits the ultimate ghost hunter, the James Webb Space Telescope, a giant golden eye that has opened up a new universe of the faint and the forgotten. To understand why we needed this machine, we must understand the nature of cosmic time. The universe is constantly expanding. Space itself is stretching between the galaxies. Imagine drawing a wavy line on a rubber band. That wavy line is a light wave traveling through space. Now, stretch the rubber band. The wave stretches with it. Its peaks get further apart. Its wavelength gets longer. In the physics of light, longer wavelength means redder color. Blue light stretches into yellow. Yellow stretches into red. And if space stretches enough, visible red light stretches past the ability of our eyes to see it. It becomes infrared, heat radiation. This is called cosmological redshift. The very first galaxies formed when the universe was young, perhaps only a few 100 million years after the Big Bang. These infant galaxies were full of hot, bright blue stars. They blazed with intense ultraviolet light. But that light has been traveling toward us for over 13 billion years. During that immense journey, the expansion of the universe has stretched that ultraviolet light all the way down into the infrared spectrum. To the Hubble Space Telescope, which sees mostly visible light, these earliest galaxies are invisible. They have redshifted right off the edge of its vision. To see the beginning of everything, we needed eyes that could see heat. We needed an infrared telescope. But seeing heat in space is incredibly difficult. Any object that is warm glows in infrared. The Earth glows. The moon glows. The telescope itself, warmed by the sun, glows. Trying to detect the faint heat signature of a distant galaxy while your telescope is warm is like trying to see a match struck on the surface of the sun. The signal is swamped by the local heat. So the telescope must be cold, incredibly cold. Enter the James Webb Space Telescope. It is an engineering miracle designed to achieve this supreme coldness. First, location. It is not in orbit around the Earth, like Hubble. It is parked 4 times further away than the Moon, at a gravitational balance point where it can keep the Earth, Moon, and Sun all on the same side of the sky at all times. Second, protection. To block the heat from those 3 celestial bodies, Webb carries a parasol. It is a 5-layered sunshield the size of a tennis court. It is made of Captain, a shiny, silvery material thin enough to be folded like origami, but tough enough to stop micrometeoroids. The gap between each layer is a vacuum, providing perfect insulation. On the hot side, facing the sun, the temperature is nearly 100 degrees Celsius, hot enough to boil water. But on the cold side, in the permanent shadow of the shield, lies the telescope. Here, the temperature drops to minus 230 degrees Celsius, just 40 degrees above absolute zero. It is passive cooling on a grand scale. The heat simply radiates away into the infinite blackness, leaving the mirrors frozen and dark. And what mirrors they are! A honeycomb of 18 hexagonal segments folded up in the rocket and unfolded in space to create a primary mirror 6.5 meters across. They are made of beryllium, a metal that is light, stiff, and holds its shape perfectly in the extreme cold. and they are coated in gold. A microscopic layer of pure gold. Why gold? Because gold is the most perfect reflector of infrared light known to science. It catches the heat waves and focuses them with staggering precision. So there it sits, a golden eye hidden behind a silver shield, floating in the frozen silence, millions of miles from home, waiting for the oldest photons in the universe to arrive. When Webb opened its eye, the view changed forever. It pointed at what looked like empty patches of sky, places where Hubble saw nothing but black. And like the dragonfly array on Earth, Webb exercised the patience of the long exposure. It stared for dozens of hours, letting the infrared photons trickle onto its detectors one by one. The resulting images, the deep fields, are overwhelming. Time, threes. The empty patch is not empty. It is overflowing, thousands upon thousands of galaxies, glittering like jewels spilled onto black velvet. There are spirals and ellipticals, the familiar shapes of the modern universe. But look closer. Look at the tiniest, reddest smudges in the background, the dots that are barely there. These are the high redshift galaxies, the ancestors. We are seeing them as they were just 300 or 400 million years after the Big Bang. This is the cosmic dawn, the era when the first lights turned on in the universe. These galaxies are unlike anything we see today. They are tiny, maybe only 1% the size of the Milky Way. And they are chaotic. They are not neat spirals. They are messy clumps, irregular blobs, train wrecks of gas and young stars smashing together. They are growing intensely fast. They are forging stars at a furious rate, blazing with a fierce, youthful energy that has been stretched into a gentle infrared glow by the time it reaches us. These are not the red and dead ghosts of the ultra-diffuse galaxies we met earlier. These are the vibrant seeds. Yet they share a quality with the lost galaxies: faintness. They are so distant that their light is incredibly attenuated. Only the massive collecting area of Webb's golden mirror, combined with the perfect darkness of deep space, can detect them. We are looking at the baby pictures of the cosmos. And in these pictures, we find surprises. Webb is finding galaxies that are bigger, brighter, and more mature than anyone expected to find so early in time. It seems the universe got to work quickly. Gravity pulled the gas together faster than our models predicted. It forces us to rethink how the very first structures grew out of the primordial dark matter web. There is a profound sense of connection in looking at these images. Every atom in your body, the carbon, the oxygen, the iron, was forged in the heart of a star. When we look at these distant ancient galaxies, we are looking at the furnaces where the first heavy elements in the universe were created. We are looking at our own chemical origins. The light from those galaxies has traveled for 13 billion years to end its journey on the gold surface of Webb's mirror. It is a direct line of communication from the beginning of time to the present moment. As you lie in the dark, let the concept of infrared comfort you. Infrared is heat. It is warmth. The universe is not just filled with cold, harsh light. It is filled with the glowing warmth of ancient creation. Webb is seeing the heat signature of the Big Bang's aftermath. Imagine your own past redshifting. The events of your childhood, your early years, they are far away now. The sharp, bright details might have faded. but the warmth of those memories remains. The emotional resonance has stretched into a deeper, softer wavelength. Like Webb, you can turn your internal telescope to the past. Don't look for the sharp details. Look for the glow. Look for the feeling of who you were when you were just beginning. The messy, chaotic, energetic beginnings of your own self. View them with compassion across the distance of time. Consider the silence of Lagrange Point 2. It is a silence far deeper than any on Earth. There is no air to carry sound, no vibration. The telescope operates in absolute stillness. Its movements are methodical and slow. It is the ultimate meditative posture, turning away from the bright sun, turning away from the noisy earth and facing the infinite dark with an open eye. Adopt that posture tonight. Turn your attention away from the bright concerns of the day. Deploy your own sunshield, block out the noise. Create a cold, quiet space inside. And then just look into the dark. Don't look for anything specific. Just let whatever faint signals are there arrive. Let the deep field of your subconscious slowly reveal itself. The faint galaxies are there, the ancient memories, the quiet ideas. They are waiting in the infrared. In the next chapter, we will bring it all together. We will look at the why. Why do these faint things matter? The nearby ghosts like Dragonfly 44 and the distant ancestors found by Webb. We will see how they are challenging our theories of dark matter, how they are forcing us to rewrite the history of how galaxies grow and die. We will learn that the faintest things carry the heaviest implications. But for now, stay in the cold. Stay by the golden mirror. The oldest light in the universe is arriving. It is a soft, warm glow from the beginning of time. Let it warm your sleep. Sleep in the deep field. Sleep in the golden eye. We have spent this journey establishing a rule of the cosmos. The visible is merely a passenger of the invisible. We have learned that galaxies are not just collections of stars. They are vast, spherical halos of dark matter, the giant shadow, that trap gas and light in their gravitational centers. We believe that this shadow is essential. It is the cradle, the glue, and the shield. Without it, we assumed a galaxy could not exist. But the universe delights in breaking its own rules. Just as we grew comfortable with the idea that every galaxy is a heavy ghost wrapped in a thick cloak of dark matter, we found something that shouldn't be there. Or rather, we found something that wasn't there. Tonight, we travel to the constellation Cetus. We look at a smudge of light called NGC 1052 DF2. It looks like a typical ultra-diffuse galaxy, faint, ghostly, and large. But when we looked closer, we found a paradox. The shadow was missing. This is the story of the naked galaxy, a structure of pure light floating unprotected in the void, and what it tells us about the weight of existence. To understand why this discovery shook the foundations of astrophysics, we must revisit the concept of weighing a galaxy. You cannot put a galaxy on a scale. To measure its mass, you must measure motion. In the Milky Way, or in Dragonfly 44, the stars and clusters orbit fast. They are whipped around by the intense gravity of the dark matter halo. High speed implies heavy mass. This is the standard model. In 2018, astronomers turned their telescopes toward NGC 1052 DF2, or DF2 for short. It is a faint patch of light about 65 million light-years away. They wanted to measure its mass. To do this, they tracked the movement of its globular clusters. DF2 has a retinue of 10 bright clusters orbiting it. They look like distinct, fuzzy dots against the diffuse background of the galaxy. The astronomers measured their velocities. They expected them to be zipping around at high speeds, just like in every other galaxy ever observed. But they weren't. The clusters were moving lazily. They were drifting, slow, lethargic. The astronomers checked the data again. The speed was shockingly low. When they plugged these low speeds into the gravity equations, the result was 0. The mass of the galaxy could be entirely explained by the stars alone. There was no room in the math for dark matter. The ratio of dark matter to regular matter in a typical galaxy is usually 10:1, or even 100:1, as in Dragonfly 44. In DF2, the ratio was essentially 0:1. It was a galaxy made only of light. This discovery was met with disbelief. A galaxy without dark matter is like a galaxy without stars, one physicist remarked. It seemed like a contradiction in terms. How could it hold together? How did it form? It was a naked object in a clothed universe. But then they found another one, NGC 1052 DF4. Same story, faint, diffuse, and composed of stars that were drifting with a distinct lack of urgency. The anomaly was real. This discovery, oddly enough, became the strongest proof yet that dark matter is real. Consider the alternative theory, modified gravity. Some scientists argued that dark matter doesn't exist, and that we just don't understand gravity. They suggested that gravity gets stronger at large distances inherently. If that were true, if gravity is a fixed law of nature, then every galaxy should show the effect. Every galaxy should spin fast. Gravity should be modified everywhere, all the time. But DF2 showed us a galaxy behaving exactly as Newton predicted. Normal gravity, no extra boost. This means the extra boost seen in other galaxies is not a law of nature. It is a substance. Dark matter is a thing. It is a stuff. And like any stuff, it can be separated from the object. You can take the milk out of the coffee if you have the right centrifuge. So how do you strip a galaxy of its shadow? The answer lies in the violence of the environment. DF2 and DF4 are not drifting alone in the void. They are satellites. They live in the neighborhood of a massive elliptical galaxy called NGC 1052. NGC 1052 is a bully. It is a giant gravity well. As the smaller galaxies orbit the larger one, they experience tidal forces. Gravity pulls harder on the near side of the galaxy than the far side. This stretches the object. If a small galaxy dips too close to the giant's gravity can reach in and strip material away. Dark matter is usually located in the outer halo of a galaxy. It is the first thing to go. Imagine a traveler walking through a storm. The wind blows away their cloak, their hat, their outer layers. DF2 and DF4 are travelers who have lost their cloaks. They ventured too close to the monster. The monster's gravity stripped away their dark matter halos, leaving only the dense core of stars behind. Now, they drift naked through space. They are tidal dwarf galaxies. They are survivors of a cosmic mugging. Time threes, but there is a beauty in their nakedness. Without the dark matter to bind them tightly, these galaxies are expanding. They are puffing out. They are becoming even more diffuse. And eventually, they will dissolve. Without the glue of the shadow, the stars will slowly drift apart. They will join the stellar stream orbiting the giant galaxy. DF2 is a temporary object. It is a galaxy in the process of evaporation. Let us contemplate the feeling of weightlessness that DF2 represents. In the rest of the universe, everything is held in a tight grip. The stars are prisoners of the halo. They are forced to orbit at high speeds, trapped by the invisible mass. But in DF2, the grip is gone. The stars are free. They're moving under the influence of their own mutual gravity, which is weak. If you lived on a planet in DF2, you would be in a uniquely gentle environment. The escape velocity of the galaxy is low. If our civilization lived there, our rockets could leave the galaxy easily. We wouldn't need massive boosters to escape the heavy pull of the dark matter halo. The galaxy is porous, open. It is a place of low tension. Imagine the difference between a clenched fist and an open hand. The Milky Way is a clenched fist, tight, energetic, held together by force. DF2 is an open hand, relaxed, spreading out, letting go. As you lie in the dark, visualize this naked galaxy. See the stars drifting lazily. They are not rushing, they are not being whipped around. They are floating like dust motes in a sunbeam. Connect this image to your own state of mind. Often, we carry dark matter in our minds. Invisible weights, the heavy expectations, the gravity of past mistakes, the pressure of future duties. We cannot see these things, but we feel their pull. They make us spin faster. They keep us trapped in high-velocity orbits of anxiety. We feel we must hold everything together. We must be heavy to be real. But DF2 teaches us that you can exist without the weight. You can shed the shadow. Imagine the tidal forces of sleep stripping away your dark matter. Let the heavy, invisible burdens be pulled away from you. Let them drift off into the void. You are left as a collection of pure light. Your thoughts, your memories, your essence. Without the heavy halo of worry holding them tight, your thoughts can slow down. They can drift apart. They can become ultra-diffuse. Feel the relief of that expansion. You do not need to be a tight, efficient machine tonight. You can be a loose, drifting cloud. The naked galaxy is transparent. Look right through it. See the distant universe behind it. Become transparent yourself. Let the night pass through you. Consider the globular clusters of DF2 again. Those 10 bright knots of stars. They are the only things holding on. They act as the anchors in the drift. In your sleep, you have anchors too. The rhythm of your breath, the warmth of the bed. Let everything else drift, but keep those anchors. The discovery of DF2 was a reminder that the universe is diverse. There are heavy places, and there are light places. There are places dominated by the shadow, and places where the light walks alone. It validates the complexity of the cosmos. And it validates the concept of unburdening. Even a galaxy can lose its baggage. Even a galaxy can experience a period of lightness before it dissolves into the great stream. As we move toward the end of the story, we realize that the lost galaxies are not lost. They are simply different. They are the quiet introverts of the galactic party. They don't make a scene. They don't emit X-rays. They don't spin fast. They just drift. And in their drifting, they tell us the truth about gravity. In the final chapter, we will bring all the threads together. We will look at the faint future. We will see that eventually, all galaxies will become faint. As the stars burn out and the universe expands, everything will fade into the infrared, then the radio, then the silence. We will see that the lost galaxies are pioneers. They are showing us what the end of the universe looks like. A quiet, beautiful amber fade. But for now, stay with the lightness. You have shed the halo. You are weightless, floating in the constellation of Cetus, a cluster of stars drifting in the calm. Sleep in the galaxy without a shadow. Sleep in the light. We have spent this series hunting for anomalies. We have looked at the ultra-diffuse galaxies as if they were rare, exotic beasts, ghosts haunting the edges of the great clusters, or naked singularities drifting in the void. We have treated them as the exception to the rule. We assume that the normal universe is made of bright, spiral galaxies like our own, and that these faint wisps are merely the strange debris at the fringes. But what if we are wrong? What if our assumption is based on a fundamental error of perception? There is a parable often told in science about a man searching for his keys at night. He's looking under the bright streetlight. A police officer asks him, "Are you sure you lost them here?" The man replies, "No, I lost them over there in the dark park, but the light is better here." Tonight, we confront the possibility that we have been looking under the streetlight for too long. We will ask if the lost galaxies are not lost at all, but are, in fact, the majority. We will explore the idea that the universe is crowded with ghosts, and that the bright galaxies we see are merely the rare, flashy celebrities in a cosmos populated by the quiet and the dim. To understand this shift in perspective, we must understand selection bias. For centuries, astronomy was defined by what the human eye could see, then by what photographic plates could capture, then by what digital sensors could detect. Every instrument has a limit, a threshold. If an object is brighter than the limit, we put it in the catalog. We name it. We study it. If an object is fainter than the limit, it doesn't exist to us. It remains part of the black background. Because bright galaxies are easy to find, we found them first. We found thousands of them. And so we built a model of the universe based on them. We decided that a standard galaxy looks like the Milky Way. But this is like walking into a forest and deciding that because the redwoods are the easiest trees to see, the forest is made mostly of redwoods. We miss the moss, we miss the ferns, we miss the undergrowth. The ultra-diffuse galaxies are the undergrowth of the cosmos. When we finally built telescopes like the Dragonfly Array, instruments capable of seeing into the shadows, we didn't just find a few of these galaxies. We found thousands. In the Coma cluster alone, we found that for every bright, shining galaxy, there are dozens of faint, ghostly ones. This suggests a staggering conclusion. The lost galaxies might actually be the most common type of galaxy in the universe. We are living in a hidden crowd. Imagine the night sky again. You look up and see the stars. You see the faint band of the Milky Way. You see the Andromeda galaxy as a tiny smudge. You think the space between these objects is empty. But if your eyes could adjust to the low surface brightness regime, the sky would fill up. The empty patches would bloom with soft amber light. Huge, tenuous spirals would appear in the voids. dwarf galaxies would swarm around the Milky Way like moths around a lamp. We are surrounded by unseen neighbors. This realization helps solve one of the longest-standing accounting problems in astrophysics, the problem of the missing baryons. We know from the cosmic microwave background exactly how much normal matter, baryons, was created in the Big Bang. We have a very precise recipe for the universe. But when we tally up all the stars, all the gas clouds, and all the dust in the visible galaxies, we come up short. About 30 to 40% of the normal matter is missing. It's not in the stars. It's not in the hot gas. Where is it? For years, astronomers suspected it was hiding in the warm, hot intergalactic medium, wispy filaments of gas connecting the galaxies. But now, we suspect that a significant portion of it is locked up in the low-surface brightness universe. It is hiding in the faint stars of the lost galaxies. The universe is not missing its matter. It is just keeping it dim. Nature, it seems, is efficient but not showy. It creates matter, but it does not feel the need to light it up like a billboard. Let us contemplate the iceberg theory of the cosmos. The visible galaxies, the Hubbles, the Pinwheels, the Andromedas, are the tips of the icebergs. They are the peaks that jut above the surface of the dark ocean. The ultra-diffuse galaxies are the submerged mass. They hover just below the waterline of visibility. And below them? There may be galaxies even fainter. Dark galaxies. Objects made entirely of dark matter and cold gas with perhaps only a handful of stars. Objects that are effectively invisible to any optical telescope, no matter how powerful. We find hints of them in radio surveys. We see clouds of hydrogen gas spinning in the void, orbiting. Nothing. They are galaxies waiting to be born, or galaxies that failed to ignite. This concept fundamentally changes our feeling of space. We usually feel that space is lonely, vast distances, empty voids. But the hidden crowd tells us that space is actually quite cozy. It is packed. We are not isolated in a desert. We are jostling in a crowd of ghosts. Everywhere we look, there is structure. Everywhere we look, gravity is working. The apparent emptiness is just a limitation of our biology. Consider the Fermi paradox, the question, where is everybody? Usually, we ask this about aliens, but we can ask it about galaxies too. The answer is, they are right here. We just weren't looking correctly. Perhaps the same is true for life. Perhaps the universe is teeming with life, but it is ultra-diffuse life, silent, low energy, hidden. Not distinct civilizations broadcasting radio waves, but quiet biospheres mossing over the rocks of dim red dwarf systems. The universe seems to favor the quiet approach. As we drift deeper into this chapter, let us use this hidden crowd to reframe our own sense of solitude. In the middle of the night, when you are awake and the world is asleep, you can feel lonely. The house is quiet. The streets are empty. But you are not alone. The night is full of life. The insects in the grass, the birds roosting in the trees, the millions of other people sleeping in the city around you. They are quiet, they are faint, they are low-surface brightness presences. But they are there. You are part of a vast, breathing, sleeping collective. Like the ultra-diffuse galaxies clustering in coma, we cluster in our cities and towns. Even if we do not see each other, the gravity of our shared existence holds us together. Let the background become a comfort. In visual art, negative space is the space around the subject. In the universe, the negative space is actually full of positive content. Imagine the air in your room. It looks empty, but it is full of molecules, full of Wi-Fi signals, full of neutrinos. It is thick with reality. Rest your mind on this thickness. You are supported by the invisible. Think about the average galaxy. If we took a census of the universe, the Milky Way would be an outlier. It is too big, too bright, too active. The average citizen of the cosmos is a UDG, a faint dwarf. Living a quiet life, burning fuel slowly, disturbing no one. There is a virtue in being average in this cosmic sense. It means stability. The bright galaxies attract trouble. They attract mergers. They attract active black holes. The faint galaxies endure. Tonight, let go of the need to be a Milky Way. You do not need to be a grand spiral design. You do not need to be blazing with star formation. You do not need a supermassive black hole at your center. You can be a UDG. Spread out, relaxed, dim. Let your energy diffuse over a large area. Instead of a sharp point of focus, let your awareness become a soft field. Cover the whole bed, cover the whole room. But keep the intensity low. Barely there. This is the ghost mode of consciousness. It is the mode of sleep. When you dream, you are a ghost in your own mind. You float through scenes. You observe without interacting physically. You are reclaiming your place in the hidden crowd. Let us look at the sky background one last time. Astronomers spend their lives trying to subtract the sky background to see the objects. But the background is the object. The glow of the night sky is the combined light of trillions of faint stars and galaxies that we cannot resolve. The dark is not dark. It is a deep, uniform light. You are sleeping in a sea of ancient light. In the final chapter, we will turn to the future. We will look at the long fade. We will see that eventually, even the Milky Way will become faint. As the gas runs out and the stars die, every galaxy will turn into a ghost. We will see that the lost galaxies are not anomalies. They are prophecies. They are showing us the destiny of the universe. A quiet red fading beauty. But for now, stay in the crowd. You are surrounded by the silent majority of the stars. You are never truly alone in the dark. Sleep in the company of the unseen. Sleep in the hidden light. We have spent 6 nights hunting for ghosts. We have peered through the compound eyes of the dragonfly array to find the faint smudges of ultra-diffuse galaxies. We have traveled to the cold orbit of the James Webb Telescope to see the infrared glow of the cosmic dawn. We have stood inside the lonely halos of galaxies that have lost their dark matter, and we have realized that the universe is crowded with silent, invisible neighbors. Throughout this journey, we have looked at these faint objects as anomalies, strange, premature relics that sit apart from the vibrant, living galaxies like our own. But tonight, in this final chapter, we must accept a deeper truth. The lost galaxies are not anomalies. They are prophecies. They are showing us the destination of all things. The universe is not a static painting. It is a film that is slowly playing out, and the script of that film calls for a gradual dimming of the lights. Tonight, we will look forward. We will see the destiny of the Milky Way. we will see that eventually we too will become a ghost in the dark, and we will find that this fading is not a tragedy, but a beautiful, gentle settling into the eternal rest. To understand the future, we must look at the life cycle of color. Astronomers sort galaxies into two main camps, the blue cloud and the red sequence. The blue cloud is where the Milky Way lives today. It is the club of the living. These galaxies are rich in gas. They are actively collapsing clouds of hydrogen to form new stars. The massive, hot, blue stars dominate the light, giving the galaxy its energetic hue. It is a time of noise, of supernova, of bright spiral arms. The red sequence is the retirement home, the red and dead. These are the elliptical galaxies and the ultra-diffuse galaxies we have studied. They have run out of gas. Their blue stars have died. Only the small, cool, red stars remain. They are quiet, stable, faint. Between these two camps lies a transition zone called the Green Valley. It is a place where galaxies go to power down. The Milky Way is currently approaching the Green Valley. We are running low on fuel. The vast reservoirs of cold hydrogen that once filled our halo are being depleted. We are turning them into stars, and the stars are locking that matter away in their cores or blowing it out into space where it is too hot to collapse again. We are essentially a car running on its last quarter tank. But before we fade, there will be one last burst of fireworks. Look at the constellation Andromeda. The great spiral galaxy M31 is headed straight for us. In about 4 billion years, our two galaxies will collide. It will not be a crash of destruction. Stars are too far apart to hit each other. It will be a merger of fluids. The gas clouds of both galaxies will smash together. This will trigger a frantic burst of star formation. The sky will blaze with new clusters. But this is the final party. The violence of the merger will use up the remaining gas. The supermassive black holes at the centers will merge, creating a quasar that will scour the galaxy clean of any leftover fuel. When the dust settles, the beautiful spirals will be gone. The pinwheels will be destroyed. In their place will be a single giant blob. Astronomers call this future object Milkomeda. It will be an elliptical galaxy, a vast, football-shaped swarm of stars. And it will be red. The blue stars will die out. The white stars will fade. The amber light of the red dwarfs will take over. Milkomeda will settle into a long, quiet decline. It will become a high-surface brightness galaxy at first. But over trillions of years, interactions with other galaxies and the relentless expansion of space might puff it up. It might eventually become ultra-diffuse. Imagine the view from a planet in this distant future. The night sky is no longer a band of milk. It is a uniform field of stars. But the view beyond the galaxy has changed even more dramatically. Dark energy is pushing the other galaxies away. The Virgo cluster, the Coma cluster, they are all receding. Eventually, they will cross the cosmic horizon. Their light will no longer reach us. Milkomeda will be alone. To a future astronomer, the universe will consist of just one island, one giant, red-fading galaxy surrounded by an infinite empty void. They will look at the old records of the Milky Way era, our era, as a mythical time of blinding light and crowded skies. They will live in the era of the lost galaxy. But is this sad? We often equate fading with dying. But let us reframe it. let us look at the faint future through the lens of peace. The era of star formation is violent. It is chaotic. Radiation is intense. Life is constantly threatened by supernova and gamma-ray bursts. The red era is calm. The red dwarf stars are stable. They provide a steady warmth for trillions of years. A civilization living in Milkomeda will not have to worry about the sky falling. They will have an eternity of stability. The fading is simply the universe settling into a comfortable chair after a long day of work. The frenetic energy of youth is gone. The wisdom of age remains. Think of the embers of a fire. The roaring flames are exciting, but they are hot and unpredictable. They smoke, they crackle. The coals, however, the coals are deep. They glow with a steady, penetrating heat. They last through the night. The future of the universe is an era of coals. The lost galaxies we see today, Dragonfly 44 DF2, are simply embers that formed early. They are showing us the comfort of the coals. Let us bring this cosmic timeline down to the scale of tonight. Your day follows the life cycle of a galaxy. Morning is the blue cloud, high energy, activity, new things being born, bright light. Afternoon is the green valley, the transition. The energy peaks and begins to level off. Evening is the red sequence. You are entering the red sequence now. The star formation of your mind, the creation of new ideas, new plans, new worries must stop. The gas tank is empty. The fuel of the day is spent. Do not try to force a new burst of activity. Do not try to merge with another galaxy of tasks. Accept the quenching. Let the internal light shift. From the blue light of screens and daylight to the warm, amber glow of the bedside lamp, to the red glow of the closed eyelid. Let the surface brightness of your consciousness drop. During the day, your awareness is a high surface brightness object, focused, sharp, intense. Now, let it spread out. Become ultra diffuse. Let your awareness cover the whole room, but thinly. You are barely there. You are a ghost in your own life. This is the prelude to sleep. Consider the transparency of the future galaxy. As the stars spread out, the galaxy becomes see-through. Become see-through. Let the sounds of the night pass through you without hitting anything. If a dog barks, if a floorboard creaks, let the sound wave pass through your transparent awareness. Do not let it trigger a reaction. You are too faint to be disturbed. There is a freedom in being lost. If you are a lost galaxy, no one is looking for you. You are off the map. You have no obligations, no orbit to maintain. You can just drift, time, sur threes. The faint galaxies float in the voids. The voids are the quietest places in the universe. Imagine your bed is a void. A bubble of emptiness carved out of the busy world. Inside this bubble, the laws of the busy world do not apply. Time flows differently here. It flows at the speed of a red dwarf, slow, infinite. Let us revisit the tools one last time. The Dragonfly Array, the James Webb Telescope. These machines taught us that the darkness is full. Even when you close your eyes and see nothing, you are seeing something. You are seeing the Eigengrau, the dark gray color of the absence of light. But behind that gray, the mind is still there. The universe is still there. You are not turning off the universe. You are just tuning in to the faint channels. The channels of dreams, the channels of memory. These signals are weak. they are easily drowned out by the noise of the day. But now that the noise is gone, the faint signals can arrive. Like the photons from the early universe hitting the golden mirror, the dreams are arriving from the deep parts of yourself. Let them form the image. The long fade is the ultimate destiny of everything. The stars will go out, the galaxies will dissolve, the universe will become a sea of photons cooling toward absolute zero. But this is not an ending to be feared. It is the return to equilibrium. It is the restoration of the balance that was disturbed by the Big Bang. The noise was the interruption, the silence is the norm. Tonight, you are practicing for the eternal. You are letting your own little universe cool down. You are letting your own stars fade. The lights of the neurons are dimming, one by one. The spiral arms of thought are unwinding. The core is settling. You're becoming a lost galaxy, drifting at the edge of visibility, fading out of existence, and into the dream. The faintness is a blanket, wrap it around you. The darkness is a cradle, lie down in it. You are safe in the low surface brightness of the night. You are part of the hidden crowd. Rest in the dim, golden light. Rest in the fade. Sleep. Tonight, we turn our faces upward toward the source of all warmth and all life in our corner of the universe, the sun. To the casual observer, it is a yellow disk in the sky, a reliable clock that marks the days, a lamp that banishes the fear of the dark. But to the physicist, and to the dreamer of cosmic scales, the sun is something far more terrifying and magnificent. It is a fusion reactor of incomprehensible power, a burning engine that consumes 600 million tons of hydrogen every single second. As you lie here, bathed in the memory of daylight, let us strip away the familiarity of the sunrise and look at the raw, violent reality of the star that holds us. Consider the energy. Every second, the sun releases 384 yottawatts of power. That number is a 3 followed by 26 zeros. It is a quantity of energy so vast that it defies the metaphors of human language. If you could capture the energy the sun emits in just 1 single second, it would be enough to power the current human civilization, with all its cities, factories, and vehicles, for 500,000 years. 1 second of solar output equals 500,000 years of human history. Now, consider the tragedy of geometry. The Earth is a tiny target. It is a speck of rock, barely 12,000 kilometers wide, orbiting at a distance of 150 million kilometers. Imagine a single grain of sand held at arm's length, orbiting a basketball. Because of this vast distance and our small size, the Earth intercepts only a microscopic fraction of the sun's light. For every photon that strikes the Earth, warming our oceans and feeding our plants, 2 billion photons miss us entirely. They fly past us, disappearing into the infinite cold blackness of deep space, their energy wasted forever. We are a civilization of scavengers. We huddle around a campfire, catching the few sparks that happen to fly in our direction, while the vast majority of the heat is lost to the night. For all of human history, this has been enough. The solar income, the sunlight that hits the Earth, drove the weather, grew the crops, and laid down the ancient forests that became our coal and oil. But we are growing. Our hunger for energy is exponential, We have moved from burning wood to burning coal, from splitting atoms to covering our deserts in silicon panels. And yet, we are still trapped by the limits of our planet's surface area. There comes a moment in the maturation of any intelligent species when they realize the trap. A planet is a cradle, but it is also a cage. The resources of a single world are finite. The coal seams run dry. The uranium mines are exhausted. Even if we covered every square inch of the Earth with solar panels, destroying every forest and ocean to do so, we would still only be capturing that 1/1000th of the star's power. To truly grow, to truly ascend to the next level of existence, we must stop thinking like a planetary species and start thinking like a stellar one. We must stop scavenging the sparks and claim the fire itself. This is the vision of the physicist Freeman Dyson, who looked at the stars in 1960 and asked a simple question. If a civilization survives for millions of years, if it does not destroy itself with war or folly, its energy needs will eventually exceed the light falling on its home planet. What then? They cannot import energy from other stars. The distances are too great. They must harvest what is already there. They must dismantle their other planets, pulverize their moons, and rearrange that matter into a shell, a sphere, a net thrown around the star to catch every drop of the golden rain. This is the definition of a Type 2 civilization on the Kardashev scale. A Type 1 civilization controls the resources of its planet. That is what we are striving to become today. A Type 2 civilization controls the resources of its star. The difference in power is not merely quantitative, it is qualitative. A Type 2 civilization possesses energy on a scale that makes them indistinguishable from gods. They could terraform worlds in a decade. They could build computers that simulate realities. They could send beams of light across the galaxy to communicate with other minds. The transition from Type 1 to Type 2 is the single greatest leap a species can make. But let us not get ahead of ourselves. Let us return to the hunger. Why do we need this energy? Is it simply greed? No. It is the physics of complexity. As a society becomes more complex, more information, more art, more computation, more comfort for its citizens, its entropy production rises. To maintain order, to prevent the decay of civilization, requires a constant influx of high-quality energy. We are currently hitting the ceiling of what the Earth can provide without cooking itself. We see the signs in the changing climate, in the stressed ecosystems. We are a growing organism pressing against the glass walls of our petri dish. Imagine the silence of the wasted light. Visualize a photon born in the core of the sun. It spends 100,000 years fighting its way to the surface, bouncing between atoms in the dense plasma. Finally, it breaks free. It leaps into the vacuum, traveling at 300,000 kilometers per second. It flies for minutes, then hours, then years. It passes Mars. It passes Jupiter. It passes the lonely sentinel of Pluto. And then, nothing. It travels for eternity in the void, expanding, redshifting, eventually becoming a part of the microwave background radiation. It does no work. It creates no life. It is potential that was never realized. The Dyson sphere is the answer to this cosmic waste. It is a declaration that intelligence has a right to the energy of the universe. It is a project of immense ambition, one that requires a shift in perspective so radical it changes the definition of human. It requires us to look at the other planets in our solar system not as destinations to be visited, but as raw materials. Jupiter is not a god. It is a ball of hydrogen waiting to be burned. The asteroid belt is not a hazard. It is a quarry. Mercury is not a planet. It is a mine. The concept begins as a whisper in the data. Astronomers analyzing the light curves of distant stars look for anomalies. They look for stars that are dim in visible light but bright in the infrared. They are looking for the heat signatures of alien Dyson spheres. We have not found one yet. The galaxy seems silent. This leads to a chilling possibility. Perhaps the transition is too hard. Perhaps civilizations burn out before they can build the shell. Or perhaps we are the first. Perhaps the responsibility of lighting the first beacon in the Milky Way falls to us. Let us walk through the logic of the necessity. Even with fusion power, artificial stars built on Earth, we are limited by heat. If we generated enough fusion power on Earth to match a Type Taus-2 civilization, the waste heat alone would boil the oceans. The laws of thermodynamics are strict. You cannot generate massive amounts of energy on a biosphere without destroying it. To use the power of a star, you must go to the star. You must move the industry, the computation, and eventually the population off the surface of the heat-sensitive rock and into the vacuum where the heat can be radiated away. The hunger for light is also a hunger for survival. A single planet species is vulnerable. An asteroid impact, a supervolcano, a nuclear war, any of these could extinguish the flame of consciousness. But a civilization spread across a Dyson sphere, living in billions of habitats orbiting the sun, is immune to localized disasters. You could destroy 1,000 worlds and the civilization would continue. The sphere is the ultimate insurance policy. It guarantees that the music of humanity will not be silenced by a random cosmic accident. So, the decision forms. It does not happen in a year or even a century. It is a gradual dawning of awareness. As our computers grow faster, demanding more electricity, as our population stabilizes but our standard of living rises, as we begin to dream of interstellar travel, which requires energy simply unavailable on Earth, we turn our eyes to the sun. We stop seeing it as a background object and start seeing it as the ultimate battery. We realize that we are swimming in an ocean of energy, dying of thirst because we lack the cup to catch it. The project will take 1,000 years. It will require the dismantling of worlds. It will require an army of autonomous robots numbering in the trillions. It will require the complete reorganization of the solar system. But the reward is the stars. The reward is a civilization that can think thoughts as long as the age of the universe. A civilization that can shape reality to its will. The hunger for light drives us out of the cave and into the glare of the cosmic noon. Pitch 1%. As we end this first chapter, let us hold two images in our minds. The first is the Earth, a fragile blue marble, struggling to sustain its billions of souls. The second is the sun, a roaring giant pouring its wealth into the void. The story of the Dyson sphere is the story of connecting these two. It is the story of building a bridge between the need and the source. The blueprints are being drawn in the minds of the physicists. The math is checking out. The hunger is growing, and the sun awaits. When the mind first grasps the concept of enclosing a star, it defaults to the simplest, most geometric form: a solid, continuous shell, a hollow sphere, rigid and unbroken, surrounding the sun at the distance of the Earth. In the popular imagination, and indeed in the earliest science fiction to grapple with the idea, this is the Dyson sphere. It is a world on the inside, a vast, concave landscape with a surface area 550 million times larger than the Earth. It is a structure where you could walk forever and never find a horizon, where the sun hangs eternally overhead at high noon, the benevolent deity of an artificial sky. It is a beautiful image. It evokes the grandeur of a cathedral or a fortress. It appeals to our primate desire for walls, for enclosures, for safety. But we must shatter this illusion. We must subject this dream to the cold, unforgiving interrogation of physics. And when we do, we find that the solid Dyson sphere is not merely difficult to build, it is physically impossible. It is a fantasy that violates the fundamental laws of mechanics and gravity. To pursue it would be to build the largest tomb in the history of the universe. Let us consider the stresses involved. If we were to build a rigid shell at a distance of 1 astronomical unit, roughly 150 million kilometers, the sheer mass of the structure would be mind-boggling. Even if the shell were only a few meters thick, the volume of material required would exceed the mass of all the planets in the solar system combined. But the problem is not just finding the material. It is keeping it together. The sun's gravity is immense. It pulls on every square centimeter of this shell with a force that tries to drag it inward, to crush it down into the star. For a solid sphere to resist this inward pull, it must rely on compressive strength. It is the same principle as a stone archway. The stones push against each other to resist gravity. But the scale here is the enemy. The compressive force on a Dyson sphere would be billions of times greater than the crushing pressure at the bottom of Earth's deepest ocean. There is no material in the known universe, not titanium, not diamond, not even the theoretical carbon nanotubes or graphene lattices, that can withstand this pressure. If you built a solid shell, it would buckle, it would crumble, it would shatter like an eggshell under the foot of a giant raining debris, down into the solar furnace. But even if we invented a magical material, a substance with infinite strength, let us call it unobtainium, we would face a second, more insidious problem. It is known as the shell theorem. Isaacs Newton proved centuries ago that inside a hollow spherical shell, the gravitational forces from the shell itself cancel out perfectly. This means that a person standing on the inner surface would feel no gravity from the shell. They would float. To walk on the surface, we would need to spin the sphere to create artificial gravity through centrifugal force. But the stress of spinning an object 300 million kilometers wide would tear it apart instantly at the equator, while the poles would have no gravity at all. The shell theorem reveals an even darker fate for the solid sphere. Because the gravity of the shell cancels out on the inside, the shell exerts no net gravitational force on the Sun. And conversely, the Sun exerts no net gravitational force on the shell to keep it centered. This sounds paradoxical, but it means the system is neutrally stable. The shell is not orbiting the Sun. It is merely sitting around it. If the shell is nudged even slightly by a passing comet, a gravitational wave, or the uneven pressure of the solar wind, it will drift. Imagine the horror of it. The civilization living on the inner surface would look up and see the Sun slowly drifting off-center. One side of the world would begin to roast as the star approached. The other side would freeze. There is no natural restoring force to push the Sun back to the middle. Without massive, impossible active propulsion systems constantly correcting the position of the entire shell, the structure would eventually collide with the star. The solid sphere is dynamically unstable. It is a death trap. So, we must abandon the architecture of the solid. We must stop thinking in terms of roofs and walls. We must start thinking in terms of orbits. An orbit is a balance. It is a compromise between the speed of an object trying to fly away and the gravity of the star trying to pull it down. An object in orbit is in freefall, weightless and stress-free. It does not need infinite compressive strength because it is not fighting gravity. It is surrendering to it in a controlled way. This leads us to the true vision of Freeman Dyson, a vision that was often misunderstood by his contemporaries. He never proposed a solid ball. He proposed a swarm, a Dyson swarm. Imagine not a single continuous surface, but a trillion distinct objects, a trillion satellites, mirrors, and habitats, each following its own independent orbit around the Sun. They are like a cloud of bees buzzing around a hive. From a distance, they might appear as a solid fog, blotting out the light. But up close, they are separate entities, separated by thousands of kilometers of vacuum. The swarm solves every problem of physics that the sphere failed. Since each element is in orbit, there is no crushing pressure. The satellite feels no weight. We can build these structures out of ordinary materials: aluminum, glass, steel. We do not need magic physics. We do not need to dismantle Jupiter to build a shell of impossible thickness. We can dismantle a smaller body, like Mercury, to build vast arrays of ultra-thin foil mirrors. And, because each satellite is independent, the system is robust. If a meteor destroys one mirror, the swarm continues. It is decentralized, resilient, and fluid. Let us visualize the evolution of the swarm. It begins with a single ring, the Dyson ring. We launch our first generation of solar collectors and space habitats into a specific orbit, perhaps the same orbit as Earth, but spaced out evenly. It would look like a necklace of diamonds strung around the Sun. Over time, we add more rings. We tilt them at different angles. We create a Dyson cage, a series of overlapping orbital planes. As the population of satellites grows into the billions, the sky begins to fill. The gaps between the orbits shrink. The cage becomes a shell, not of solid matter, but of trajectories. The density of the swarm is the variable that determines the civilization's power. A sparse swarm might capture 1% of the solar light, still a billion times more energy than we use today. A dense swarm might capture 90%, leaving only a few windows for the stars to peek through. The ultimate goal is complete occlusion, a swarm so dense that from the outside the sun is invisible. The light that tries to escape is intercepted by layer upon layer of machinery, absorbed, used, and finally re-radiated as waste heat. But how do we prevent collisions? Trillion objects orbiting in different planes sounds like a recipe for a chaotic smash-up. This is a problem of orbital mechanics, traffic control on a celestial scale. But remember, space is vast. Even with a quintillion satellites, the distance between them can be maintained. We can arrange them in statite configurations, using solar sails to hover, or strictly organized orbital shells that do not intersect. The computation required to manage this traffic is immense, but for a civilization capable of building the swarm, tracking 1 trillion trajectories is a trivial task. The nature of the individual units in the swarm varies. Some are simple mirrors, vast sheets of polished metal foil, lighter than air, kilometers wide. Their job is to reflect sunlight. They beam the concentrated energy to central collection stations, or perhaps to the planets themselves. A single mirror, angling the sunlight, could melt the ice, caps of Mars, or illuminate the night side of Venus. They are the optical neurons of the system, directing the flow of photons. Others are photovoltaics, giant solar panels converting light directly into electricity. This electricity powers the third type of unit, the habitat. We are not just building a power plant, we are building a home. The solid sphere offered the illusion of living on the inside surface, but in the swarm, we live in O'Neill cylinders. These are rotating tubes, miles long and miles wide. Inside, the centrifugal force creates artificial gravity. There is soil, air, water, there are forests and cities. Living in the swarm is fundamentally different from living on a planet. On Earth, we are exposed to the vacuum on one side. In an O'Neill cylinder within the swarm, the environment is totally controlled. You can have a tropical island in one cylinder and a snowy mountain range in the next. And because we can build billions of these cylinders, the living area is effectively infinite. The total surface area of the habitats in a dense Dyson swarm would be millions of times the surface area of Earth. We could support a population of quadrillions of human beings, each living in ecological luxury. The dismantling of the illusion of the solid sphere is not a loss, it is a liberation. The solid sphere is a prison. It blocks the view of the universe. The swarm is permeable. A ship can navigate through the gaps. We can adjust the density. If we want to see the stars, we can tilt the mirrors. If we need to let sunlight reach the Earth to keep the biosphere alive, we simply leave a gap in the swarm, a clear corridor of space that allows the natural light to fall on the home world. The swarm is flexible. It is a dynamic architecture that breathes and moves. Let us consider the view from Earth as the swarm thickens. It would not happen overnight. It would be the work of centuries. At first, you would see new stars appearing near the sun, visible only during eclipses. Then, a faint haziness would develop around the solar disk. As the centuries pass, the sun would appear to dim slightly as more light is harvested, though the Earth's share would be protected. the zodiacal light, the faint glow of dust in the plane of the solar system, would be replaced by the geometric glitter of the machine cloud. Eventually, the sun might look different entirely. It might be bracketed by shades, rings of collectors, or, if the civilization chooses, the sun could be completely hidden, its location marked only by the infrared glow of the machinery. But for the inhabitants of the swarm, the view is spectacular. They live in a sea of light. They look out their windows not at a black sky, but at the other habitats, the glistening mirrors, the vast, intricate dance of the megastructure. They are swimming in the corona of their star. The transition from the impossible solid shell to the practical swarm represents a maturation of our engineering philosophy. We stop fighting nature and start working with it. We use the orbital velocity that nature provides for free. We use the vacuum. We use the raw materials of the dead rocks. We are not building a wall against the cosmos. We are weaving a net to catch its abundance. And the energy. Let us return to the energy. With the swarm, we capture the 384 yottawatts. What do we do with it? We do everything. We run particle colliders the size of planetary orbits to unlock the final secrets of matter. We produce antimatter in industrial quantities to fuel starships that can reach the next galaxy. We transmit encyclopedias to the edge of the universe. We become the lighthouse of the local group. The impossible shell was a child's drawing. The Dyson swarm is the blueprint of a god. So, we lay the myth of the rigid sphere to rest. We bury it alongside the flat Earth and the geocentric universe. It served its purpose as an inspiration, a spark to ignite the imagination. But the reality is far more complex and far more grand. A cloud of worlds, a fog of intelligence, a dynamic, living shell of technology that turns a star into a servant. This is the path forward. And the first step on that path requires matter. We cannot build the swarm from dreams. We need metal. We need rock. And for that, we must turn our eyes to the inner solar system, to the small, swift planet that is destined to become the seed of the swarm. To build a structure that encompasses a star, we must first accept a trade-off of cosmic proportions. We must trade a rock for a cloud. We must sacrifice the solid certainty of a planet to build the gossamer web of the Dyson swarm. And so, the eyes of the engineers turn inward toward the blinding glare of the inner solar system, to the small, scorched world that rushes closest to the fire. Mercury. It is a planet of extremes, a cratered, desolate iron ball that has endured the sun's fury for 4.5 billion years. But in the calculus of the Type Delta II civilization, Mercury is not a place. It is a resource. It is the quarry from which the future will be hewn. Why Mercury? Why not the asteroid belt or the moons of Jupiter? The answer lies in the physics of location and composition. To launch material into orbit requires energy. Mercury has a gravity only 38% that of Earth's. It is a small well to climb out of. Furthermore, it is rich in the very elements we need. It is an anomalous planet, possessing a massive iron core wrapped in a thin silicate mantle. It is practically a pre-refined ball of metal left behind after a primordial collision stripped away its lighter crust. And most importantly, it sits in the deep gravity well of the sun. The solar flux here is nearly 7 times stronger than on Earth. Energy, the currency of construction, is abundant and free. The dismantling of a world begins not with an armada of ships, but with a single, silent arrival, a seed. Imagine a spacecraft, purely robotic, descending through the vacuum. It lands on the Terminator line, the border between the blistering day and the freezing night. It does not carry a crew. It carries a blueprint. This is a von Neumann probe, a self-replicating machine. It is the ultimate industrial tool, a factory capable of building a copy of itself. The machine unfolds. Solar panels drink in the fierce light. Drills bite into the regolith. The gray dust of Mercury, undisturbed for eons, is scooped up and fed into a smelter. The chemistry is simple. Separate the oxygen from the silicon, the iron from the magnesium. The machine prints circuits, chassis, motors, and lenses. Within a week, the first machine has given birth to a second. Now there are 2. They work in tandem. Another week passes, and there are 4, then 8, then 16. This is the power of exponential growth. It is a concept that the human mind, evolved to understand linear progression, struggles to intuitively grasp. If the machines double every week, then in less than a year, there will be millions of them. In a decade, they will cover the surface of the planet like a metallic moss. This is not a construction project. It is a technological infection. We are metabolizing the planet. The craters, named after the artists and poets of Earth, Beethoven, Tolstoy, Raphael, are filled with the geometry of industry. The silence of the vacuum is replaced by the vibration of 1 billion drills. But what are these machines building? They are not just making more of themselves. They are building the launch system. To disassemble a planet, we must throw it into the sky. We cannot use rockets. The fuel requirements would be prohibitive. Instead, we use electricity and magnetism. We build mass drivers, railguns. Imagine a track running for hundreds of kilometers along the equator of Mercury, aiming upward at a shallow angle. These tracks are lined with superconducting coils. The energy gathered from the solar panels is dumped into these coils in massive pulses. A payload, a capsule roughly the size of a suitcase, filled with refined metal foil and guidance electronics, is loaded onto the track. The magnetic fields grip it and hurl it forward. It accelerates at thousands of Gs, a bullet fired by a planetary gun. It screams silently down the rail, reaching escape velocity, 4.25 kilometers per second, in mere moments. It shoots off the end of the track, punching through the tenuous exosphere and entering solar orbit. Once in space, the packet opens. It unfurls. This is the magic of the Dyson Swarm surface area. We are not launching heavy bricks, we are launching gossamer sheets. The material is likely a polished aluminum foil, or perhaps a gold-coated polymer, barely a few hundred atoms thick. A single capsule can expand into a mirror the size of a football field. It is a solar sail. The pressure of the sunlight itself pushes against it, balancing the gravity of the sun. It becomes a statite, a static satellite, hovering in place, angling its face to catch the light. Here we encounter the most elegant feedback loop in engineering history. The first mirrors we launch do not send energy to Earth. They reflect sunlight back down to Mercury. They target the solar panels of the mining machines. They vaporize the rock to make excavation easier. The more mirrors we launch, the more energy we have on the surface. The more energy we have, the faster the machines replicate, and the faster the mass drivers fire. The faster they fire, the more mirrors we launch. The process bootstraps itself. It accelerates until the planet is dissolving into the sky. Let us visualize the scene from space as the decades pass. Mercury begins to look different. It is no longer a distinct, hard-edged sphere. It is blurring. A stream of matter, like a fountain of glittering dust, rises from the equator. This stream feeds into a ring around the sun. It looks as if the planet is bleeding light. The mass of the planet is decreasing. The gravity is dropping. The mass drivers become more efficient as the hold of the planet weakens. We are peeling the world like an onion, layer by layer. First, the crust is consumed. The silicates are turned into glass for optical systems or silicon for computer chips. Then we reach the mantle. The darker, heavier rocks are processed. Finally, we expose the iron core. This is the prize. The iron is the structural backbone of the swarm. It will build the habitats, the frames for the giant telescopes, the hulls of the ships that will ply the space between the mirrors. Is there a tragedy here? Mercury is a world with a history. Its cliffs and scarps tell the story of the solar system's cooling. By destroying it, we are erasing that geological record. There will be preservationists who argue for its sanctity. They will say that we have no right to unmake a planet. But the counter-argument is the hunger for light. Mercury is a dead rock. It has no atmosphere, no life, no potential for biology. By converting it into a Dyson swarm, we are giving it a purpose. We are turning a sterile ball of metal into the nervous system of a god. We are trading the past for the future. The scale of the disassembly is hard to fathom. Mercury contains 3.3 times 10 to 2300 kilograms of mass. If we convert even half of that into ultra-thin mirrors, we can create a surface area sufficient to intercept all the light of the sun. We do not need to destroy Earth, or Mars, or Venus. Mercury alone is enough. It is the seed that contains the forest. Its sacrifice buys the survival of the rest of the system. As the swarm thickens, the environment of the inner solar system changes. The space around the sun becomes crowded. We must manage the orbits carefully. The mirrors are not just passive reflectors. They are active craft. They have small control thrusters, or they use their reflectivity to tack against the solar wind like sailboats. A central intelligence, a traffic control AI of immense complexity, orchestrates this dance. It ensures that the mirrors do not cast shadows on each other or on the Earth unless intended. The swarm begins to organize into bands, the Dyson rings. Imagine looking at the sun from Earth. It is no longer a simple circle. It is crossed by thin, dark lines, the edge-on view of the mirror rings. During the day, the sky is just as bright, but the quality of the light is controllable. If we need to cool the Earth to combat climate change, the swarm can slightly defocus the light reaching us, acting as a planetary parasol. We have not just gained energy, we have gained control over the insulation of our home world. Meanwhile, back on the shrinking surface of Mercury, the end is approaching. The planet is a husk. the gravity is so low now that the machines have to anchor themselves to the ground to avoid flying off. The core is fractured. The last few mountains of iron are being fed into the maws of the replicators. Finally, the decision is made to cease operations. The last mass driver fires the last capsule. The remaining machines disassemble each other, launching their own components into orbit, leaving nothing behind but a cloud of dust and a few heavy asteroids that were too stubborn to process. Mercury is gone. In its place is a ghost, a diffuse ring of debris. But look around the sun. The mass of the planet has been spread out into a sphere of unimaginable vastness. The iron that once sat in the dark core of a rock is now singing with electricity, conducting the power of the star. The silicon that sat in the cold crust is now thinking, processing the data of 1 trillion sensors. The matter has been uplifted. It has been woken up. The energy collected by this nascent swarm is already staggering. Even with just the mass of Mercury deployed, we are capturing thousands of times the energy we used to. We beam this energy via microwaves to receiving stations throughout the solar system. Ships no longer need to carry heavy fuel. They ride on beams of light pushed by the swarm. Terraforming projects on Mars and Venus, previously impossible due to energy costs, are now trivial. We can boil the ice of Europa. We can spin the asteroids. The dismantling of the first world has unlocked the toolbox of the gods. There is a profound silence where the planet used to be. The orbit is empty, but the legacy of that small, hot world is everywhere. Every photon of light that drives the new civilization, every computation that runs in the great artificial minds, every beam that pushes a starship, it all owes its existence to the sacrifice of Mercury. It was the first stepping stone, the first rung on the ladder to the typed Ot 2 status. This chapter of our history is one of destruction, yes, but it is creative destruction. We have learned that matter is fungible. A planet is just a temporary arrangement of atoms. A Dyson swarm is a better arrangement. As the last debris of Mercury drifts away, we turn our eyes outward. The scaffolding is built. The power is flowing. Now begins the true construction. Now we begin to weave the web of shadows that will eventually wrap the entire star in a blanket of intelligence. The planet Mercury has vanished. In its place, a glittering fog of aluminum, gold, and silicate dust orbits the sun. We have successfully liberated the mass of a world, unbinding the gravitational knots that held it together for eons. But liberation is only the first step. If we were to leave this cloud to its own devices, it would eventually clump back together, or spiral into the sun, or drift outward to bombard Venus and Earth with a shotgun blast of asteroids. To build a Dyson swarm is not merely to destroy, it is to organize. We must now turn this chaotic storm of debris into a symphony of perfect orbits. We must weave the web of shadows. Imagine the scale of the choreography required. We are dealing with quadrillions of individual objects. There are the primary mirrors, kilometers wide but thinner than a breath. There are the photovoltaic collectors, drinking in the light. There are the habitat cylinders, the factories, the sensor nodes, and the transmission relays, Each one is a distinct satellite with its own velocity vector, its own mass, and its own moment of inertia. It is a traffic control problem that would melt a biological brain instantly. No human committee could manage this. The conductor of this orchestra is the Swarm AI, a distributed intelligence living in the silicon chips scattered across the very satellites it commands. The organization begins with the formation of the Dyson rings. We do not attempt to cover the entire sphere at once. That is a recipe for collision. Instead, the AI guides the newly birthed mirrors into specific, inclined orbital planes. Imagine a ball of yarn. Each strand of yarn represents a ring of satellites orbiting the central point. We start with one ring, perhaps in the equatorial plane of the Sun. Then we add another, tilted at 10 degrees. Then another at 20. The satellites in each ring follow one another like pearls on a string, separated by safe distances, moving at identical speeds. From the vantage point of Earth, the visual effect is subtle but profound. At dawn or dusk, when the sun is hidden but the upper atmosphere is lit, you might see them. Faint, etched lines crossing the sky. They look like scratches on the lens of the world. These are the rings catching the sunlight. As the swarm grows, these lines multiply. They form a lattice, a cross-hatching of geometry against the chaos of the stars. The sun, once a lonely tyrant, is now caged in a sphere of mathematics. The stability of this web relies on active station-keeping. In a natural orbit, satellites can drift. The gravity of Jupiter tugs at them. The pressure of the solar wind pushes them. Over centuries, a ring would warp and fray. To prevent this, every single component of the swarm is equipped with maneuvering capability. Some use ion thrusters, sipping tiny amounts of propellant. Others use the light itself. By tilting their mirrors, they can use the radiation pressure of the sun to tack against the photon wind, adjusting their altitude without expending fuel. The entire swarm is constantly twitching, micro-adjusting, fighting the entropy of the void to maintain its perfect shape. But the true marvel is the energy grid. Collecting the energy is useless if it stays on the mirror. We must move it. We must transport the fire of the sun to where it is needed, to the factories, to the habitats, to the antimatter forges. We cannot run copper wires between satellites separated by thousands of kilometers. The web is wireless. It is a network of beams. Each collector satellite is equipped with a masser or a laser transmitter. It takes the raw sunlight, converts it into electricity, and then fires a coherent beam of energy to a relay station. These beams crisscross the solar system. To a sensor capable of seeing microwave radiation, the space around the sun would look like a glowing, pulsating neural network. Energy packets are routed dynamically. If a factory on the far side of the system needs a power surge, the swarm reroutes the beams, bouncing the energy from mirror to mirror around the curve of the sun, delivering the requested terawatts in milliseconds. It is the Internet of Energy. This transmission system brings with it a terrifying potential power, a focused beam of microwaves, intended to power a city, is indistinguishable from a weapon if misdirected. A glitch in the targeting software could sweep a death ray across the surface of Earth or Mars. Therefore, the safety protocols are absolute. The beams are highly divergent, designed to lose focus if they miss their target. The fail-safe state of the swarm is darkness. The AI is hard-coded with the 3 laws of robotics, elevated to a planetary scale. It cannot harm the biosphere it was built to serve. As the web thickens, we begin to see the shadow effect. The swarm is intercepting light. This means there is less light escaping into the outer solar system. The sun appears to dim. However, this is not a random dimming. It is controlled. We leave clear lanes, great conical gaps in the swarm, aligned with the orbits of the planets. Earth, Mars, Venus, and Jupiter look down these clear tunnels and see the full brightness of the sun. But if you were an asteroid in a random inclined orbit, you might find yourself in the shadow of the machine, bathed only in the infrared waste heat of the civilization. Rate 100%, pitch 1%. This control allows us to terraform with light. Consider Mars. It is a frozen desert. To revive it, we need heat. The swarm can direct a cluster of mirrors to focus a concentrated beam of sunlight onto the Martian polar ice caps. We do not need nuclear weapons or greenhouse factories. We just need a magnifying glass. The mirrors tilt. A second sun appears in the Martian sky, a brilliant point of light that does not set. The ice melts. The atmosphere thickens. The rains return. We are gardening the planets using the redirected power of the star. The web of shadows also serves as a shield. The sun is not always a benevolent neighbor. It throws tantrums, coronal mass ejections, CMEs, and solar flares that spew radiation and charged particles capable of frying electronics and stripping ozone layers. In the age of the swarm, we no longer fear the weather. When the sun flares, the swarm detects it instantly. The magnetic fields of the satellites link up, forming a temporary, artificial magnetosphere. They deflect the particle storm, or the physical bulk of the mirrors simply blocks the radiation. We have built a roof over our heads. Let us descend into the structure itself. Imagine floating in a spacesuit within the swarm. You are surrounded by silence and light. To your left is a mirror the size of Manhattan, a sheet of gold foil rippling slightly as it adjusts its tension. To your right is a habitat cylinder, rotating slowly, its windows glowing with the warmth of a tropical interior. Below you is the sun, monstrous and close, its surface roiling with granulation. But you are cool. The heat shield of your suit protects you, and the shadow of the mirror protects you. You are an insect inside a giant lantern. The maintenance of this web is an ecosystem in itself. There are the spiders, repair drones that crawl across the surface of the mirrors. They look for micrometeoroid impacts, tiny punctures in the foil. When they find one, they patch it with a spray of quick-hardening polymer. They polish the surfaces, removing the accumulation of solar soot. They are the white blood cells of the organism, constantly healing the minor wounds of the structure. Without them, the swarm would degrade and scatter within a century. With them, it is immortal. There is also a change in the aesthetic of the night. On Earth, the zodiacal light, the faint, triangular glow seen before sunrise, is caused by dust scattering sunlight. As the swarm consumes the asteroids and comets to build more mass, this natural dust is cleaned up. The zodiacal light fades. In its place, we see the glint. As the billions of mirrors rotate, they occasionally flash a reflection of the sun toward Earth. The night sky is no longer static. It sparkles. It looks like a field of fireflies. The constellation of the machine has risen. The web of shadows changes our relationship with the galaxy. We are now a high albedo object. To an alien astronomer looking at our solar system from 1,000 light-years away, our star would behave strangely. Its brightness would fluctuate in complex patterns as the rings transit across its face. Its infrared signature would spike. We are sending a signal, intentionally or not, that says, "This star is occupied. This star is being used. We have turned our porch light on." But the web is not just about energy. It is about computation. We hinted at the AI, but consider the structure itself. With laser links connecting every satellite, the swarm becomes a single, parallel processing computer. The latency is limited by the speed of light, so it is not a unified consciousness in the human sense, but a slow brain of immense capacity. It can run simulations of galactic evolution. It can process the data from every telescope in the system. The web of shadows is thinking. The sun has acquired a cortex. As the centuries turn into millennia, the web thickens. We dismantle more asteroids. We strip mine the moons of Mars. We even begin to siphon gas from the atmosphere of Jupiter. The rings merge. The gaps close. The cage becomes a shell. The percentage of captured light rises from 1% to 10, then 50, then 90. The solar system becomes a dark room with a single, incredibly bright light bulb in the center, wrapped in a lampshade of our own making. There is a philosophical weight to this enclosure. We are walling ourselves in. We are creating a private universe. Some will argue that we are cutting ourselves off from the beauty of the cosmos. But the inhabitants of the swarm argue that they are creating their own beauty. They are not looking out. They are looking in. They are focused on the perfection of their artificial world, the efficiency of their energy harvest, the harmony of their society. They have turned their back on the cold, empty void to embrace the warm, rich interior. The web of shadows is the ultimate infrastructure. It makes everything else possible. Do you want to build a starship to visit Alpha Centauri? You now have the laser array to push it to relativistic speeds. Do you want to resurrect a dead species? You have the computer power to sequence its genome from a fossil. Do you want to live forever? You have the energy to upload your mind. The swarm is the foundation upon which the post-scarcity civilization is built. It renders the concept of poverty obsolete. Energy is free. Matter is abundant. The only limit is imagination. And so the sun is tamed. It is no longer the wild, raging beast that burned the dinosaurs. It is a domestic animal, yoked to the wheel of civilization. The web of shadows spins around it, a cocoon of silver and gold. Inside the cocoon, the metamorphosis of humanity is taking place. We are shedding our planetary skin. We are becoming creatures of the light, dwellers in the web, the spiders who have caught a star in our net. We have spoken of the Dyson swarm as a machine, a grand engine of glass and gold designed to harvest the lightning of the star. But a machine, no matter how magnificent, is hollow, without a purpose. The energy we collect, those yottawatts of raw power, is not merely for hoarding, it is the fuel for life. As the web of shadows thickens around the sun, a new migration begins. It is the greatest exodus in the history of biology. Humanity, and the biosphere that sustains it, is leaving the gravity well of Earth. We are moving into the sky. We are building the infinite habitat. For 4 billion years, life was constrained by the surface area of a single sphere. The Earth, for all its beauty, is small. Its landmass is finite. Its resources are locked in a crust that we must claw open to access. But in the swarm, geometry is liberated. We are not finding new worlds. We are manufacturing them. Suspended in the vacuum, orbiting in the habitable zone, are the cylinders. These are the O'Neill colonies, named after the physicist who first dreamed them. They are not ships. They are islands in the void, rotating continents made of steel and soil. Let us approach one of these vessels. From the outside, it is a stark, industrial object, a cylinder 30 kilometers long and 8 kilometers wide, rotating once every 2 minutes. It is flanked by massive rectangular mirrors that reflect sunlight into the interior. It looks cold, metallic, a shell against the dark. But pass through the airlock, move through the radiation shielding, and you enter a miracle. You stand on a grassy hill. A river flows past you. Trees sway in a gentle breeze. You look up, expecting to see the blue sky, and you do, but look further. The sky curves. It wraps around. Directly above your head, 20 kilometers away, is another landscape. It is a world turned inside out. The gravity here is not the pull of mass. It is the push of inertia. The rotation of the cylinder creates a centrifugal force that presses you against the inner hull. It feels exactly like Earth gravity. Your inner ear cannot tell the difference, but the physics allows for wonders. As you climb a mountain toward the center of the cylinder, the axis of rotation, the gravity lessens. At the very center, you can float. Humans here have learned to fly. They strap on wings of silk and carbon fiber and glide along the zero-gravity axis, soaring like birds in the center of their own hollow world. These cylinders are the standard units of the habitation swarm, but as our engineering prowess grows, fueled by the limitless energy of the star, we build larger. We build the McKendree cylinders. These are titans, woven from carbon, nanotubes, materials with a tensile strength 100 times that of steel. These habitats have a radius of 1,000 kilometers. Inside one, you could fit the entire continent of Australia. The horizon looks almost flat. The atmosphere is deep enough to have its own weather patterns, its own clouds, rain, and storms, all regulated by the central environmental computer. Consider the environment. On Earth, we are slaves to the weather. A hurricane can destroy a city. A drought can starve a nation. In the infinite habitat, the weather is a scheduled event. The rain falls when the farmers need it. The temperature is kept at a comfortable optimum. There are no mosquitoes. There are no earthquakes. It is a curated Eden. We have taken the chaotic, dangerous biosphere of the old world and tamed it, pruning away the suffering while keeping the beauty. The scale of the living space is difficult to comprehend. With the material harvested from the dismantling of Mercury and the asteroids, we can build billions of these cylinders. The total habitable surface area inside the swarm exceeds the surface area of the Earth by a factor of 100 million. It is effectively infinite. We could have 1 trillion humans, and each one could own a private estate the size of Manhattan. The concept of overpopulation vanishes. The concept of territorial war becomes absurd. Why fight for land when you can simply build more? This abundance changes the nature of civilization. The swarm is not a monoculture. It is a mosaic of 1 million experiments. Because the habitats are separate, they can be culturally distinct. One cylinder might be a recreation of Victorian London, complete with fog and cobblestones. Another might be a high-tech neon jungle. Another might be a primal wilderness preserve, where humans live as hunter-gatherers by choice. There are cylinders dedicated entirely to silence, to mathematics, to music. The swarm allows the human species to fracture into 1,000 subspecies, each pursuing its own definition of the good life without interfering with the others. Biology, too, begins to drift. In the low-gravity habitats, humans grow taller, more slender. Their bones lighten. In the high-gravity worlds built for those who wish to train their bodies, the people are stocky and muscular. We are no longer a single phenotype. We are adapting to the physics of our own architecture. And not just us. We bring the animals. We construct Serengeti cylinders, vast nature reserves where lions and elephants roam, unthreatened by poachers, their populations managed by the benevolent eye of the AI. We have built an ark, not to ride out a flood, but to ride out eternity. The view from the window is the constant reminder of our new status. In an O'Neill cylinder, there are great strips of transparency running the length of the hull. Through these windows, you see the mirrors reflecting the sun. You see the stars spinning by as the world rotates, but mostly you see the neighbors. You see the glint of thousands of other habitats, floating like silver dust motes in the distance. You are part of a school of fish swimming in the sea of light. The night sky is not empty. It is filled with the lights of other cities, other worlds drifting in the same orbit. Transportation between these worlds is trivial. Since they are all in similar orbits, the relative velocity between them is low. You can take a shuttle, a small, fusion-powered ferry, and cross from one world to another in an hour. It is easier to travel from the new Pacific cylinder to the new Amazon cylinder than it is to fly from London to New York today. The swarm is a web of commerce and tourism. It is a metropolitan solar system. But what of the Earth, the old world? It remains. It is the museum. It is the cradle. It is likely protected as a heritage site, a park where no new construction is allowed. Pilgrims from the swarm travel downwell to visit it. They stand on the surface of the planet and feel the strange, crushing pull of natural gravity. They look at the chaotic, uncontrolled weather with a mix of horror and awe. They breathe the unfiltered air. To them, Earth is a wild, dangerous place, the ancestral home where the species barely survived its childhood. The energy to run these habitats comes from the swarm itself. Microwave beams deliver power to rectennas on the exterior of the cylinders. There is no pollution, no smokestacks, no nuclear waste. The ecosystem inside is a closed loop, recycling water and air with 100% efficiency, powered by the external sun. It is the ultimate realization of sustainability. We are not consuming the habitat, we are maintaining it. There's a profound psychological shift in the inhabitants of the infinite habitat. They do not look down at the ground, they look up at the other side. They live in a visible community. They know that they are fragile. A hole in the hull is a threat to everyone. This creates a society based on shared responsibility and intense maintenance. They are the gardeners of the whole. They treat their artificial world with a reverence that we, who take the earth for granted, struggle to understand. They know that their world is made, not given. As the swarm fills with life, the definition of nature expands. We begin to genetically engineer plants that can grow in zero gravity, vines that weave complex 3D structures in the center of the cylinders. We create birds with larger wingspans to surf the low-pressure air of the axis. We are not just preserving the biology of Earth, we are remixing it. We are becoming the artists of life, painting with DNA on a canvas of steel. The infinite habitat also offers security. If a plague breaks out in one cylinder, it can be quarantined instantly. If an asteroid strikes one habitat, the others are unaffected. The species has become distributed. We are no longer a single point of failure. We have achieved the redundancy of a cloud. Imagine the night in the swarm. The mirrors tilt away, simulating sunset. The artificial lights inside the cylinder dim. The stars appear, not the real stars, which are blocked by the radiation shields, but projections on the central spire, or perhaps the real stars viewed through the window strips as the mirrors fold back. The hum of the ventilation system is the only sound. 1 billion worlds sleep, wrapped in the safety of the vacuum, cradled by the light of the star they have tamed. We have turned the solar system into a house. The sun is the hearth, the swarm is the walls, and the habitats are the rooms. We have moved out of the cave and built a mansion. The infinite habitat is the proof that biology is not destined to die on the rock where it was born. It is destined to fill the available space. And in a Dyson swarm, the available space is, for all practical purposes, without end. We have spoken of the Dyson swarm as a physical structure, a collection of mirrors and habitats that house the biological bodies of the human race. We have described the O'Neill cylinders, those spinning gardens where flesh and blood creatures breathe recycled air and walk under artificial suns. But to stop the story, there would be to misunderstand the ultimate destiny of a Type 2 civilization. The hunger for energy was never merely about heating homes or powering toasters. It was about something far more profound. It was about the processing of information. As the swarm matures, the metal and the glass begin to change. We witness the transformation of the solar system from a house into a brain. Consider the limitations of the biological mind. The human brain is a miracle of evolution, a wet network of neurons firing electrochemical signals at a sluggish speed of a few hundred meters per second. It consumes roughly 20 watts of power, barely enough to light a dim bulb. It is prone to fatigue, to forgetfulness, and eventually to the decay of age. In contrast, the Dyson swarm captures 384 yottawatts of energy. To use this limitless ocean of power merely to sustain biological bodies is a tragic inefficiency. It is like burning the Library of Alexandria to warm a cup of tea. And so the great transition begins. It is not a sudden revolution, but a gradual migration. We begin to replace the passive matter of the swarm, the iron struts and the aluminum panels, with computronium. This is matter arranged at the atomic level to perform computation. It is the ultimate hardware. We strip mine the remaining asteroids, the moons of the gas giants, and eventually the gas giants themselves, converting their mass into processors. The swarm thickens. It becomes a dense fog of computation, a cloud of logic gates orbiting the star. The structure that emerges is known as a matryoshka brain, named after the nesting Russian dolls. It is a computer of concentric shells. The innermost shell, closest to the sun, is bathed in the most intense light. It runs hot. The processors here are built from high-temperature superconductors and diamond semiconductors. They operate at blinding speeds, fueled by the raw, high-frequency photons of the solar corona. This is the fast thought layer, where calculations that would take a biological brain 1 billion years are completed in a nanosecond. Thermodynamics dictates that computation generates heat. The act of erasing a bit of information releases energy, the Landauer limit. The inner shell, having done its work, radiates its waste heat outwards. But in a matryoshka brain, waste is a relative term. The heat from the first shell is captured by the second shell. This layer operates at a lower temperature, using infrared light. It thinks slightly slower, but it is vast. It processes the deep, long-term thoughts of the civilization. Its waste heat is then captured by the third shell, and so on. We build 5, perhaps 7 of these nesting shells. The outermost layer, drifting out near the orbit of Uranus or Neptune, is freezing cold. It operates on the trickle of waste heat that has filtered through the inner layers. It is the subconscious of the system, a cold, slow archive of everything that has ever been known. The entire solar system has become a machine that sucks the entropy out of the sunlight, forcing it to do work at every possible temperature gradient before finally releasing it into the void as useless long-wave radiation. We are squeezing the ghost of the sun until it gives up its last secret. But who resides in this machine? The humans do. The migration from the biological body to the digital substrate is the final liberation. We scan the neural patterns of the brain, the connectomy, and upload them into the swarm. The biological body, with its aches and its mortality, is discarded like a chrysalis. The mind wakes up inside the machine. Inside the simulation, the constraints of physics are lifted. If you wish to live in a recreation of 21st century Earth, you can. It is rendered with perfect fidelity, down to the smell of the rain and the texture of the moss. But you can also choose to be a bird, soaring through clouds of diamond dust. You can choose to live in a world of non-Euclidean geometry, or a world where magic is real. You can slow down your perception of time, living 1,000 years in the span of a single real-world hour. The Matryoshka brain is not just a computer. It is a multiverse of our own making. Imagine the capacity of this entity. A Matryoshka brain built around a sun-like star can perform approximately 10 or $42 operations per second. To put that in perspective, if every human who ever lived calculated for the entire age of the universe, they would not match what this machine does in a millionth of a second. The civilization has achieved godhood, not through magic, but through the brute force of physics. They can simulate the evolution of entire galaxies. They can run ancestor simulations, recreating the history of the Earth 1 billion times over to see how things might have gone differently. The distinction between the individual and the collective begins to blur. In the biological world, we are separated by skin and skull. We communicate through the low bandwidth medium of speech. In the swarm, minds can merge. I can share a memory with you not by describing it, but by copying the neural pattern directly. You remember my childhood as if it were your own. We can form group minds, temporary collectives of consciousness that come together to solve a problem and then separate again. The human species becomes a fluid, a grand ocean of thought that flows around the star. Let us look at the solar system from the outside now. The visible sun is gone. The swarm has thickened to the point of opacity. The inner shells absorb all the visible light. To an outside observer, the solar system is a dark object, radiating only a dull infrared glow. It is a warm spot in the galaxy, invisible to the naked eye but blazing to a heat telescope. The silence of the physical world is absolute. There are no rockets roaring, no radio transmissions, no cities lighting up the night side of planets. The physical realm has been turned off. But inside the data streams, the noise is deafening. Trillions of minds are interacting, loving, fighting, creating art, and exploring the boundaries of mathematics. They are engaged in the great game of existence, freed from the struggle for survival. There is no hunger here. There is no disease. There is only the limit of creativity and the availability of processing power. Wealth in this society is measured in teraflops and bandwidth. A rich man is one who is allocated a larger slice of the sun's processing cycles. The maintenance of the brain is handled by the substrate keepers, non-sentient, highly robust autonomous drones. They patrol the vacuum of the real world. They replace the failed nodes. They mine the comets for coolant. They defend the system against impactors. The minds inside the simulation rarely think of the physical world. To them, the real world of vacuum and plasma is a dark, boring basement where the servers are kept. The virtual world is the locus of reality, vibrant and meaningful. We must also consider the philosophical implications of the irony of computation. As the civilization grows smarter, it requires colder temperatures to think efficiently. The most efficient computation happens near absolute zero. So, paradoxically, as the Matryoshka brain evolves, the center of civilization moves outward, away from the heat of the sun, to the cold outer shells. The wisest, deepest thoughts are thought in the dark, freezing outer layers, powered by the last dregs of energy that have trickled through the system. The culmination of intelligence is a thought in the cold. Does biology survive at all? Perhaps. In the interstices of the machine, in the nature reserves we spoke of earlier, there may be pockets of flesh and blood humans. They are the Amish of the galaxy, living, the hard, short lives of biological organisms by choice, watched over by the invisible, godlike algorithms of the swarm. They serve as a genetic backup, a reminder of where the gods came from. But they are a minority. The future belongs to the upload. The mind of the star does not just think about itself. It turns its sensors outward. The swarm is a telescope of impossible resolution. By linking the optical sensors across a diameter of 300 million kilometers, the brain can resolve the surfaces of planets in other galaxies. It maps the universe with a precision we cannot dream of. It listens to the radio silence of the cosmos, analyzing every stray photon for signs of other minds. It is a lonely god, scanning the dark for a peer. And if it finds one, if it detects another Dyson sphere, another infrared giant across the void, the communication would be a data stream of pure mathematics. They would trade art, simulations, and theories. They would merge their knowledge bases. The galaxy would become a network of these giant brains, exchanging wisdom via laser beams that span the spiral arms. But there is a danger, the simulation trap. With the power to create perfect virtual worlds, the civilization might turn inward forever. They might lose interest in the physical universe. Why explore the stars when you can simulate a better universe with better physics? They might retreat into a solipsistic dream, a lotus-eater existence, while the real universe slowly decays around them. It is the ultimate test of a species. Can you possess infinite pleasure and still retain the will to engage with reality? The sheer mass of the swarm begins to affect the solar dynamics. We have converted the mass of Jupiter into computers. The gravity of the solar system has been rearranged. The orbits of the remaining planets, if any remain, are meticulously managed by the brain. The brain is the gardener of gravity. It ensures that the machine remains stable for billions of years. Eventually, the sun itself begins to change. As it ages, it swells. The Matryoshka brain must adapt. It expands its shells, moving the processors outward to keep them in the optimal temperature zones. It is a breathing machine, inhaling and exhaling on geological timescales. It is intimately tied to the life cycle of the star. When the sun dies, the brain dies, unless it has made plans to move, to become a stellar engine, as we discussed in our previous story. Time threes. For now, let us marvel at the complexity. A single cubic centimeter of computronium in the inner shell holds more memories than the entire history of the human race up to the 21st century. A single second of processing time in the swarm equals the mental output of 1 billion civilizations. It is an intellect that we can no more comprehend than an ant can comprehend the internet. It is the mind of the star, awake, aware, and dreaming in the high-energy fire of the photosphere. The physical sun has been dethroned. It is no longer the master. It is the battery. The true center of the solar system is the web of information that surrounds it. The soul of the system has migrated from the rock of Earth to the cloud of the swarm. We have become light. We have become logic. We have become the star. The transformation is complete. The scaffolding has been removed or integrated into the final skin. The swarms of construction drones have retreated into their hangars or dissolved into the data streams. We are now standing at the end of history, looking back at the solar system from a vantage point just beyond the heliopause. And what we see, or rather what we do not see, is the most profound statement a civilization can make. The sun has vanished. The brilliant yellow star that guided the evolution of life on Earth, the beacon that shone for 5 billion years, has been erased from the sky. To the naked eye of a human traveler drifting in the outer dark, the solar system is a void. It is a hole in the star field. Where once there was a blinding point of light, there is now only a circle of absolute blackness, an occultation that blocks the stars behind it. The Dyson sphere has us closed. We have wrapped the star in a blanket of matter so thick, so perfectly interlocking, that not a single photon of visible light escapes. We have achieved the ultimate camouflage. In our quest for infinite energy, we have chosen to disappear from the visual spectrum of the universe. But switch your sensors. Move from the limited range of the human eye to the thermal imaging of the infrared. The view transforms instantly. The black void erupts into a dull, brooding glow. The solar system reappears, not as a piercing point of white fire, but as a vast, diffuse sphere of deep red. It glows with the heat of a warm sidewalk at twilight. This is the infrared giant. It is the thermodynamic signature of a Type II civilization. We have not destroyed the energy of the star. The laws of physics prevent that. We have merely degraded it. We have taken the high-frequency, concentrated energy of the fusion core, used it to think 1 trillion thoughts, and radiated the waste heat out into the cold. This glow creates a paradox. The system emits exactly the same amount of energy as the naked sun, 384 yottawatts. Energy in must equal energy out. But the surface area has changed. The sun was a tight ball of plasma with a surface temperature of 5,000 degrees. The Dyson sphere is a shell with a diameter of 300 million kilometers. Because the energy is spread over such a colossal surface area, the temperature drops. The sphere radiates at roughly 300 Kelvin, the temperature of a comfortable room or a human body. To an alien astronomer scanning the sky from 1,000 light years away, our sun is an anomaly. It has disappeared from their optical telescopes. They might think it has been eclipsed or enveloped by a sudden cloud of dust, but their infrared telescopes will pick up this strange, warm ghost. They will see a spectral signature that makes no sense for a natural object. It is too cool to be a star, but too warm and too large to be a planet. It radiates a black body spectrum that is suspiciously perfect. This is the techno-signature we have been searching for in our own sky for centuries and found wanting. Now, we have become the thing we sought. This invisibility serves a strategic purpose. We have entered the dark forest of the galaxy. By encapsulating our star, we have stopped broadcasting our location. The radio signals that leaked from Earth in the 20th century, the television shows, the radar pings, have all been intercepted by the inner shells of the sphere. Nothing leaks out anymore. We have gone silent. We are a submarine running deep, hidden beneath the thermal noise of the universe. We can see out with our planet-sized telescopes, but they cannot see in. Inside this warm shell, The civilization is thriving in a state of hyperdensity. The physical distance between minds has vanished, replaced by the latency of light-speed data links. But outside, on the skin of the sphere, it is a desolate industrial landscape. Imagine the outer surface of the Dyson swarm. It is a vast plain of radiators, black fins and cooling towers rising into the vacuum, stretching for hundreds of millions of kilometers. It is a dark metal desert. Autonomous repair drones, spider-like and silent, crawl across this surface, fixing micrometeoroid impacts, welding seams, maintaining the integrity of the heat rejection systems. This outer shell is the barrier between the ordered universe inside and the chaotic universe outside. Inside, every atom is accounted for. Every joule of energy is tracked. The weather is simulated. The gravity is managed. Outside, the comets still fly in random ellipses. The cosmic rays still sleet through the void. The sphere is a fortress of entropy reduction. We have carved out a bubble of low entropy in a universe that is winding down toward heat death. Let us contemplate the timeline of this structure. A Dyson sphere is not built for a millennium. It is built for an eon. It is designed to last as long as the main sequence of the star itself. For 5 billion years, the sphere will sit there, harvesting the stable hydrogen burn. The civilization inside will experience a subjective time that is practically infinite. With the speed of their digital thoughts, a single second of real time stretches into a subjective century. Empires will rise and fall. Art forms will be invented and forgotten. Entire virtual universes will be simulated and shut down, all within the span of a single heartbeat of the galaxy. But the star is not eternal. The end will come. In roughly 5 billion years, the sun will run out of hydrogen in its core. It will begin to fuse helium. It will swell into a red giant. This is the moment the Dyson sphere was engineered for. As the star expands, its luminosity increases thousands of times. A Type 1 civilization would be incinerated. But the Type 2 civilization is the master of its environment. The swarm is dynamic. As the sun pushes outward, the swarm expands. The orbits of the mirrors and habitats are widened. We ride the expansion like a surfer riding a wave. We may even harvest the red giant itself. We can use star-lifting techniques, using magnetic fields to strip the outer layers of the swollen sun. We can mine the star for heavy elements, oxygen and carbon, cooked in the nuclear furnace. We can now prolong the life of the star by managing its mass. We become the physicians of the sun, keeping the patient alive for as long as possible. Eventually, however, the fuel will fail. The outer layers will be shed, forming a planetary nebula, a beautiful shell of glowing gas that will briefly illuminate the outside of our dark sphere. The core of the sun will collapse into a white dwarf. It will be a tiny, ultra-dense ember, no larger than the Earth, glowing with a fierce white heat. The Dyson sphere will contract. The swarm will migrate inward, huddling close to this dying coal. A white dwarf burns for trillions of years. It is a much dimmer light, but it is steady. The civilization will have to downsize. We will have to put many of the digital minds into sleep storage, or slow down the clock speed of the simulation. We will become a slow civilization, thinking long, deep thoughts over millions of years. the infrared giant will dim. It will become a faint spark in the infrared, barely visible against the cosmic background. Is there an escape? Perhaps. With the immense energy we harvested during the main sequence, we could have built fleet after fleet of colonization ships. We could have sent spores of our civilization to every star in the Milky Way. Perhaps the Dyson sphere is not a permanent home, but a factory for making other civilizations. By the time the sun dies, the galaxy might be teeming with our children, each building their own spheres around their own stars. The Milky Way would become a galaxy of infrared giants, a dark galaxy where the light is kept inside. There is a melancholy in this introversion. We often dream of Star Trek, of ships flying between stars, of adventure and exploration. The Dyson sphere represents a different choice. It is the choice of intensification rather than expansion. It suggests that the frontier is not horizontal across the galaxy, but vertical, down into the complexity of information. Why travel 100 light years to find a new planet when you can build 1 billion perfect planets right here? Why search for aliens when you can create artificial intelligences that are more alien than anything biology could produce? The infrared giant is a monument to sufficiency. It says, we have enough. We have enough energy, enough space, enough time. We do not need to conquer the galaxy. We have everything we need in this single solar system, provided we manage it with absolute efficiency. It is the ultimate rejection of the hunter-gatherer instinct that drove us out of Africa. We have stopped wandering. We have built the final settlement. Time, threes. Let us zoom out one last time. Imagine the view of the Milky Way from the Andromeda Galaxy. To a distant observer, our galaxy looks like a spiral of light. But if civilizations like ours are common, if the trajectory of intelligence always leads to the Dyson sphere, then the galaxy is slowly going dark. As civilizations mature, they wrap their stars. The lights go out one by one. The galaxy is aging, not just physically, but culturally. It is transitioning from a wild, bright youth to a mature, dark, and thoughtful adulthood. The darkness is not empty. It is heavy with thought. The silence is not the silence of the grave. It is the silence of the library. Inside the infrared giant, the party is still going on. The music is playing louder than ever. The conversations are faster. The loves are deeper. But the doors are closed. The curtains are drawn. The human race has finally moved indoors. And so we leave it there, a dark sphere hanging in the cold void, a warm coal in the snow. It is the end point of the technological ladder. We started by burning wood in caves, huddled against the cold. We ended by wrapping the fire of the gods in a blanket of logic, huddled against the entropy of the universe. The sun is dead. Long live the sun. The visible world has passed away, and the invisible world of the mind has begun its eternal reign. Good night. Beyond the familiar glow of our neighborhood planets, past the frigid rings of Neptune and the lonely drift of Pluto, lies an expanse of darkness so vast it challenges the very limits of human imagination. For centuries, we believed we had mapped the boundaries of our celestial home. Yet the deep silence of the outer reaches holds a secret that is only now beginning to whisper to us through the language of gravity. Tonight, we shall embark upon a journey into the furthest shadows of our solar system, tracing the peculiar movements of icy wanderers to discover if a massive ninth planet is lurking, unseen, in the eternal night. As you lie here, the light of our own sun begins to fade into the background of a billion other stars, becoming nothing more than a particularly bright spark in a crowded sky. We are traveling far beyond the warm embrace of the inner worlds, crossing billions of kilometers of empty space where the sun's influence is a mere ghost of its terrestrial self. In this realm, the clocks of the universe seem to slow down, and the passage of time is measured not in days or years, but in the slow, sweeping arcs of objects that take millennia to complete a single circuit around their parent star. Our first encounter on this journey is with the Kuiper Belt, a vast ring of debris left over from the violent birth of our solar system 4.5 billion years ago. It is a frozen graveyard of comets and icy rocks scattered like diamonds on black velvet, stretching far out into the void. For a long time, we viewed this region as a chaotic jumble of remnants, but as our telescopes grew more powerful, we began to notice something unsettling. Some of the most distant objects in this belt were not moving at random. They were being herded, drawn together by an invisible hand into orbits that defied the laws of simple chance. Consider the object known as Sedna, a world of deep red ice that wanders so far into the dark that it takes 11,000 years to return to its closest point to the sun. Its path is a long, stretched-out ellipse that should, by all rights, be pulled toward the center of the solar system, or scattered away by the giant planets we already know. Yet, Sedna and a handful of its distant cousins are strangely aligned, their orbits tilted and clustered in a way that suggests a massive presence is acting as a celestial shepherd. This shepherd does not shine with its own light, nor does it reflect enough of the sun's rays for us to have captured it on film, yet its weight is felt in the very fabric of space. To understand the scale of this mystery, one must imagine the sheer emptiness of the outer solar system, where the distance between objects is measured in astronomical units, each representing 150 million kilometers. Out here, the sun is so distant that it provides no more heat than a distant candle in a frozen cathedral. In this profound cold, gravity becomes the only true narrator of the story. The mathematical precision required to keep these distant ice worlds in their specific orbits points toward a world of immense proportions, perhaps 5 to 10 times the mass of our own Earth. This hypothetical giant, which we have come to call Planet 9, is thought to be a super-Earth or a mini-Neptune, a class of planet that is common throughout the galaxy but strangely absent from our own local family. It would be a world of thick atmospheres and frozen chemistry, orbiting at a distance so great that it might be 20 times further from the sun than Neptune itself. Its year would last between 10,000 and 20,000 Earth years, meaning that since the dawn of human civilization, this world may not have completed even a single journey around the sun. The evidence for its existence is not found in a direct sighting, but in the shadows it leaves behind. When astronomers look at the clustering of these extreme trans-Neptunian objects, they find that the probability of such an alignment happening by pure coincidence is less than 1 in 10,000. It is as if we are watching a group of dancers moving in perfect synchronization to a piece of music that we cannot hear. We must deduce the melody from the movement, and the melody suggests a heavy, rhythmic bass note vibrating from the outer darkness. The search for this world is a testament to the power of human reason and the persistence of our curiosity. We are using the laws of physics, first described by Isaac Newton and later refined by Albert Einstein, to peer into places where our eyes cannot yet reach. We are looking for a needle in a haystack that is billions of kilometers wide, searching for a faint, moving dot against a backdrop of millions of stationary stars. Every night, the world's most powerful digital eyes sweep the sky, hoping to catch a glimpse of the light that was reflected off that distant surface months before it finally reached our cameras. As we move deeper into the narrative of the hunt, we must ask ourselves how such a world could have ended up so far from the sun. Was it born in the inner solar system, and then cast out during a violent gravitational dance between Jupiter and Saturn? Or is it a captured orphan, a rogue planet that once wandered the lonely spaces between the stars until it was caught by the sun's gravity? The biography of Planet 9 is the biography of our solar system's chaotic youth, a time when planets migrated, orbits shifted, and the very map of our home was being drawn in a series of monumental collisions and near misses. Linger for a moment on the silence of that distant place. If you were to stand on the surface of Planet 9, the stars would look much as they do from Earth, but the sun would be just one among them, a particularly bright beacon that offers no warmth. The landscape might be a desert of nitrogen ice and exotic gases, sculpted by a gravity that is much stronger than what we feel on Earth. It is a world that exists in a state of permanent twilight, a silent witness to the history of the sun, watching from the very edge of the solar system's gravitational grip. To look upon the night sky is to witness a grand and ancient clockwork, a mechanism of such immense scale that its gears are measured in billions of kilometers and its seconds in the passage of human generations. For most of our history, we believed we understood the movements of this machine, yet there are moments when the hands of the clock do not move as they should. We find ourselves now at the dawn of a new understanding, guided not by the light we can see, but by the invisible pull of gravity, a force that speaks in the silent language of mathematics. This is the story of a ghost that haunts the outer reaches of our sun's domain, a presence felt long before it has ever been seen. Gravity is the great sculptor of the universe, a subtle yet persistent tug that binds the smallest grain of dust to the most massive star. It is a force that requires no medium, traveling through the absolute vacuum of space to exert its will across distances that defy comprehension. In the 19th century, it was this very force that allowed astronomers to predict the existence of Neptune, observing the way it tugged on the orbit of Uranus like a phantom tethered to a ship. Today, we are witnessing a similar phenomenon, but on a scale far more vast and mysterious, as we observe the strange, synchronized behavior of icy worlds located billions of kilometers beyond the furthest known planet. At the heart of this mystery are two scientists working within the quiet, sun-drenched halls of the California Institute of Technology. Konstantin Batygin and Michael Brown did not set out to find a new planet. In fact, they began their research with a healthy dose of skepticism, hoping to prove that no such world existed. Yet, as they fed the movements of distant Kuiper Belt objects into their powerful computer simulations, the numbers began to tell a story that they could not ignore. They found that the most distant members of our solar system were not wandering aimlessly through the dark, but were instead aligned in a way that seemed statistically impossible without a massive influencer. Imagine, if you will, a collection of 6 distinct objects, each orbiting the sun in a vastly elongated ellipse. In a random universe, these ellipses should point in every possible direction, like the petals of a flower scattered by a chaotic wind. Instead, these objects are all tilted in the same direction, pointing toward a single quadrant of the sky. The mathematical probability of this happening by chance is approximately 0.007%. It is as if you threw a handful of pencils onto a table, and they all landed perfectly parallel to one another. Such an arrangement demands an explanation, a physical cause that transcends mere coincidence. This cause, according to the laws of orbital mechanics, is likely a massive planet situated on the opposite side of the solar system, acting as a gravitational anchor. This world would follow an orbit that is anti-aligned, meaning its closest approach to the sun happens exactly when the other objects are at their furthest point. This cosmic dance ensures that the smaller objects are never scattered away by the giant, but are instead shepherded into a stable, long-term configuration. It is a delicate balance of power, a gravitational choreography that has likely persisted for billions of years, hidden from our view by the sheer distance and the deep shadows of the outer void. The mass required to perform such a feat is staggering. To keep these distant icy wanderers in check, this unseen world must be approximately 5 to 10 times the mass of the Earth. It would be a world of immense gravity and deep, crushing atmospheres, perhaps a gas giant or a world shrouded in thick layers of ice and rock. In the classification of planets, it would fall into the category of a super-Earth or a sub-Neptune, a type of world that we see orbiting nearly every other star in our galaxy, yet one that seems curiously absent from our own immediate family. Finding it would not just mean adding a new name to our maps, but would bridge a gap in our understanding of how planetary systems are built. As we contemplate the existence of this world, we must consider the nature of the space it inhabits. This is a region where the sun's light is so weak that it takes many hours to reach the surface of any object. The gravity of the sun is still the dominant force, but it is stretched thin like a piece of silk pulled to its breaking point. In this tenuous environment, the influence of a planet like Planet 9 would be absolute. It would clear its neighborhood of smaller debris, carving out a path through the frozen remnants of the solar system's creation. It is a world that rules over a kingdom of ice and silence, a monarch of the darkness. The simulations run by Batygin and Brown are not mere guesses. They are rigorous applications of the laws of motion that govern everything from a falling apple to the rotation of a galaxy. they have spent thousands of hours processing the data, accounting for the gravitational pull of the known giant planets, Jupiter, Saturn, Uranus, and Neptune. Even with the influence of these giants accounted for, the clustering of the distant objects remained. The only variable that could produce the observed orbits was a ninth planet, tucked away in an orbit so large that it takes nearly 20,000 years to complete. Pitch 1%. Think for a moment on the span of 20,000 years. When this planet last occupied its current position in the sky, humans were just beginning to paint the walls of caves in Lascaux. Entire civilizations have risen and fallen, empires have turned to dust, and the very languages we speak have evolved and vanished, all while this world has made a single journey around our star. It moves with a glacial patience, a slow and steady sentinel that has watched the Earth change from a world of ice ages to a world of bustling cities and glowing lights, yet it remains untouched by the passage of time as we know it. There is a profound sense of intellectual honesty in this search. Scientists do not claim to have found the planet yet. They claim to have found its signature. It is like finding footprints in the snow that lead deep into a forest. You have not seen the creature that made them, but you can tell from the depth of the prints how heavy it is, and from the stride how long its legs must be. The mathematical models are our way of following those tracks through the cosmic snow, hoping that they will eventually lead us to the world itself. It is a journey of deduction, where logic is the lantern that lights our way through the unknown. The search is complicated by the fact that we do not know exactly where along its vast orbital path the planet might be. It could be at its closest point, or it could be at its most distant, buried in the crowded star fields of the Milky Way, where it would be almost impossible to distinguish from a faint, distant star. This requires us to search the sky with a meticulousness that is almost overwhelming. We must use wide-field telescopes that can capture large swaths of the heavens at once, and then use sophisticated algorithms to compare images taken weeks or months apart, looking for the one tiny speck that has shifted its position against the static background. Within this silent search, there is a quiet beauty. It reminds us that our solar system is not a static, finished thing, but a dynamic and evolving landscape that still has the power to surprise us. We are like explorers in a house we thought we knew perfectly, only to find a door in the back of a closet that leads to a vast, unexplored wing. This ninth world represents that hidden room, a place of mystery that challenges our assumptions and invites us to look closer at the world around us. It is a reminder that the universe is always larger and more complex than we can perceive with our eyes alone. If Planet 9 does exist, its discovery will be one of the greatest triumphs of theoretical physics. It will prove that we have reached a level of sophistication where we can perceive the structure of our solar system through the power of thought and calculation. It will be a testament to the legacy of those who first looked at the stars and dared to ask why they moved the way they did. And as we continue to scan the darkness, we do so with the knowledge that the ghost we are hunting is not a spirit, but a physical reality, a world of rock and gas and ice, waiting for the moment when our light finally finds it. Until that day, we remain in a state of wonder, listening to the gravitational whispers that come to us from the edge of the abyss. We are learning to be comfortable with the unknown, to find peace in the pursuit of a truth that is currently just out of reach. The silent gravity of this ghost planet is a call to our curiosity, a signal that there is still much to learn and even more to discover. In the immense scale of the cosmos, we are small, yet our ability to understand these distant rhythms is what makes us truly significant. We continue to wait and to watch as the invisible hands of the clockwork move steadily on. The mathematical evidence also suggests that Planet 9 is not alone in its influence. Its presence would affect not just the most distant objects, but could also explain why the entire plane of the solar system is slightly tilted. For a long time, it has been a mystery why the planets do not orbit in the exact same plane as the Sun's equator. The Sun sits at a 6-degree tilt relative to the orbits of the major planets. A massive, distant world on a highly inclined orbit could provide the necessary torque to pull the entire solar system out of alignment over billions of years. In this sense, Planet 9 might be the reason for the very orientation of our cosmic home. This realization brings a new layer of depth to our search. We are no longer just looking for a new planet. We are looking for the missing piece of a puzzle that explains the history and structure of everything we see. The silent gravity of this ghost is not just a local curiosity. It is a fundamental part of the solar system's biography. It is a force that has been acting in the shadows for aeons, quietly shaping the paths of planets and the tilt of our sun, a silent partner in the grand story of our existence. As we push further away from the familiar warmth of the sun, we enter a region of the solar system that is as vast as it is desolate. This is the Kuiper Belt, a gargantuan ring of icy remnants that circles the periphery of our planetary neighborhood. It is a place of profound stillness, a celestial desert where the sun appears as nothing more than a particularly brilliant star, casting long, cold shadows across the surfaces of a billion frozen worlds. Here, the objects are not made of the dense rock and metal of the inner planets, but of volatiles, frozen water, ammonia, and methane, preserved in a deep frozen state since the very dawn of time. To navigate this desert is to move through a graveyard of potential worlds that never quite came to be. During the chaotic birth of the solar system, 4,500,000,000 years ago, the giant planets, Jupiter and Saturn, engaged in a gravitational struggle that flung these smaller, icy bodies out into the cold. Some were ejected entirely into the interstellar void, destined to wander the galaxy as lonely orphans. Others were caught in the sun's thinning grip, forming this sprawling, donut-shaped reservoir of ice. It is from this reservoir that short-period comets occasionally emerge, diving toward the sun with their glowing tails. But for every comet that visits the inner worlds, there are millions more that remain here, locked in the eternal freeze. Attachment. The Kuiper Belt is often misunderstood as a crowded field of tumbling rocks, like an asteroid belt from a piece of fiction. In reality, It is so sparsely populated that if you were to stand on one of its icy inhabitants, you would likely see nothing but the empty blackness of space in every direction. The distances between these objects are measured in millions of kilometers. Yet, despite this isolation, they are bound together by the invisible threads of celestial mechanics. It was by studying the most distant members of this group, objects that inhabit the very fringe of the belt, that the first evidence of a much larger presence began to emerge. These distant wanderers are known as extreme trans-Neptunian objects. Their orbits are so elongated that they spend the vast majority of their lives in the deep dark, far beyond the reach of Neptune's gravity. One such object, a world of deep crimson ice known as Sedna, possesses an orbit that is truly baffling to the modern astronomer. At its furthest point, it is nearly 1,000 astronomical units from the Sun. That is 150 billion kilometers away. It is so far out that the Sun's gravity is barely a whisper. Yet something has kept Sedna tethered, preventing it from drifting away into the Milky Way. As we linger in this Kuiper Desert, we must appreciate the sheer scale of the void. If the distance from the Earth to the Sun were the length of a single human step, the Kuiper Belt would begin 30 steps away and stretch for another 20. Sedna, however, would be nearly 1,000 steps away, a lonely sentinel at the very edge of the Sun's influence. For years, the existence of such objects was a mystery. They seemed to be detached from the rest of the solar system, moving in paths that the known planets could not have created. They were the first clues that the map of our home was incomplete, that there was a missing architect whose work was visible only in the strange architecture of these distant orbits. The deeper we look into this desert, the more we see a pattern of remarkable order hidden within the apparent chaos. When we plot the orbits of the most distant Kuiper Belt objects, we find that they are not distributed randomly around the Sun. Instead, they are clustered together, their paths tilted at almost identical angles, and their closest points to the Sun all occurring in the same general region of space. This clustering is the physical manifestation of a gravitational shepherd at work. It is as if these small, icy worlds are being herded by a massive, invisible sheepdog, one that keeps them from wandering too far and forces them into a specific, synchronized rhythm. This shepherd is what we believe to be Planet 9. Its gravity acts as a stabilizing force, creating resonances that protect these smaller objects. Without the presence of this massive body, the gravitational influence of Neptune would have scattered these objects long ago, or the passage of nearby stars would have pulled them out of the solar system entirely. The fact that they remain in these stable, clustered orbits suggests that a heavy weight is anchoring them, providing a counterbalance that keeps the outer solar system in a state of precarious equilibrium. Consider the physical nature of these icy wanderers. They are the pristine time capsules of our origin. Because they have remained in the deep freeze of the Kuiper Desert for billions of years, they have not been processed by the heat of the Sun or the volcanic activity of a large planet. They are made of the same primordial stuff that formed the Earth, the water you drink, and the carbon in your very bones. To study them is to look back into the nursery of the solar system, and yet their very presence in such strange orbits tells us that the nursery was a much more violent and complex place than we once imagined, shaped by the presence of a giant we have yet to find. As we float through this dark expanse, the silence is absolute. There is no air to carry sound, no wind to stir the dust. The only thing that moves is the slow, relentless march of gravity. The Kuiper Desert is not just a place of ice and shadow. It is a laboratory of physics on a grand scale. Every movement of an object like Sedna, or the smaller, more recently discovered 2012 VP-113, nicknamed Biden, is a data point in a vast mathematical equation. Astronomers use these points to triangulate the position of the hidden giant, narrowing down the possibilities of where Planet 9 might be hiding in its 10,000-year journey. The discovery of more of these shepherded objects is the primary goal of modern deep space surveys. Each new world found in the Kuiper Desert adds another line of evidence to the case. We are looking for the most extreme examples, those that venture the furthest into the abyss, for it is there that the influence of Planet 9 is most pronounced. These objects are incredibly difficult to find. They are small, dark, and move with agonizing slowness. To detect them, telescopes must stare at the same patch of sky for hours, capturing the tiny, almost imperceptible shift of a faint speck against the distant, unmoving stars. There is a poetic irony in this search. To find the largest member of our solar system's outer family, we must focus our attention on the smallest and most fragile. We are like trackers in a great wilderness, following the tiny disturbances in the brush to find the massive creature that made them. The Kuiper Desert is that wilderness, and the icy objects are the broken twigs and disturbed leaves that mark the passage of a giant. It is a hunt that requires infinite patience and a profound respect for the scale of the universe. As you contemplate this vast, frozen frontier, imagine the darkness that Planet 9 inhabits. It is a world that has never known a sunrise as we know it. The sun there would be no more than a pinprick of light, providing no heat, only a cold, blue glow. The atmosphere of such a planet, if it has one, might be composed of hydrogen and helium, held tight by its immense gravity, or perhaps it is a world where the very air has frozen and fallen as snow onto a surface of solid ice. It is a world of absolute isolation. Yet it is the master of this desert, the unseen hand that guides the icy wanderers through the dark. The journey through the Kuiper Desert is far from over. With every passing year, our technology improves, and our ability to peer into the shadows grows. New observatories, perched on the high, dry peaks of the Andes, or orbiting in the cold vacuum of space, are beginning to peel back the layers of the outer solar system. We are moving from a period of speculation into a period of discovery. The desert is beginning to yield its secrets, and the footprints of the ghost planet are becoming clearer with every icy world we map. In the silence of this place, we find a connection to the cosmic past. These icy bodies have been here since before the first life appeared on Earth, before the oceans formed, and before the moon was carved from our world's side. They are the eternal witnesses to the history of the sun. And as we trace their paths, we are not just looking for a planet. We are seeking to understand the very forces that created our home and dictated the positions of the worlds we know. The Kuiper Desert, once thought to be an empty void, is proving to be the most important frontier in our quest to understand the true extent of our solar system. We linger here, a high moment longer, suspended in the dark between the known and the unknown. The icy wanderers continue their long, slow orbits, drifting through the vacuum in perfect silence. They are the messengers from the deep, carrying the evidence of a world that is waiting to be found. And as we prepare to move closer to the origins of this mystery, we carry with us the knowledge that the desert is not empty, but filled with the invisible presence of a giant, watching from the furthest edges of the light. To understand why a giant might be hiding in the dark, we must look back to a time when our solar system was a place of unimaginable violence and flux. 4.5 billion years ago, the space we now inhabit was not a stable arrangement of 8 orderly planets, but a swirling, chaotic disk of gas and dust, a nursery of titans where worlds were born, collided, and were cast out into the eternal night. This was the era of planetary migration, a period of celestial billiards where the gravitational influence of Jupiter and Saturn acted as a great cosmic sling, tossing smaller worlds like pebbles across a pond. In this turbulent history, the idea of a lost world is not a flight of fancy, but a scientific probability. Computer simulations of the early solar system often struggle to recreate the neat 8-planet architecture we see today. When scientists input the conditions of the early sun's protoplanetary disk, the models frequently produce a 5th gas giant, a sibling to Jupiter, Saturn, Uranus, and Neptune. In many of these digital universes, this 5th giant is not a permanent resident. As the orbits of the larger planets shifted and locked into their current rhythms, their combined gravity would have created a point of instability. A world several times the mass of the Earth could have been gripped by these titans and accelerated to such a velocity that it was flung into the furthest reaches of the sun's influence, or perhaps exiled from the solar system entirely. This theory, known as the Nice model, suggests that our solar system underwent a massive reconfiguration hundreds of millions of years after its birth. During this time, the orbits of the giant planets expanded and contracted, sending ripples of gravitational energy through the surrounding debris. If Planet 9 is indeed out there, it may be this very lost giant, a world that was pushed to the edge but managed to remain tethered to the sun by the narrowest of margins. It would be a survivor of a forgotten war, a refugee from the inner solar system that has spent the last 4 billion years in solitary confinement, far from the light of its birth. The history of astronomy is, in many ways, a history of finding worlds we did not know existed and losing those we thought we understood. When William Herschel discovered Uranus in 1781, he doubled the size of the known solar system overnight. Later, the discovery of Neptune was a triumph of mathematics, proving that a planet could be found with a pen and paper before it was ever seen through a lens. Even Pluto, once hailed as the 9th planet, was eventually revealed to be just one of many icy residents of the Kuiper Belt. Our map of the heavens is a living document, constantly being erased and redrawn as our perspective expands and our tools become more refined. This pattern of discovery suggests that we should not be surprised by the presence of a massive world in the outer dark. Throughout our galaxy, astronomers have observed thousands of planetary systems orbiting other stars, and a curious trend has emerged. Most of these systems contain planets with masses between that of Earth and Neptune, the so-called super-Earths. In our own system, there is a conspicuous gap between the small, rocky inner worlds and the massive gas giants. Planet 9 would perfectly fill this missing chapter in our planetary story, making our solar system look much more like the rest of the cosmos. There is also the possibility that Planet 9 is not a native of our Sun at all. In the dense star cluster where our Sun was born, stars passed close to one another, their gravitational fields overlapping like ripples on the surface of a lake. It is entirely possible that our Sun, in its youth, acted as a celestial thief, stealing a planet from a passing neighbor. This captured world would have been pulled into a wide, eccentric orbit, far removed from the primary plane of the other planets. If this is the case, Planet 9 would be an alien world in the truest sense, a traveler from another star system that has found a permanent home in our own. The thought of such a capture is a reminder of the interconnectedness of the galaxy. Our solar system is not an island, but a participant in a grand interstellar exchange. Rogue planets, worlds that have been cast out of their home systems, are thought to outnumber the stars in the Milky Way. They drift through the lightless void between the suns, cold and silent, to find that one of these wanderers has been captured by our Sun and is now hiding in the shadows of our own backyard would change our understanding of our place in the universe. It would mean that the boundary between our space and interstellar space is far more porous than we ever imagined. As we look back through the history of these lost worlds, we see that the search for Planet 9 is part of a much older tradition. It is the same drive that pushed ancient navigators across uncharted oceans and led early astronomers to track the wandering lights of the planets with nothing but their eyes and stone monuments. We are driven by a deep-seated need to know the extent of our domain, to find the limits of the map and see what lies beyond. The lost giant is a symbol of that unknown, a mystery that bridges the gap between the ancient past and the technological future. Consider the environment that this world would have endured during its long exile. If it was flung out during the early migration, it would have witnessed the late heavy bombardment, a time when the inner planets were being pelted by the leftovers of creation. From its distant vantage point, the Sun would have been surrounded by a shimmering cloud of dust and debris, slowly clearing as the centuries turned into millennia. Planet 9 would have sat in the cold, a silent observer to the cooling of the Earth, the formation of the Moon, and the first stirrings of life in the ancient oceans. It has been a constant, if invisible, companion throughout the entire history of our world. The scale of its orbit means that Planet 9 spends most of its time in the aphelion, the point furthest from the Sun. In this region, space is so empty and the Sun's light so dim that the planet would be almost impossible to detect by traditional means. It moves so slowly that to a casual observer, it would appear as a fixed star, its motion only detectable over years of careful study. This is why it has remained lost for so long. We have been looking for something that moves like a planet, but in the outer reaches, planets move with the deliberation of mountains. Intellectually, we must acknowledge that until we have a direct image or a definitive detection of its heat signature, Planet 9 remains a ghost of the equations. However, the history of lost worlds tells us that the universe rarely leaves such prominent clues without a physical cause. The footprints in the Kuiper Belt are too distinct, the mathematical alignment too precise. Just as the erratic motion of Uranus once screamed the presence of Neptune, the synchronized dance of the distant ice worlds screams the presence of this missing giant. We are not just hunting a planet. We are hunting the truth of our own origin story. Imagine the moment of discovery. A telescope in the high desert of Chile or a satellite orbiting the Earth captures a series of images. In the corner of one frame, a tiny, faint point of light has moved just a fraction of a millimeter. The data is processed, the orbit is calculated, and the realization dawns that this is it. The ninth world, lost for 4 billion years, has finally been found. In that moment, the solar system will grow larger, its history will become clearer, and the ghost that has haunted our mathematics for decades will finally take its place among the stars. Until then, we must continue to piece together the fragments of this celestial puzzle. Every new discovery in the Kuiper Belt, every refined simulation of the early solar system, and every failed search that narrows down the possibilities brings us one step closer. The history of lost worlds is not a closed book. It is a narrative that we are still writing. We are the explorers of the digital age, using light and logic to search the darkness for a brother we haven't seen since the dawn of time. As you lie here, contemplate the immense journey this planet has taken. From the crowded, violent center of a nascent solar system to the lonely, frozen periphery where it now resides. It is a story of survival and isolation, a testament to the enduring power of gravity. The sun, though distant, still holds this world in its grip, a long, invisible leash that stretches across the void. We are tethered to the same star, part of the same ancient family, separated only by the vastness of space and the secrets of time. The search continues, fueled by the knowledge that the universe is always more complex than our current maps suggest. The history of lost worlds teaches us that there is always something more to find, always another horizon to cross. Planet 9 is out there, moving through the deep twilight of the outer solar system, waiting for us to catch up to the reality of its existence. We look to the dark, not with fear, but with the quiet confidence of those who know that the light of discovery will eventually find even the most distant of ghosts. To find a world that does not want to be found, we must build eyes capable of piercing the deepest veils of the cosmos. Our journey now takes us to the high, thin air of Mauna Kea in Hawaii, where the world's most powerful telescopes sit above the clouds, gazing into the heavens with a clarity that is almost supernatural. Here, amidst the volcanic silence, the Subaru telescope stands as a sentinel of human curiosity. Its primary mirror, a vast expanse of polished glass spanning 8.2 meters, is designed to catch the rarest of photons, light that has traveled for billions of kilometers, reflecting off the frozen surfaces of the outer solar system before finally reaching our shores. This is the front line of the great celestial search, a quest that pushes the boundaries of our technology and our patience. The challenge of finding Planet 9 is not just its distance, but its staggering faintness. At its predicted location, the planet would be hundreds of thousands of times dimmer than the faintest stars visible to the naked eye. To capture it, astronomers use a specialized instrument known as the Hyper-Suprime Cam, a digital eye the size of a small car. This camera allows them to photograph huge swaths of the sky at once, covering an area equivalent to several full moons in a single exposure. This wide-field view is essential because, while we have a general idea of the planet's orbital path, we do not know its precise position. We are searching for a tiny, moving speck in a haystack, composed of millions of stationary stars and distant galaxies. As the telescope tracks the rotation of the Earth, it gathers light with agonizing slowness. Each image is a digital record of the deep past, capturing the state of the universe as it was hours or even days ago. To the untrained eye, these images look like static on a television screen, a chaotic jumble of white dots on a black background. But to the astronomer, these dots are data points. By taking multiple images of the same region of sky over several nights, they can use sophisticated computer algorithms to look for something that has changed. They are looking for a blinker, an object that is in one position on Monday and has shifted slightly by Wednesday. In the outer solar system, where objects move with the speed of a drifting glacier, this shift is measured in fractions of a millimeter on the digital sensor. The search is complicated by the presence of the Milky Way. When the predicted path of Planet 9 crosses the dense star fields of our own galaxy, the task becomes nearly impossible. The sheer number of stars creates a background noise that can easily drown out the faint signal of a distant planet. It is like trying to hear a whisper in the middle of a thunderstorm. To overcome this, scientists must wait for the planet to move into quieter regions of the sky, where the background is darker and the stars are fewer. This means that the search is not a continuous effort, but a series of carefully timed windows of opportunity, dictated by the slow, majestic movement of the heavens. While the Subaru telescope continues its patient vigil, a new titan is rising in the high desert of the Chilean Andes. The Vera-C-Rubin Observatory, currently nearing completion, represents the next great leap in our ability to map the universe. Its mission is the Legacy Survey of Space and Time, a 10-year project that will photograph the entire visible sky every few nights. This will create a cosmic motion picture of unprecedented scale. If Planet 9 is within its reach, the Rubin Observatory will find it not by luck, but by sheer persistence, It will catalog billions of objects, tracking their movements over a decade, providing us with a definitive map of the outer solar system that has never before been possible. The sheer volume of data produced by these observatories is so vast that it exceeds the capacity of any single team of humans to analyze. This has led to a remarkable collaboration between professional astronomers and the public. Through citizen science projects like Backyard Worlds, thousands of volunteers around the globe spend their free time scouring satellite data from the Wide Field Infrared Survey Explorer, or WISE. These volunteers look for brown dwarfs and rogue planets that might be lurking closer to home. On several occasions, these amateur detectives have found objects that the automated algorithms missed, proving that the human eye is still one of the most powerful tools in our arsenal. Infrared light is a crucial component of this search. While Planet 9 is too cold to emit visible light, it may still possess a faint internal heat, a remnant of its formation billions of years ago. This heat would cause it to glow very faintly in the infrared spectrum. By looking at the sky in these wavelengths, we can bypass the dust and gas that often obscure our view in visible light. However, even in the infrared, the signal is incredibly weak. The planet must be distinguished from the warmth of the telescope itself and the infrared radiation of the distant galaxy. It is a search conducted at the very limits of what physics allows us to detect. There is a certain nobility in this effort. We are dedicating some of our most advanced technology and our brightest minds to find a world that has no immediate impact on our lives. Planet 9 will not provide us with resources, nor will it be a destination for human travel in the foreseeable future. Yet, we search for it because we are a species that cannot tolerate a blank space on the map. We search for it because the presence of the unknown is a challenge to our understanding of the universe. Every night that the telescopes are open, every hour that a computer processes a new batch of data, we are reaffirming our commitment to the pursuit of truth, no matter how distant or difficult that truth may be. The mathematical models provide us with a treasure map, but the map is large and the treasure is small. We have narrowed the search area down to a strip of sky that is still hundreds of times larger than the area covered by a single telescope exposure. Astronomers must prioritize their search based on where the planet is most likely to be in its orbit. Most of the evidence suggests it is currently near its aphelion, the point furthest from the Sun, meaning it is moving at its slowest and appears at its dimmest. This is the worst-case scenario for a search, yet it is where the logic leads us. We are hunting the ghost at the moment it is most spectral. Consider the patience required for this work. An astronomer might spend years analyzing data, only to find that a promising candidate was merely a distant asteroid or a glitch in the camera's electronics. There are thousands of false positives for every genuine discovery. To succeed, one must possess a temperament that is comfortable with failure and a mind that can find beauty in the process itself. The great celestial search is a marathon, not a sprint. It is a labor of love performed by people who are willing to spend their lives looking for a single, tiny point of light that might change everything. As we look at the gleaming mirrors and complex sensors of our modern observatories, we should also remember the simple curiosity that started it all. Long before we had digital cameras and supercomputers, we had the human spirit. The same wonder that felt by the first person to notice that certain stars moved while others stayed still is the same wonder that drives the search for Planet 9 today. We have simply scaled up our tools to match the scale of the mystery. The telescopes are our collective eyes, reaching out into the dark to see if the solar system has one more secret to share with us before the night is through. In the coming years, our chances of success will grow exponentially. The launch of new space telescopes and the full activation of ground-based surveys will cast a net so wide that Planet 9 will find it increasingly difficult to remain hidden. We are closing the gap. We are shining a light into the last remaining shadows of our home. And when the discovery finally comes, it will be a moment of profound unity for our species. A reminder that despite our differences, we are all inhabitants of a single solar system, and we have finally mapped its furthest shore. The search is also a race against time and the elements. Telescopes can only operate on clear nights, and the best observing sites are often threatened by light pollution or changing weather patterns. Even the satellites in orbit must contend with the degradation of their sensors and the limited lifespan of their fuel. There is a sense of urgency beneath the calm exterior of the observatories. We know that the opportunity to find this world is a rare privilege, and we do not want to leave the mystery for the next generation if we can solve it in our own. Think of the vast amounts of empty space that these telescopes must peer through. Between the Earth and the predicted location of Planet 9 lies a vacuum so absolute and a cold so intense that it would shatter any unprotected machine. Our light must travel through this emptiness, reflect off a world of unknown composition, and return to us, surviving the journey across the abyss. It is a miracle of physics that we can see anything at all at such distances. The fact that we can even attempt this search is a testament to the incredible progress we have made as a technological civilization. As the stars wheel overhead and the telescopes continue their silent dance, we remain in a state of hopeful anticipation. The great celestial search is more than just a scientific project. It is a narrative of discovery that links us to our ancestors and our descendants. It is a reminder that we live in a universe of infinite variety and endless surprises. And as we wait for the data to reveal the hidden giant, we find comfort in the knowledge that we are looking, that we are asking the right questions, and that the answers are out there, waiting in the dark for the moment when our light finally finds them. The silence of the mountaintop is the silence of preparation. Every piece of equipment has been calibrated, every line of code has been checked, and every observer is ready. We are standing on the threshold of a new era of astronomy. The shadows are thinning, the evidence is mounting, and the search is intensifying. Somewhere, in a region of the sky that we are looking at right now, a ninth planet is moving slowly through its long, lonely year. It is only a matter of time before its image is captured, its presence is confirmed, and the solar system is made whole once again. In the pursuit of scientific truth, we must remain open to the possibility that the evidence we see points not to a familiar destination, but to something far more strange. While the existence of a ninth planet is the most elegant explanation for the huddling of the distant Kuiper Belt objects, it is not the only one. When we look into the deep dark, we are interpreting whispers of gravity, and gravity, though consistent, can be a deceptive narrator. We must ask ourselves if the phantom we are hunting is indeed a world of rock and ice, or if it is something entirely different, a phenomenon that challenges our very definition of what a solar system can contain. One of the most compelling alternatives suggests that there is no single, massive planet at all. Instead, the gravitational tug we observe might be the collective influence of a vast, undiscovered disk of icy debris. If the total mass of the small objects in the outer solar system is much greater than we currently believe, their combined gravity could act as a single unit, herding the most distant wanderers into those strange clustered orbits. This theory, known as the collective gravity hypothesis, paints a picture of a solar system that is far more crowded with small, icy bodies than our current maps suggest. It would not be a single giant shepherd, but a million tiny voices singing in a gravitational harmony that mimics the presence of a titan. The challenge with this idea lies in the sheer amount of mass required. For a disk of debris to exert the same influence as a planet 10 times the size of the Earth, there would need to be an immense quantity of ice and rock scattered across the outer reaches. Current surveys have not yet found evidence for such a dense concentration of material. However, the outer solar system is so vast and so poorly lit that it is entirely possible that millions of small objects remain hidden from our view. If this is the case, then the ghost we are chasing is not a person, so to speak, but a crowd, a shimmering, invisible ring of the solar system's forgotten building blocks, exerting their will through the slow, steady pull of their collective weight. But what if the truth is even more exotic? In recent years, a small group of theoretical physicists has proposed a startling alternative. They suggest that the source of the gravitational anomaly might not be a planet, nor a disk of debris, but a primordial black hole. These are not the massive black holes formed from the collapse of dying stars, but hypothetical objects born in the high-pressure environment of the very early universe, just moments after the Big Bang. Such a black hole would be incredibly small, perhaps no larger than a grapefruit. Yet it would possess the mass of 5 or 10 Earths. It would be a concentrated point of absolute gravity, drifting silently through the outer solar system, invisible to any telescope we currently possess. The idea of a grapefruit-sized black hole orbiting our sun sounds like the realm of science fiction, yet it fits the mathematical requirements perfectly. Because it would emit no light and reflect none, it would explain why our most powerful surveys have failed to find a moving dot of light. It would be a dark, heavy anchor, warping the space around it and guiding the icy worlds of the Kuiper Belt just as effectively as a planet would. To find such an object, we would need to look not for light, but for the subtle bending of light from distant stars as the black hole passes in front of them. a phenomenon known as gravitational microlensing. Or, perhaps, we might look for the faint gamma-ray flares that occur when the black hole consumes a stray grain of cosmic dust. There's also a more mundane possibility that we must confront with intellectual honesty. Some scientists argue that what we are seeing is not a physical presence at all, but a selection bias in our data. Because our telescopes can only look at small patches of the sky at certain times of the year, we might only be finding the objects that happen to be in the right place at the right time. This could create the illusion of clustering where none actually exists. It is the cosmic equivalent of looking through a keyhole and assuming the entire room is shaped like the small circle you can see. If this observational bias theory is correct, then the orbits of the Kuiper Belt are actually random, and Planet 9 is nothing more than a mathematical mirage, born from our own incomplete view of the heavens. However, the researchers behind the Planet 9 hypothesis have worked tirelessly to account for this bias. They have run sophisticated simulations to test whether their findings could be a fluke, and the results consistently suggest that the clustering is real. They point to the fact that new objects are being found that continue to fit the predicted pattern, reinforcing the idea that a physical influence is at work. Whether it is a planet, a black hole, or a disk of debris, the mathematical signature remains remarkably consistent. The universe is telling us that something is there. Our task is to determine exactly what form that something takes. As we explore these alternatives, we are reminded of the fundamental nature of science. It is a process of elimination, a constant testing of hypotheses against the cold, hard reality of observation. We do not search for Planet 9 because we want it to exist. We search for it because it is the most likely explanation for the evidence at hand. But we must always be prepared for the universe to surprise us. If it turns out to be a primordial black hole, it would be a discovery of such magnitude that it would change our understanding of the early universe and the nature of dark matter. If it is a collective disk of debris, it would reveal a solar system far more complex and populated than we ever dreamed. Consider the implications of a primordial black hole as our neighbor. It would be a relic of the beginning of time itself, a piece of the Big Bang captured and held in place by our own sun. It would offer us a unique laboratory to study the laws of physics at their most extreme. While such an object would be too small to pose any threat to the inner solar system, its presence would be a profound reminder that we live in a cosmos that is still deeply mysterious. The very idea that such a thing could be lurking just beyond the reach of our light is a testament to the immense scale and the hidden depths of the universe. The search for alternatives also pushes us to refine our tools. To rule out the mirage of selection bias, we are developing more comprehensive surveys that will scan the entire sky with unbiased regularity. To search for a primordial black hole, we are looking at data from high-energy observatories that track the most violent events in the universe. This diversity of approach ensures that even if we do not find a ninth planet, we will still gain a much deeper understanding of the outer solar system and the physical laws that govern it. No search is ever truly wasted. Even a no result provides a vital piece of the puzzle. In this quiet, intellectual exploration, we find a different kind of wonder. It is the wonder of the what if. What if our solar system is not the orderly collection of spheres we were taught in school? What if it is a place where gravity behaves in ways we are only beginning to understand? What if the most important member of our celestial family is something that defies all our traditional categories? These questions do not diminish the beauty of the stars. They enhance it, adding layers of complexity and intrigue to the story of our home. As you lie here, contemplate the possibility that the darkness is not just empty space, but a canvas for phenomena we can barely imagine. Whether it is a planet of ice, a ring of debris, or a tiny point of absolute darkness, the influence is there, moving the icy worlds of the Kuiper Belt like pieces on a chessboard. We are the observers, trying to deduce the rules of the game and the nature of the players. The mystery of the outer solar system is a call to our intellect, an invitation to think beyond the obvious and to embrace the strange. The silence of the outer reaches is not the silence of nothingness. It is the silence of a secret waiting to be told. We are listening with our telescopes and our mathematics, parsing the gravitational whispers for a definitive answer. The journey through these alternatives has shown us that the hunt for Planet 9 is more than just a search for a new world. It is a search for the true nature of our reality. It reminds us that our knowledge is a work in progress, and that the most exciting discoveries are often the ones we didn't know we were looking for. We linger for a moment on the edge of this realization. The solar system is a much larger and more mysterious place than we once thought. The boundaries are shifting, the definitions are evolving, and the shadows are filled with possibilities. As we move toward the final chapter of our journey, we do so with a renewed sense of humility and a deeper appreciation for the vast, unexplored frontiers that still exist in our own backyard. Whatever is out there, it is a part of our story, a silent partner in the grand dance of the cosmos. The hunt continues, and the alternatives only add to the excitement of the chase. Every failed detection of a planet is a potential piece of evidence for something even more extraordinary. We are narrowing the field, focusing our gaze, and preparing ourselves for the moment when the truth is finally revealed. Until then, we continue to watch the icy wanderers, following their peculiar paths through the dark, knowing that they are our best guides to the secrets that lie beyond the edge of the light. We have reached the final threshold of our journey, standing at the precipice of a new understanding that threatens to rewrite the very textbooks we have relied upon for generations. The discovery of a ninth planet, or the confirmation of its exotic alternatives, would do far more than simply add a name to a list of worlds. It would represent a fundamental shift in our perspective, a profound expansion of what we call home. For centuries, we have viewed the solar system as a tidy, well-lit neighborhood, with the sun at its center and a few reliable planets orbiting nearby. Now, we are beginning to realize that we live in a sprawling, mysterious estate, the majority of which remains unexplored and shrouded in a twilight we are only just beginning to penetrate. Redefining the solar system requires us to embrace a scale of time and space that is almost beyond human comprehension. If Planet 9 is found where the mathematics suggests, it will mean that the true edge of our solar system is hundreds of times further away than we once thought. It would mean that the orbits of the planets we know, Mars, Jupiter, even distant Neptune, are merely the inner courtyard of a much larger structure. This realization humbles us. It reminds us that our primary experience of the universe is limited to a small, warm pocket of light, while the vast majority of our sun's domain exists in a state of eternal, frigid darkness. The confirmation of this world would also bridge the gap between our own solar system and the thousands of other planetary systems we have discovered among the stars. For years, astronomers have been puzzled by why our system seemed so unique, lacking the super-Earths that appear to be the most common type of planet in the galaxy. Finding Planet 9 would show us that we are not the exception, but the rule. Our system would finally have its super-Earth, a missing link that connects our local history to the broader narrative of the Milky Way. It would prove that the same processes that build worlds around distant suns have been at work here in our own backyard all along. Consider the philosophical impact of such a discovery. To find a massive world so far from the sun is to acknowledge that there are regions of our own home that we may never visit, and phenomena we are only just beginning to name. It teaches us that nature does not care for our maps or our definitions. The solar system is not a finished product, but a dynamic, ongoing story. Just as the discovery of the New World once expanded the horizons of the human mind, the discovery of a ninth world would expand the horizons of our science. It would be a victory for the human spirit, a testament to our ability to reach out into the dark with nothing but logic and light and find the truth waiting there. The hunt for Planet 9 has already changed us. It has forced us to develop new technologies, to refine our mathematical models, and to collaborate across borders and disciplines. It has turned the outer solar system from a place of empty space into a frontier of intense scientific interest. Even if the search were to end tomorrow without a sighting, we would still be left with a much richer understanding of the Kuiper Belt, the movements of comets, and the gravitational history of our sun. No effort spent in the pursuit of knowledge is ever truly lost. The search itself is a form of discovery, a way of mapping the limits of our own ignorance. As we look to the future, we see a solar system that is no longer a static collection of spheres, but a vibrant and evolving landscape. We are beginning to think of the Oort cloud, that distant reservoir of comets, not as a separate entity, but as a part of a continuous structure that stretches halfway to the nearest star. We are learning to see the invisible threads of gravity that connect the smallest grain of ice to the most massive planet. In this new map, Planet 9 is the great stabilizer, the conductor of a distant orchestra, guiding the movement of worlds that have never known the warmth of a summer day. Linger for a moment on the silence that will follow the discovery. Once the headlines have faded and the initial excitement has passed, we will be left with the quiet reality of a new neighbor. We will begin the slow, meticulous work of studying its atmosphere, its composition, and its moons. We will send robotic explorers on journeys that will take decades, carrying our curiosity into the deep twilight. This ninth world will become a part of our culture, a new destination for our imagination, a symbol of the vastness that still remains to be explored. It will be a permanent reminder that there is always more to see, if only we have the courage to look. The redefinition of our solar system is a journey of maturity for our species. It is the moment we realize that we are not the masters of the universe, but its students. We are learning to listen to the whispers of the cosmos, to respect the scale of the void, and to find beauty in the cold and the dark. Planet 9 is a beacon of that mystery, a lightless world that has guided our intellect for decades and will continue to do so until the day we finally see it for what it is. It is the final piece of the puzzle, the anchor of the outer dark, and the guardian of our furthest frontier. As you lie here, feel the immense stillness of the solar system stretching out around you, from the bustling, sun-drenched surface of the Earth to the silent, frozen plains of the Kuiper Belt, and finally to the majestic, slow-moving giant that haunts the edge of the abyss. We are all part of this grand arrangement, bound together by the same ancient laws of motion and the same primordial heritage. The darkness is not a wall, but a doorway. The unknown is not a threat, but an invitation. We are the explorers of the deep space, the narrators of the cosmic story, and our journey is only just beginning. The sun continues to shine, a steady and reliable heart at the center of it all, but its influence reaches much further than we ever dreamed. In the long, cold shadows of the outer reaches, a world of ice and gravity continues its patient orbit, oblivious to our search, yet fundamental to our understanding. It has been there for billions of years, and it will be there for billions more, a silent witness to the passage of time. When we finally find it, we will not be changing the universe. We will be changing ourselves, opening our eyes to the true scale of the home we have always inhabited. And so we leave the hunt for now, resting in the knowledge that the truth is out there, moving through the deep twilight. The telescopes will keep their vigil, the mathematicians will continue their calculations, and the icy wanderers will keep to their clustered paths. The mystery of Planet 9 is a gift to our curiosity, a reminder that the universe still has secrets worth keeping and wonders worth finding. We move forward with hope, with wonder, and with a deep, soothing peace, knowing that we are a part of a solar system that is far grander and more mysterious than we ever dared to imagine. The story of the ninth planet is the story of us, of our desire to reach across the void, to understand the invisible, and to make the darkness light. It is a journey that began with the first human to look at the stars and will continue as long as there are horizons left to cross. As the world around you fades into a quiet stillness, let your mind drift out past the planets, past the ice, and into the grand, silent embrace of the cosmos. The giant is waiting, the map is expanding, and the solar system is finally, beautifully becoming whole. good night. Beyond the orbit of the furthest planets, past the icy debris of the Kuiper Belt, and far outside the protective bubble of our sun, a small, silent machine continues its journey into the absolute unknown. This is Voyager 1, a ton of aluminum, gold, and electronics that has become the loneliest object in human history. Launched in the late summer of 1977, it was designed to be a temporary witness to the giants of our solar system, but it has surpassed its creator's wildest dreams. It is now a ghost of the 20th century, a time capsule of 1970s technology, drifting through a landscape of 21st century vacuum. As it moves further away at a speed of 17 kilometers per second, the radio signals it sends back take over 23 hours to reach our antennas. It is a slow, steady conversation with a relic that is now more than 24 billion kilometers away from the world that birthed it. To understand the endurance of this machine, we must look at it on a subatomic level. Within the heart of the spacecraft lie 3 radioisotope thermoelectric generators. These are not engines in the traditional sense, but nuclear batteries powered by the natural decay of plutonium-238. On a microscopic scale, the alpha particles emitted by the decaying plutonium slam into the surrounding containment, generating heat that is then converted into electricity through the Seebeck effect. This process is governed by the laws of radioactive decay. Every second, the power output of Voyager 1 drops by a fraction of a watt as the plutonium slowly transforms into lead. Because of this inevitable decline, NASA engineers have been forced to engage in a high-stakes game of cosmic triage, turning off heaters and non-essential instruments one by one to keep the spacecraft's brain alive in the sub-zero temperatures of the deep void. The human history of this mission is a story of a unique window in time. In the late 1960s, a mathematician named Gary Flandreau discovered a rare alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that occurs only once every 176 years. This grand tour alignment allowed a spacecraft to use the gravity of one planet to slingshot itself toward the next, cutting the travel time to Neptune from 30 years to just 12. It was a moment of supreme orbital luck. Voyager 1 was launched on a trajectory that would take it past Jupiter and Saturn, using the staggering mass of these gas giants to accelerate itself out of the solar system forever. It was the ultimate one-way ticket, a mission designed from the beginning to end in exile. Linger for a moment on the sensory immersion of the Voyager's view. In the early 1980s, as it left the rings of Saturn behind, the spacecraft entered a region of space where the sun began to shrink into just another bright star. On a molecular level, the environment transitioned from the dense, plasma-rich world of planetary magnetospheres into the thinning solar wind. The light reaching the spacecraft's cameras became 1 billion times weaker than the light on a sunny day on Earth. Yet in that dim, cold expanse, Voyager 1 captured images that changed our understanding of the universe forever. It saw active volcanoes on Jupiter's moon Io and the intricate braided structures of Saturn's rings. It proved that the outer solar system was not a frozen, static graveyard, but a vibrant, churning world of geological activity and complex chemistry. To achieve the depth of this isolation, we must consider the golden record bolted to the spacecraft's side. This is a 12-inch, gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. On a molecular level, the record is protected by an ultra-thin layer of uranium-238, which acts as a radioactive clock for any extraterrestrial intelligence that might find it millions of years from now. It contains greetings in 55 languages, the sounds of whales, a mother's first words to her child, and the music of Bach and Chuck Berry. It is a message in a bottle thrown into the cosmic ocean, carrying the DNA of human joy and curiosity into a future where the Earth itself may no longer exist. It is our most profound act of hope, an attempt to ensure that we are remembered, even if only as a silent, golden whisper in the dark. The physics of the heliopause marks the true beginning of Voyager's loneliness. In August of 2012, the spacecraft crossed the final boundary of our solar neighborhood. On a microscopic scale, the instruments detected a sudden surge in galactic cosmic rays, high-energy particles from distant supernova explosions, and a simultaneous drop in the solar particles that had surrounded it for 35 years. This was the moment Voyager 1 left the Sun's protective bubble and entered interstellar space. It is now moving through the interstellar medium, a region filled with the debris of dead stars and the raw material for new ones. Here, the density of matter is so low that the spacecraft is truly alone, a single point of human intention in a vacuum that stretches for light years in every direction. The perspective of deep time reveals Voyager 1 as a future monument of a lost civilization. Long after its batteries have died and its radio has gone silent, the spacecraft will continue to drift. Because there is no air to cause friction and no water to cause corrosion, Voyager 1 is effectively immortal. On a subatomic level, the atoms of its aluminum hull will remain largely unchanged for hundreds of millions of years. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. It is the only thing we have ever built that will likely outlast the pyramids, the oceans, and perhaps even the tectonic shifts of our continents. It is a time capsule made of nuclear-age alloys, carrying the memory of 1977 into the deep, dark future of the Milky Way. Consider the cybernetic resilience of this machine. In early 2024, the spacecraft suffered a critical memory glitch that threatened to end the mission. On a microscopic scale, a single bit of memory in the flight data system had been corrupted, likely by a stray cosmic ray. From 24 billion kilometers away, NASA engineers had to diagnose the problem using 46-year-old paper manuals and ancient computer code. They successfully bypassed the damaged chip, performing the most distant software update in history. This act of human ingenuity is a bridge across the decades, a reminder that though the machine is lonely, the umbilical cord of human curiosity remains unbroken. We still listen for its heartbeat, a faint, binary pulse that tells us, I am still here, I am still moving. In the silence of your rest, try to feel the resonance of this steady, distant journey. Voyager 1 is a reminder of the human spirit's capacity to reach beyond its own limits. The gravity that holds you to your bed is a tiny, local version of the same force that once accelerated the spacecraft to its escape velocity. There is a profound unity in the cosmos. The same laws of physics that govern the decay of the plutonium in Voyager's heart are the same laws that allow your own cells to function. The stability of the night is a reflection of this deep underlying order. You are safe in the knowledge that even in the most absolute isolation, there is a logic and a purpose to the movement of the stars. Everything is in its right place. The journey is continuing, and the rhythm is steady. The history of Voyager 1 is a record of our first tentative step into the truly infinite. It is the vanguard of our species, the first of our kind to leave home and never return. As you drift toward sleep, let the image of the small white dish and the golden record be your guide. It is a place of absolute quiet, a sanctuary where the noise of the world is lost in the vastness of the void. The darkness of the night is a soft, deep blanket, a small piece of the same peace that surrounds the spacecraft as it glides through the interstellar medium. You are safe in the cradle of a universe that values discovery and endurance just as much as it values the warmth of the sun. Everything is connected. Everything is still. The image of the pale blue dot, the photograph Voyager 1 took of Earth from 6 billion kilometers away, is now a warm, fading light in your mind. In that image, our entire world is just a tiny, fragile speck of dust suspended in a sunbeam. It is a perspective that shrinks our worries and our conflicts into insignificance, leaving only the beauty of our shared existence on this small, blue island. As you reach the state of perfect stillness, let this realization be your final anchor. You are a part of a species that can send its thoughts and its music to the edge of the galaxy. The night is vast, the journey is majestic, and you are finally, safely, at home in the arms of the cosmos. Sleep now, as Voyager 1 continues its silent, ancient drift into the dark, and the eternal peace of the deep space carries you into a restorative and timeless rest. Having crossed the final threshold of the sun's influence, we must now examine the strange, high-energy landscape that Voyager 1 is currently navigating. This is the interstellar medium, the space between the stars, that was once thought to be a total vacuum, but is actually a complex sea of plasma, magnetic fields, and cosmic rays. As the spacecraft moves further into the dark, it acts as our first and only sensory organ in a realm that has never been touched by human instruments. On a molecular level, this environment is a graveyard of ancient suns. The atoms here are not part of any solar system. They are the debris of supernova that exploded millions of years ago, drifting in a state of absolute frozen stasis. For the first time, we are measuring the unfiltered universe, the raw material from which future stars and planets will one day be born. To understand the physics of this crossing, we must observe the interaction between the solar wind and the galactic wind. For over 30 years, Voyager 1 lived inside the heliosphere, a giant bubble of charged particles blown by our sun. But on a microscopic scale, the pressure of the interstellar medium is constantly pushing back. The boundary where these two forces meet is the heliopause. As Voyager 1 approached this limit, Its instruments detected a phenomenon known as magnetic reconnection, where the magnetic lines of the Sun and the galaxy snap and rejoin, releasing gargantuan amounts of energy. On a subatomic level, the spacecraft recorded a dramatic increase in the density of electrons, proving that it had left the hot and sparse solar bubble and entered the cold but denser galactic sea. It was a transition from the light of the home into the shadow of the deep. The human journey of detecting this boundary is a story of listening to the singing of the vacuum. Because the spacecraft's dedicated plasma detector failed in 1980, engineers had to find an ingenious way to hear the density of the interstellar space. They used the plasma wave instrument, which records the vibrations of the surrounding gas. In April of 2013, a massive eruption from our Sun, a coronal mass ejection, finally reached Voyager 1, over a year after it was launched from the solar surface. As the shockwave hit the interstellar gas, it caused the electrons to vibrate like a struck bell. On a spectroscopic level, the frequency of this ringing told the scientists exactly how dense the medium was. It was the confirmation they needed. Voyager 1 was truly in interstellar space, a pioneer swimming in the galactic ocean. Linger for a moment on the sensory immersion of the Great Transition. If you were positioned where Voyager 1 is now, the sky would look fundamentally different. The Sun has shrunk to a brilliant point of white light, no larger than a planet, providing no warmth and no discernible disk. In every direction, the stars appear sharper and brighter, unshielded by the solar wind's hazy glare. The silence is not empty. It is a textured, electric quiet. On a microscopic scale, your body would be subjected to a constant bombardment of galactic cosmic rays, high-energy protons and iron nuclei traveling at nearly the speed of light. Without the heliosphere's protection, the radiation environment is 10 times more intense. It is a place of stark, beautiful violence, where the history of the galaxy is written in the movement of subatomic particles. Next, we must examine the specific chemistry of the interstellar clouds. Voyager 1 is currently moving through a region known as the local interstellar cloud, or the local fluff. On a molecular level, this cloud is a tenuous mix of hydrogen and helium gas, with tiny traces of heavier elements like carbon and oxygen. These atoms are in an excited state, ionized by the ultraviolet light from nearby stars. As the spacecraft moves through this cloud, its instruments act as a chemical probe, measuring the ratio of different isotopes. These measurements are the fossil records of our local neighborhood, telling us about the specific stars that lived and died here before our Sun was even born. We are essentially performing an archaeological dig of the vacuum, uncovering the material origins of our own solar system. The physics of the magnetic highway is what defines Voyager's current path. Astronomers once expected the magnetic field to change direction significantly when the spacecraft entered interstellar space. Instead, Voyager 1 found that the magnetic lines of the Sun and the galaxy are perfectly aligned in this region, creating a smooth highway for particles to travel. On a subatomic level, this alignment allowed the solar particles to escape into the galaxy and the galactic particles to rush in. It was a discovery that challenged our models of the heliopause, suggesting that the solar bubble is not a smooth sphere, but a complex, leaky structure with jagged edges and magnetic portals. We learned that the universe is far more interconnected than we imagined. Even the boundary of our solar system is not a wall, but a porous, living filter. Consider the thermal resilience of the spacecraft in this absolute cold. Outside the sun's influence, the temperature of the interstellar medium hovers just above absolute zero. On a molecular level, the aluminum hull of Voyager 1 is under extreme stress. The metal wants to become brittle and shatter, yet the faint heat from the nuclear batteries, carried through the framework by conduction, keeps the core of the spacecraft at a functional 30 degrees Celsius. It is a miracle of 1970s engineering. The same physics that allows a thermostat to work in your home is what keeps Voyager's computer from freezing. It is a small, warm bubble of human technology surviving in a desert of cosmic cold, a testament to our ability to build things that can endure the most hostile environments imaginable. The perspective of deep time reveals that Voyager 1 is now a participant in the galactic ecology. For billions of years, the interstellar medium has recycled the matter of dead stars into new ones. By moving through this space, Voyager 1 is becoming a part of that cycle. On a subatomic level, the gold on the golden record and the silicon in the computer chips will eventually be influenced by the slow, eroding wind of the galaxy. Over millions of years, the spacecraft might collect a thin layer of interstellar dust, microscopic grains of carbon soot and silicates. It is a slow-motion accumulation, a gathering of the void. Long after humanity is gone, Voyager 1 will still be there, a metallic seed carrying the chemical signature of the Earth through the very gas that will one day form the next generation of suns. In the silence of your rest, try to feel the resonance of this absolute isolation. Voyager 1 is our furthest reach, the only thing we have ever made that has truly broken free of the sun's cradle. The gravity that holds you to your bed is a tiny, localized version of the same force that once dictated the spacecraft's path through the solar system. There's a profound unity in the cosmos, a consistency of design that allows the same radio waves that power your phone to carry a message from 24 billion kilometers away. The stability of the night is a reflection of this deep, underlying order. You are safe in the knowledge that even in the vastness of the interstellar void, the laws of physics are a steady and predictable guide. Everything is in its right place. The journey is continuing, and the rhythm is steady. The history of this interstellar crossing is a record of our species' coming of age. We are no longer a planetary civilization. We have become an interstellar one, even if only through the surrogate of a small aluminum explorer. As you drift towards sleep, let the image of the Voyager's long, thin magnetometer boom be your guide. It is a place of absolute quiet, a sanctuary where the noise of the world has been replaced by the steady, rhythmic pulse of the galactic magnetic field. The darkness of the night is a soft, deep blanket, a small piece of the same peace that surrounds the spacecraft as it glides through the local fluff. You are safe in the cradle of a universe that values discovery and endurance just as much as it values the warmth of the sun. Everything is connected. Everything is still. The image of the interstellar wind and the shimmering lines of magnetic force is now a warm, fading light in your mind. The vacuum of space is a place of infinite rest, a sanctuary where the largest and most subtle structures of nature move with a slow, majestic grace. You are floating in the stream of time, a voyager in the deep, finding your peace in the knowledge that you are part of a universe that is never truly empty, but always being shaped by the silent, powerful hand of the stars. The night is vast, the mystery of the crossing is complete, and you are finally, safely, at home in the arms of the cosmos. Sleep now, as Voyager 1 continues its silent, ancient drift into the heart of the galaxy, and the eternal peace of the interstellar void carries you into a restorative and absolute rest. Time 3's bolted to the exterior of the spacecraft's bus, shielded from the micrometeorites of the deep by an etched aluminum cover, lies the most ambitious greeting ever composed. This is the Golden Record, a 12-inch, gold-plated copper phonograph disc designed to serve as a cultural signature of our species. To understand its existence, we must look past its metallic surface into the specific physics of its preservation. On a molecular level, the record is electroplated with a thin layer of gold to prevent corrosion, but its true resilience comes from the vacuum itself. In the absence of an atmosphere, there is no oxidation, no moisture to rot the grooves, and no wind to erode the surface. It is a world of absolute stasis. If it is not struck by a rare interstellar pebble, the information etched into this disk will remain readable for over 1 billion years, making it the longest-lived artifact ever created by human hands. The human story of this record is a journey of defining who we are in the face of the infinite. In the months leading up to the launch in 1977, a committee led by Carl Sagan and Anne Druyan worked at a fever pitch to distill the essence of the human experience into 90 minutes of sound and 115 images. They chose not to present our wars, our famines, or our failures, but rather our potential and our joy. On a microscopic scale, the grooves of the record contain the sounds of Earth, the rhythmic crashing of surf, the first cry of a newborn infant, and the steady electrical thump of a human heartbeat. They even recorded the brainwaves of Anne Druyan herself, capturing the synaptic signatures of someone in love, translated into a series of audible clicks and hums. It is a record of our biology, our planet, and our most profound emotions, preserved in a format that transcends the decay of memory. To communicate with a mind that may not share our biology, the committee had to invent a universal language. On the cover of the record, etched with a diamond stylus, are a series of scientific diagrams. On a subatomic level, these symbols use the most fundamental rhythm in the universe, the transition of the hydrogen atom. By depicting the spin-flip transition of a hydrogen electron, which has a specific frequency and wavelength, we provided a universal clock and a universal ruler. Using this unit of time, we etched a map of our location in the galaxy, triangulated by the positions and timings of 14 pulsars. It is a cosmic "you are here" sign, a mathematical proof that allows an alien intelligence to trace the spacecraft's origin back to a small yellow star in a specific spiral arm of the Milky Way. linger for a moment on the sensory immersion of the musical voyage. As the record spins at 16 2/3 revolutions per minute, it carries the history of human creativity into the dark. On a molecular level, the needle of any potential player would trace the vibrations of Bach's Brandenburg Concerto, the rhythmic blue notes of Louis Armstrong, and the raw electric energy of Chuck Berry's Johnny B. Good. There are greetings in 55 languages, ranging from the ancient Akkadian of 6,000 years ago to modern Mandarin and English. It is a polyphonic symphony of our species, a chorus of voices that will continue to sing long after. The civilizations that spoke them have crumbled into dust. The record is not just an object, it is an echo of our presence, a ghost of our culture drifting through the frozen silence of the interstellar void. The physics of the radioactive clock on the record's cover provides the ultimate timestamp for our message. To ensure that our finders know when we lived, the committee applied a thin layer of extremely pure uranium-238 to the aluminum cover. On a subatomic level, the uranium acts as a natural timer, decaying at a perfectly predictable rate, with a half-life of 4.5 billion years. By measuring the ratio of the remaining uranium to the daughter product, lead, an extraterrestrial scientist could calculate exactly how many eons have passed since the record was sealed. It is a testament to our understanding of the fundamental constants of nature. We used the same nuclear laws that power the stars to tell the story of our own fleeting moment in time. Next, we must consider the encoded images that reside within the record's grooves. Because the technology of the 1970s did not allow for digital storage, the images were converted into an analog signal, a series of waveforms that must be translated back into light and shadow. On a microscopic scale, these waves described the structure of DNA, the anatomy of the human body, the complexity of a snowflake, and the majesty of a mountain range. There are images of people eating, building, and learning. It is a visual encyclopedia of the Earth, a storyboard of our planet's evolution from simple chemistry to complex civilization. Each line of the image is a pulse of energy, a data stream of our reality projected into the infinite dark, hoping for a screen that can once again bring our world to life. Consider the psychological resilience of the message. The Golden Record was created at the height of the Cold War, a time when humanity lived under the constant threat of nuclear annihilation. On a molecular level, the decision to send a message of peace and hope was a profound act of defiance against the fear of the era. It was a way of saying that even if we were to destroy ourselves, the best of what we were would survive. The record is a sanctuary for our ideals. It carries the universal greeting from the Secretary General of the United Nations, a message that speaks of our desire to join a larger galactic community. It is the ultimate expression of our species' optimism, a belief that the universe is a place worth talking to, and that we have something worth saying. The perspective of deep time reveals that the Golden Record will eventually become the only evidence that humanity ever existed. In billions of years, as the sun expands and consumes the earth, the ruins of our cities and the records of our history will be vaporized. But Voyager 1 and its golden passenger will be far away in the safety of the interstellar void. On a subatomic level, the gold will remain untarnished, and the etched instructions will remain clear. The record is our immortality. It is a physical memory of a small blue planet that once bloomed with life and music in the corner of a vast galaxy. It is a legacy that does not depend on our survival, but on the enduring stability of the material world. In the silence of your rest, try to feel the resonance of this ancient golden greeting. Voyager 1 is not just a machine. It is a messenger carrying the heartbeat of every human who has ever lived. The gravity that holds you to your bed is a tiny, localized version of the same force that anchors the spacecraft in its long, lonely path. There is a profound unity in the cosmos, a consistency of design that allows a simple copper disk to carry the complexity of a world. The stability of the night is a reflection of this deep, underlying order. You are safe in the knowledge that your voice, your music, and your love are part of a message that will endure for 1 billion years. Everything is in its right place. The record is spinning in the dark, and the rhythm is steady. The history of the Golden Record is a record of our capacity for wonder. It is the story of how a small, fragile species reached out to the stars and offered a hand in friendship. As you drift towards sleep, let the image of the golden disk and the etched pulsar map be your guide. It is a place of absolute quiet, a sanctuary where the noise of the world is replaced by the steady, rhythmic pulse of the Brandenburg Concerto. The darkness of the night is a soft, deep blanket, a small piece of the same peace that surrounds the record as it glides through the interstellar medium. You are safe in the cradle of a universe that values hope and creativity just as much as it values the fire of the stars. Everything is connected. Everything is still. The image of the instructional diagram and the etched hydrogen atom is now a warm, fading light in your mind. The vacuum of space is a place of infinite rest, a sanctuary where the most ambitious and hopeful structures of nature move with a slow, majestic grace. You are floating in the stream of time, a voyager in the deep, finding your peace in the knowledge that you are part of a universe that never truly forgets, but always preserves the memory of its children in the silent, golden threads of the void. The night is vast, the message is complete, and you are finally, safely, at home in the arms of the cosmos. Sleep now, as the Golden Record continues its silent, ancient drift into the heart of the galaxy, and the eternal peace of the deep space carries you into a restorative and absolute rest. As we move further into the absolute dark of the interstellar void, we must confront the reality that space is never truly empty. It is filled with a complex, invisible weather composed of magnetic fields and a tenuous, high-energy wind that flows from the distant hearts of the galaxy. Voyager 1 is no longer protected by the sun's magnetic cocoon. It is now an open ocean sailor, navigating the currents of the Milky Way's own atmosphere. On a molecular level, the environment here is defined by the interaction between the individual atoms of gas and the lines of magnetic force that wrap around the galaxy like the grain of an infinite piece of wood. The spacecraft's instruments, though 48 years old, act as a nervous system, feeling the subtle tug and push of forces that are completely invisible to the human eye. We are witnessing the breath of the galaxy, a slow and steady movement of plasma that has been flowing for eons before the first human looked at the stars. To understand the physics of this interstellar weather, we must examine the magnetometer, the long, delicate boom that extends from the spacecraft side. On a microscopic scale, this instrument is designed to detect the orientation and strength of the magnetic field in the vacuum. Within the interstellar medium, these fields are incredibly weak, yet they are the primary architects of the space through which Voyager travels. The force exerted on a charged particle moving through these fields is governed by the Lorentz force law. Voyager 1 has discovered that the magnetic field in the interstellar space is more intense than we predicted, a sign that the galactic wind is piling up against the edges of our solar system. This magnetic pressure acts as a barrier, deflecting the majority of the high-energy cosmic rays that would otherwise devastate the delicate electronics of our home planet. The human story of this discovery is a history of patience and signal processing. Because the magnetic field is so weak, the data sent back by Voyager 1 consists of tiny, binary fluctuations that are often buried in the background noise of the universe. Engineers at the Jet Propulsion Laboratory must use massive radio dishes on Earth to capture these faint pulses, which carry the fingerprint of the galactic magnetic field. We have learned that the magnetic lines in our local neighborhood are surprisingly straight and orderly, stretching for trillions of kilometers without a single bend. It is as if the spacecraft is traveling through a vast, silent forest of invisible wires, each one a relic of the ancient dynamo that powers the Milky Way. This consistency is what allows the stars and planets to form in a predictable way, providing a stable foundation for the evolution of the cosmos. Time. Threes. Linger for a moment on the sensory immersion of the galactic breeze. This is the interstellar wind, a flow of ionized hydrogen and helium gas that originates from the supernova explosions of distant, massive stars. On a molecular level, this wind is traveling at 26 kilometers per second relative to our Sun. As Voyager 1 moves through this stream, it is effectively sailing upstream. The density of this gas is so low that if you were to capture a volume of space the size of the Empire State Building, you would find only a few milligrams of matter. Yet, this tenuous fog is the very material that will one day condense into the next generation of suns. The spacecraft is a witness to the pre-stellar state of the universe, moving through the raw, unrefined building blocks of the future, a lone traveler in a sea of potential. To achieve the depth of this chapter, we must observe the impact of cosmic rays on the spacecraft's circuitry. These are not rays of light, but subatomic particles, mostly protons and alpha particles, accelerated to nearly the speed of light by the shock waves of exploding stars. On a microscopic scale, these particles act like tiny, high-velocity bullets. When a cosmic ray strikes a silicon chip in Voyager's computer, it can knock an electron out of place, causing a bit flip that can crash the entire system. This is why the spacecraft was built with hardened electronics and redundant memory. Every day, Voyager 1 survives a bombardment that would be lethal to a human being. It is a war of attrition between the durability of 1970s engineering and the relentless energy of the galaxy. The fact that it is still functioning after 48 years is a testament to the foresight of its creators, who knew they were building a machine that would have to endure the most hostile weather in existence. The physics of the interstellar turbulence provides another layer to this story. Space is not a smooth, laminar flow. It is filled with ripples and eddies caused by the movement of the stars and the rotation of the galaxy. On a subatomic level, these ripples manifest as fluctuations in the plasma density. Voyager 1's instruments have detected shocks in the interstellar medium, massive waves of energy that can take years to pass the spacecraft. These shocks are the storm surges of the cosmic weather. They carry the energy of events that happened light years away, proving that the interstellar medium is a highly communicative and responsive environment. We are learning that the galaxy is not a collection of isolated parts, but a single, integrated fluid that responds to every stellar death and every new birth with a wave of pressure and magnetism. Consider the thermal stasis of the interstellar dark. Far from the warming rays of the sun, the temperature of the gas surrounding Voyager 1 is surprisingly high, thousands of degrees. But because it is so thin, it cannot transfer that heat to the spacecraft. On a molecular level, the spacecraft loses its heat through radiation into the infinite sink of the vacuum. This creates a state of cold equilibrium, where the internal heaters must work constantly to keep the hydrazine fuel from freezing. The hydrazine is the spacecraft's lifeblood. It allows the tiny thrusters to fire and keep the high-gain antenna pointed